My name is Andreas, and in this video we'll train a multimodal AI model from scratch and deploy it to the cloud. The model we will build accepts a video and finds out the emotion and sentiment of all sentences said in the video. We will then build a software as a service application allowing access to a trained model through an API so you can get a full insight into a real-world use case of AI. If you are new to AI, don't worry, we'll start with the absolute basics and build up to a finished model, and I'll explain all parts and decisions along the way. I will walk you through neurons, how neural networks work, and how we can train them. I'll explain concepts related to training, such as underfitting and overfitting, and how we can deal with these. We'll talk about representing data in deep learning and how video, text, and audio can be encoded such that a model understands it. We'll also use transfer learning to leverage existing models to improve the performance of our model. To train the model, we'll use the MELT dataset containing large amounts of training data from the Friends TV series. After the AI introduction, I'll first walk you through how we can load data into our system. Next, I'll introduce the model architecture, break it down, and explain every single part. We will then implement all the concepts in the code and test it locally. When we are ready to train the model, we'll use AWS SageMaker training jobs and use machines with powerful GPUs to train the model in the cloud. I'll also provide you with the model file if you do not want to train the model yourself, but you still want to follow along and learn. TensorBoard will also be set up so you can visualize training losses and accuracies and see how well our trained model performs. After training, we'll deploy the trained model on AWS SageMaker Endpoints and prepare it for production. Next, we'll build out a simple API software as a service application. Users will have monthly quotas from which they can use when calling our API, and this quota will be reset monthly. In the dashboard, they'll also be able to upload a video to test out the API. The user will be able to see the overall emotion and sentiment of the video, along with the emotion and sentiment for each sentence said in the video. We will also build out a sign up and sign in page for the user to keep track of the users and their quotas. The AI model will be implemented with the PyTorch framework, and the frontend will be built with technologies such as Next.js, Prisma, Tailwind, and React. So let's now go ahead and get started with the project. To get started with the project, first of all I open up Visual Studio Code, which is going to be the code editor for this project. We're going to work with Python for training the model and also doing inference. So I'm going to go ahead and search for Python right now. So if I search for Python PyTorch, the newest Python version is going to be Python 13. So Python 13 support for PyTorch. We will be able to see that it is not fully supported yet, PyTorch for Python 3.13, because it is still open. So we'll go ahead and install Python 3.12 instead. So if you do not have Python installed in your machine, you should go ahead and install Python 12. So you can go ahead and go to this page, head to download, and then you should be able to download Python from this page right here. So you'll be looking for a specific release, which is Python 3.12.8 probably. So you can press download and go ahead and install that if you do not have it already. You can then go to the Visual Studio Code again, and then we would like to create a new folder for our project. So first of all, I'm going to say open, and then head into my documents, repositories, and then press open. This is where all my code repositories are, so I can go ahead and say new folder inside of this. This one will be called Video Sentiment Model. And then I'm going to go ahead and say open again, and then head back to Video Sentiment Model, and then open up that folder instead. So now instead of being in the root folder, we are in the actual folder we would like to be. In here, we would like to create a Python environment. So I can go ahead and say view command palette, and then Python create environment. If you do not see this, you might need to install a plugin. So the ones I'm using for my setup are AutoPip8, Python Debugger, iSort, Python, and then Pylance. These are the ones I use for intelligence and debugging, for example, and they work very well for me. So go ahead and install these if you would like to have a setup exactly like mine. Great. So let me just go ahead and close that. So now if you press view command palette, then you should be able to see Python create environment like this. We're going to create an environment with venv. So we'll press enter, and then use Python 3.12. This is the version that I'm going to use. And then we'll just wait for this to download. And now it has been downloaded, so I'll just go ahead and close this. Open up a new terminal by right-clicking right here, pressing Open Integrated Terminal. And then I'm going to go ahead and search and say Python. And now we see Python 3.12, which is exactly what we wanted. So if I just close down this, like so, and then say PIP instead, like this. Then we should be able to see that the package manager works as well, because PIP is the package manager. Great. So this model that we're building uses a dataset for training called the MELD dataset, MELD. So I'm going to go ahead and say MELD dataset, and we'll just start downloading that already. And the reason we are starting to download it already is because it takes up about 10 gigabytes on your local machine, which is quite a bit. So if you have a slow connection speed, you might as well get it to download straight away, so you can do it as quickly as possible. And then in the meantime, I'll explain something about how the model works. So I'll just take this URL from Hugging Face, and because I'm on Mac, I'm not going to use vget, I'm going to use curl, but depending on whether you're on Linux or on Windows, you might want to use vget. If you're unsure, you can take this entire command, paste it into ChatGPT, and ask ChatGPT how to install it on your specific operating system. So I'm just going to copy this Hugging Face link without the vget, go into my terminal, and then I would like to say curl dash a big O because I'm on Mac, and then paste this in and press enter. And we should now see it start downloading. So right now it just failed actually. But if I do go ahead and just delete this, take the other link instead, like that, and then do the exact same just with the other link, we see that the total is 10.1 gigabytes and it received this many megabytes for now. And then you can see all the download information. So this will take a while, but it is well worth it because we're going to use this dataset for the entire project. So while we patiently await, we can talk about what exactly we're going to build. So what I envision is a model where you take a video as the sole input, and then the model will break that video into its components and run it through the model. The model will then extract the sentiment and the emotion from that video. So the sentiment can either be negative, positive, or neutral, and the emotion can then be joy, sadness, positive, etc. There are going to be 3 sentiments and then 7 different emotions the model can choose between. So right here in the MELD dataset, which is the one we're going to work with, what they have done is taken a bunch of episodes from Friends and then broken down the different episodes into transcripts, so utterances. So this is an utterance, this is just a short sentence, for example. So it could be you liked it, you really liked it. This is going to be surprise as the sentiment, surprise as the emotion, and then it's going to be positive as the sentiment, as you see down here at the labels. And then you can take another one, so oh yeah, for example, that will be joy as the emotion, and then it is going to be positive as the sentiment. So they have done this for a bunch of different clips from the Friends episodes, and that means they have a pretty big dataset actually. That is why it is 10 gigabytes large. So that is what we're going to work with. So because we have all of these video clips we can train the model on, we can then, after training it, give it a couple of videos that we make ourselves, for example, and then run it through the model and see if it can generalize what we trained it on, so these Friends episodes, to real life examples. So that is what I envision with this model. And the use case for a model like this might not be super obvious, but I'm sure that some people would need to use this model in some case. So a use case could be that you would have some customers submit a video in a feedback form. So this could be some customer feedback for your product or whatever. And then you could have an AI automatically determine whether the feedback is good or not. And that means you could just have an Excel sheet that is automatically being filled out whenever this model analyzes the videos the customers submit. So that is just a single use case I came up with, but I'm sure that there's a bunch of cases where people need to determine the sentiment and also the emotions of videos automatically without manually wanting to go through the entire video and do it themselves. Additionally, training a model like this, where you take a video and break it down into its components and then train the model itself and also run inference on it along with deploying the model, will give you a bunch of training in how an AI model actually works and really teach you the basics of AI, so that is why we're building this model in the first place. There is really no prerequisites for this video because I'll go through everything from how a neural network works and all the way up until we build it ourselves. So first of all, I'm going to go ahead and explain to you what a neural network is and how it works, pretty basically. So you might have seen drawings like these. So you have some input neurons, some output neurons, and then a couple of things between, some hidden layers, for example. You might have seen these or you might not. But each of these consists of neurons. So what we're trying to do with a neural network basically is the idea of just simulating how the brain works, because the brain does work in wonders. So maybe we can simulate that to create something that works pretty well for itself in computers. So the basic building stone of a neural network is a neuron. So this is just an abstract drawing of multiple neurons, but let me just go through how an individual neuron works and how we can build up a neural network with those neurons. So a neuron looks like this. A neuron is a little box like this, which has some math inside of it, and it also have a bias, and then it has two inputs and an output. So a neuron will do some computation for a given input and then use that computation to create the output. So in this case, we have two inputs. We have x1 and we have x2. These could just be two numbers, for example. And then the neuron has a couple of things. It has something called weights, first of all. So weights is what you see here, weight 1 and weight 2. So for each input, we have a weight for that specific input. That is those two lines right here leading into the neuron. And then for the neuron itself, we also have a bias, and that is the B you see right here. And then the output of the neuron is determined by a calculation based on both the weights right here, so the weight 1 and the weight 2, along with the input, so x1 and then also x2, not b2 here actually, and then along with the bias. So depending on what the weights and the biases are of this neuron, the output will change. So the magic of neurons is that you can put a bunch of these together, and then you can tune the weights and also the biases of these neurons to make it learn a pattern that you are going to teach it. And that is basically what we call training. So this is basically what we build up the neural network with. So from math class, you might remember a linear function. A linear function just looks like this. Y equals a constant times an input plus another constant, which is the bias right here. So right now you just see a linear function in here. That is a linear function, but researchers did find that linear functions made the model not be very smart when you scale up the model. So in addition to this linear function, we also wrap the output of this linear function inside an activation function, and that is what I have marked here with an F. So in total, that means that you have two inputs, and then the output will be determined on the weights, the inputs, the bias, along with the activation function right here. And we then have different activation functions for different purposes, so you can like make a model with specific activation functions. So sometimes in the model you might want some specific activation functions for a specific purpose, and then for other parts of the model you would like specific activation functions for another purpose. So that is what a lot of researchers try to do, come up with specific activation functions that can help them do specific tasks basically. So imagine you have 5 of these neurons and you take them without the activation function. You just remove the activation function, so it's just a linear function per neuron, and you put them in a sequence. What you end up with is just a sequence of 5 different linear equations, one after another. So scientists found out that they should put in these activation functions to avoid exactly that linearity, as they call it, to make the models able to learn even more. So that is why we have the activation functions, to avoid having just linear functions in a long sequence. So why activation functions? So without activation functions, the network would only contain a series of linear functions, just like I explained to you right before. And then the linearity prevents how smart the network can become. So we would like to introduce nonlinearity. So let me just give you an example of how these activation functions actually prevent nonlinearity. So this one is a specific activation function. This one is called sigmoid. So imagine you have a range of numbers. These go from minus infinity to infinity. So it'll take any number and then compress it to between 0 and 1. That is just one way to create this nonlinearity. Another one is relu, which is another activation function. This one only allows positive values to pass through. So this is a linear function if you just remove this part, for example. So imagine you have this linear function. This is just pretty linear, but we would like to avoid this linearity. So imagine we just remove all of these values that are below 0, and like this. That means we end up with a relu activation function, and this is not linear anymore. So that is exactly what we wanted. So these are just 2 examples of activation functions you might see when building out neural networks. So that is just the basic idea of why we need the weights and biases and the activation function. Weights and biases is to tune what the neural network is able to output based on the inputs, so we can train it basically. And then activation functions are to prevent linearity, which makes the network able to learn even more. So let's just go through what happens when we put these neurons together. So right here we have a small neural network that I've just built for an example. We have the activation function sigmoid, and then this linear function, and this will be the same for each of these. I have also set that all the weights and all the biases will be the same for each, just to make it simple. In real life, for each neuron, you have a weight for each input, and then you also have a bias for each neuron. But I've just set all of these for all of the weights and biases to be 0.5 for the weight, and 0 for the bias just to make the calculations easier. So in this little neural network, we have two inputs. We have 2 and 3, so 2 numbers, and we have a single output, which is the following one right here. So how do we take these inputs and determine the output? Well, we just run it through these functions for each neuron. So for the first neuron, for example, let me just take this and copy it. So for the first neuron, we can remove this because we only have a single input. The weight was 0.5. The x value was 2 because that is the input, and the b value is 0. This will become a 1. So we run through the sigmoid function, and that gives us a 0.73 as the answer. We do the same one for this one down here, which has 3, and we get the following answer right here. So for the next neuron, what we can do is take those values. So we can just take 0.73, and we can take 0.81, and then we can take the weights again, which is the same for the example, and we can add the biases, which is 0. So when running this through the sigmoid function, so this result right here, what we get is the following right here and right here. So as you see, the inputs for both of these are the same. You get these two inputs for both this one and this one. That is why the result of both of these becomes 0.68. Then you take these two inputs, do the exact same thing for the last neuron, and then the output will be the following one right here. So you see how dependent the neural network is on both the weights and also the biases. They are what determines the output from the input. So the magic of training this neural network is tuning this weight and this bias for each of these neurons, for each of the inputs of course, to learn a relation between the inputs in the network and then the output. So the weights and biases deeply influence the predictions, so we need to tune these to make the network more clever in the task we want to train it to do. So down here we have another example that I showed you just before. So what you can do is you have this little neural network right here, but this is a pretty small one. Normally you have way more inputs and way more outputs sometimes, and way more hidden inputs as well, or neurons. So based on how many inputs you have, you can scale up how many input neurons you have, and based on how many outputs you want, you can also scale up or scale down how many output neurons you have. And then if you want your model to be extremely complex and learn very complex behaviors, you can put in even more input neurons between the input and the output. And if you want it to be super simple, you can put in less of these neurons per layer. You can also scale up how many different layers you have. So this is just one single layer, but you can have multiple one of these, and for each of these layers, you can determine how many neurons there are per layer. So that is the magic of creating this neural network. It is just about finding out how many input and output layers you have, how many layers you want, what type of activation functions you have, and also how many neurons you want per layer. So it is quite a task to find out this, and it largely depends on testing. So right down here we have an example. We have a little neural network that is supposed to do some housing market predictions. So the inputs in this neural network is the square meters in a given house, the number of bedrooms, and then the age of the house. And the output of this neural network should be the price prediction, so what the neural network thinks the price might be for this house, and also how many days it'll take to sell the house whenever it reaches the market. So this one, and the two outputs will all be numbers. And then the developer can test out how many hidden layers they need, along with how many neurons they want per hidden layer, and also what type of layer they want. So the different types of layers depends on what types of activation functions each layer has. So this was a pretty small example of how a neural network works. You basically just connect neurons, and then you can take this input, run it through the neural network, through the activation functions, and then you'll obtain an output. Moving on, we can take a look at how we can train neural networks. So if we have a neural network that is supposed to get the housing price based on how many square meters there is in the house, at first, before training, it'll just give us a random guess basically, because it doesn't really know how the correlation between the inputs and the outputs are. So the output is really as good as a guess that you might give yourself. So we might give it 10 square meters, and then it might say $100 million, because it doesn't really know. So that is obviously an answer we can't use for anything because it is way off. So what we want to do is just train the model to learn the relation between the input and then how we can translate that into an output that is useful. So a method we use to train the network is called backpropagation. So here is a little example I prepared for you. Let's say we give the network a bunch of training data, and for each training sample, which is one sample of the training data, we say to the model, here is what an input might look like. And then we also say, here is what the result of that input might look like. So we give it basically the task and then also the result for that task. So just like a human would study math problems, for example, before an exam by looking at how the math problem might be done, along with how the answer is made, the model will be able to learn the correlation between what the input might look like and then what the output would then look like. So backpropagation is an algorithm we use to tune the weights to minimize how big the error that the model outputs is. So we give it an input, then we see whatever answer the model comes up with, and that is going to be the output. So for example, if the output is completely off, then we can go back again. That is why it is called backpropagation. We can then tune the weights so the error becomes a little bit smaller, and then we can try and run the input again and then see if the output is a little bit better. And by going back and forth like this, we can then train the model by tuning the weights. So let's say you, for example, study for a math exam and then you see 100 different math problems along with their 100 answers. That means you can probably learn a pattern between what kind of problems you might see along with what kind of answers you might want to give for each of these problems. So that is how you would learn in real life. So the model will also see a bunch of input data and then also see all the output data that corresponds to that input data and then learn the relations between those two. So hopping down to after training, what then happens? So let's say we give it an input. Here is an input kind of like the one you have seen before because we have given it all this training data. The model will then kind of say, aha, I recognize that, let me guess. And then the guesses are now way more likely to be correct because it has seen these types of problems before, and it can then learn the relation between the input and the output. So the data we use to train the model is called training data. And training data contains a bunch of samples, so you might hear sample a bunch of times when training AI models, and a single sample is basically one data point in the training data. So in training small models, you might use down to 100 samples, and for bigger models, you might use millions of samples. It really depends on the complexity of your model and what you want to train it to do. So a single sample contains a feature and a label. So up here, for example, where you have an input and an output, the feature is what you feed into the model. So hey, here's what an input might look like, and the label is then here's what the result of that input would look like. So the feature is the question, and then the label is the answer, if you have a math exam, for example. So this is what you want the model to input, and this is what the correct answer for that input is. So if you pass in 100 square meters, you would like the model to output $150,000. So given enough of these, this sample, this sample, this sample, and this sample, for example, if you give them a couple of thousand of these, the model will then learn the relation between the features and the labels. So when you give it a feature it has not seen before, it will then be able to generalize what it has learned and then guess a solution for the label that you need. So I talked about that we can use backpropagation to teach the model the relation between the input and the output, but what actually happens when we do train a model? So what we know is that when we use a model, for example, and we see up here, we have an input that is 10 square meters and an output that is $100 million. This is a pretty big error. So if you give it this small input of only 10 square meters, but $100 million in price, this is obviously super wrong. So we need some mathematical statistic to describe that this and this do not belong together at all. This is a big error, and then if this was smaller, then the error would also be smaller. So you can then have some mathematical statistic describing how big the error is, and then based on that you can optimize with backpropagation. So going down to what happens during training, first of all we need to measure how big the error is. And the error is what we call loss. So the bigger the loss, the bigger the error is. So this also means that the lower the loss, the better the accuracy of the model will also be. So in training the model up here, we have a couple of things. First of all, we have a sample with a correct answer and also a correct question, but we also have what the model guesses. So we can then take the difference between what the model actually guesses and what the model was supposed to guess, and that will then be the error. So to do this in a statistical way, we can do it with what we call mean squared error, which is one way to measure the loss or the error of the model. So for each prediction the model makes during training, we take the difference, which is right here, between what the model was supposed to guess, so the correct answer, compared to what the model actually guessed with inference. And this is then done for each prediction. That is why we have this variable n right here, and it is also squared, so it is also positive. So this will give us the mean of all the different errors because we divide by the amount of errors down here. So we call this number mean squared error, and it is a single number that represents how big of an error, how big the loss is for this neural network. So now that we know how wrong the neural network can actually be, we can then define training as lowering loss by tuning the weights and biases. Because that is what we want to do. If we lower loss, we know that the results up here will become more accurate, so lowering loss is just what we care about actually. So I have drawn up an example of a little network right here with a single input neuron and a single output neuron, and then two neurons in one hidden layer. And for the example's sake, we're going to say that the network has a loss of 2.5, and this is just a completely random number that I just made up. So the reason I've done this is to teach you that different weights and biases affects the loss differently. So if we tweak the weights and biases for this node, for example, then it'll affect the loss differently than if we tweak them the same way down here. And the reason that is important is because if we are to lower the loss, we need to know which weights and biases actually cause the loss. Because otherwise we won't know what in the model to fix to make it even better. So what this means is, in my little example, is that first of all we try to tweak the bias of B1 right here. So we take this bias, and I don't know what this is, but we just say we add 0.1 to that bias. So first of all the loss was 2.5, and now when we run the model the loss is suddenly 2.7. So the loss is a little bit better, a little bit worse. Then okay, we want to revert that because it made the loss even worse. And then instead we tweak the bias of this node right here. So we'll add 0.1 to that. And now we see that the loss is 2.0. So even though we made the same change to the bias for two different nodes, we get two completely different results for the loss of the model. So how our changes affect the loss greatly depends on which specific nodes or neurons we do change within the model. So that is very important to know. So what we have is the loss right here called mean squared error, and that depends on the true value and the guess of the model. So the loss depends on the model's predictions. And then we can say to improve the network, we just need to find out how each weights and bias affect the loss. So let's say we create a function down here called L, and that is the function where we can pass in all the weights and all the biases, and that will then generate a loss for us, so mean squared error. This would then be some kind of graph that shows how the different relations between these weights and biases combine to create specific losses. So we can then find minima and maxima to see where the losses are the biggest and where the loss is the smallest. But it is a pretty difficult function to do this with because it is pretty complex. It depends on both V1, V2, V3, and all of these different biases. And this is even just for a small abstracted model up here. What if we have millions of these neurons? Then we suddenly have way more computations to do. So how do we find out which of these, so which weights and which biases affect the loss, and then how they do affect the loss? So the way we can do that is with something called partial derivatives. So taking the partial derivative will give us a number describing how changing that specific variable changes the loss function. So the loss function again is a function that describes how big the loss is dependent on these variables, and then we can partially derive that function to find out how each of these variables affect the loss function. And then we can find out how we need to change each of the weights and biases to affect the loss function to become as small as possible. So this partial derivative of the loss function with respect to the first weights will then give us the slope of this graph down here. So down here we have a chart showing the loss, so the loss value of the loss function on the y-axis, and then the value of weight v1 on the x-axis. So obviously improving the model we do by finding the minima in this weight value function based on the gradients. So what this means is that when the loss is the lowest down here, that is where the best and most optimal weight value is. So up here, by taking this derivative, we get out a number, and that describes the slope of this graph. So if that number is negative, that means we are on this part of the graph because the slope of the graph is negative. So that means we are not in the optimal loss function, in the optimal weight value to optimize for the lowest loss. For example, if we get a weight that is a loss that is right here, we know that we need to increase the weight value to move further down this slope and then all the way down to here where the most optimal value is. So if the number is negative, we need to increase the weight value. If we are instead on this side of the slope because, of this side of the graph, because we have a positive number coming out of the partial derivative, we know we need to decrease the weight value to move further back and then find this optimal weight value. And then because the partial derivative is the slope, so how steep this graph is, this also means that the larger the partial derivative, the more sensitive the weight value change will also be. Whereas the smaller this partial derivative, the less sensitive this weight value change will then be. And the reason for that is if we take a graph, let me just draw another one over here. So if we take a graph like this, and then instead it looks like this. If we then take the partial derivative of the value right here, for example, we see that it is very steep. It goes almost straight down. So if we change the weight just a little bit, the loss will be greatly affected. Because if we have the weight value right here, the loss will be very high. But if we change the weight just a little bit to over here, the loss will be significantly smaller. This is the difference we're talking about. All the way up here versus all the way down here. So the greater the slope is, so the larger the partial derivative is, the more sensitive the loss function will be to weight changes. So I'll just go ahead and delete this and then move on. So going back up here, now we, for each of these variables that is used to determine the loss of the neural network, we can then determine whether we should increase or decrease the weights or bias. So this means that we can actually change these to make the loss smaller or bigger if we want to. Now, one algorithm to change these weights gradually to improve the model by decreasing the loss is called gradient descent. So what we do here is we improve the model by finding the minima in this weight value function based on the gradients. And the gradients is basically just a fancy word for saying the partial derivatives of the loss function with respect to these weights. So for each weight, we know which change we need to make to decrease the loss function. And then we just need to do this for each different weights until we have decreased the loss. So here we see a graph, we see the loss right here on the y-axis. So a smaller value is obviously better. So this down here is the best value. And then we see the value of the weight. In this case, it is going to be V1, this weight right here. And then that value is going to be on the x-axis. So the higher this value is, the more over here we are. The lower it is, the more over here we are. So there will be an optimal value for the weight, which will make the loss as small as possible. So taking the gradient up here, taking this derivative of V1, will give us the slope of this graph right here. So if this number right here is negative, then it means the slope is pointing down. So we'll be in this part of the graph, and if it is positive, we'll be on this part of the graph because we are moving up. So let's say we take the gradient and we get a negative number that is about right here. Now we do know that we need to move the weight value, or we need to increase the weight value to move further down this slope or further down this graph to find this optimal point right here. If we instead got a positive value, then we know we need to decrease the weight value to move it back and then find this optimal value right down here. Therefore, we can use this information to determine and calculate a new value of the weights to thereby optimize the loss function and increase the accuracy of the model. So a positive gradient means increasing the weight will increase the loss, so we decrease the loss. And a negative gradient means increasing the number will decrease the loss, so we do increase it. This also means that the larger the gradient, the more sensitive the weight changes will be, and the smaller the gradient, the less sensitive the weight gradients will be. And I can just take a little drawing pen and illustrate this over here. If I create a new graph, and then instead of this soft one, we have a U graph that looks like this. That's maybe a little bit too much. Now we see that we still have the weight down here, and we also still have the loss function on this axis. If we change the weight just a little bit, we see that the different points on this y-axis will be widely different. So just this little weight change right here will create a massive change in the loss, so it is very sensitive. If we instead make a change right here, then even the same change, it is basically the same in the width. Even the same change will make a much smaller change to the loss over here. So the larger the gradient is, the more sensitive the weight changes will be to the loss of the neural network. Now the only last missing piece is for each weight and bias we know in which direction to tweak them, so either this way or back, but we do not know how much to tweak them. So what we want to do is find out, should we tweak them a lot, so give them a massive jump to the right if they have a negative value, or should we give them just a little push to the right to make it just a little bit closer to this optimal value. So how we can determine this is based on a variable we'll set called the learning rate. And we'll also set this manually when training the model in PyTorch. So let's say we have the v1 value right here, the value of the weight, and we want to optimize that. So we'll make this little formula for optimizing the v1 value. So we'll just calculate what it should be. So we have a learning rate right here. If the learning rate is big, that means we'll make big jumps and take big risks because we might overshoot this minima and go all the way over here. But taking two small jumps will make sure that we almost do not get anywhere. So that's also something we do not want. So this learning rate will all make all the difference to how fast we're progressing. So if we want to calculate the new value of the v1 variable, we can use the old value of the v1 variable, and then we can subtract a term. So the term is going to be learning rate, so that is the constant we multiply this sensitivity by. So we take the partial derivative. The partial derivative will tell us whether to move to the left or to the right with the weight value, so to whether to increase it or to decrease it. And then we'll just multiply that by the learning rate. So if the learning rate is high, we'll make big jumps to the left or to the right. And if it is small, we'll make small jumps. And then we'll just make that change to the value that it currently is to hopefully move closer to this minima down here to make the loss as small as possible. So why not just apply the big learning rate when tweaking v1? And that is because we might overshoot it like we see down on this graph right here, but I'll come back to that in just a second. So every time we tweak a weight, all the partial derivatives might also change. So right here, if we take a partial derivative of this point, we see that the slope is around this slope right here. If we then change the weight a little bit, then we might have a weight that is down here instead now. Then we see that the partial derivative looks more something like this. So these two slopes will not be the same. So that is why changing the weights will always almost change this partial derivative. So just notice that changing the weight will change the partial derivative of both the weight that you just took the partial derivative to, but also all these other partial derivatives. So here is a visualization of how it looks whenever we try to optimize with gradient descent. This is where we have a very small learning rate, and the learning rate is symbolized with the length of this red arrow. So right here we have a very small learning rate. This is a little bit bigger of a learning rate, and this is a massive learning rate. So let's just look at how it happens right here. So in this example with a small learning rate, we can see that we have a weight value that starts right here. So this is the weight value, and that will give us this loss right here. And then we take the partial derivative of that, and it tells us to move in this direction to decrease the loss. So we need to increase the weight value. And then because we have a relatively small learning rate, we move a little bit down, and then we just say what is the partial derivative now. So then it tells us again we need to move in this direction. So we move down a little bit again. Then we take the partial derivative again, and then we just keep doing that. So we make very small increments down towards this minima right down here. But as you see, it takes a really long time. So we might have to train for a long time with a lot of data to make sure that we actually move down to this minima. So we don't really get anywhere, and we can also get stuck in local minima. So if the graph instead looked like this, then this is obviously the bottom we want to reach because it has the lowest loss, but this is also pretty low, so it might think that this is the minima bottom, the global minima, when it's actually just a local minima. That is because we only make small moves at a time, so it might not be able to escape this big ridge right here and get over to the global minima. So that is what we can avoid by making the learning rate a little bit larger than just a super small one. The next one is this one. This is an optimal learning rate. So here we can move down. We move down pretty quickly. We progress quickly, and then we find this global minima. We'll probably be able to escape local minima like we saw on the graph over here because we don't run into the same problem, and we can also train pretty quickly because we don't move so slow. The next problem we might encounter, so this is what we want. This is the optimal learning rate, And then another problem we might encounter is the opposite of the too small too small learning rate. This is a too big learning rate. So here we have massive jumps. So first of all, we take the gradient descent. It tells us to move down. So okay, we just move down a lot. So we move all the way down here. And now you see we're actually pretty close to this global minima. So that is pretty good. But now that we take the gradient, it again tells us to move in this direction. So now because we move this far at a time, we have to skip it and overshoot all the way to over here, because that is the only thing we can do with this massive learning rate. So now we're actually worse off than in the last iteration when we were down here. So now the loss is all the way up here, whereas before it was all the way down here. So now we overshot this global minima. So that is also what we want to avoid. So what I want to tell you about learning rates from looking at these graphs is just that you can try and play around with the learning rates, and then you might find an optimal learning rate that'll optimize your model way more than having it overshoot like this, or never getting anywhere like this with a too small learning rate. So hopping all the way down and going back to training, what can we now do to train the model? So first, we run a sample through the network and obtain the loss. Then we calculate the partial derivative for all the weights and biases. Then we update each weight and bias with using the learning rate and then also this partial derivative. So we start right here, for example. Then we calculate the loss. Okay, that's the loss right here. We can then calculate the partial derivative. It tells us to move down. So we move down using the learning rate, which is about this big. And now we're at this point. And then we just do the same until we're down here. Then we just do the same 2 more times. And now the model is as optimal as it can get. So that is how we're going to train the model. And when we reach this minima down here, it should then be as optimal as possible. Great. So the process goes like this. We show the model a bunch of samples, and remember the samples are a single data point in the dataset. And then the model learns. This is what we call training. And then the model improves such that it can generalize the samples to data it has not seen before. So if we run all the samples we have through the model, we call that one epoch. And we can keep running all the different samples through the model, and we call this running through multiple epochs. And when doing this, we should then see the loss generally become smaller like this, so decrease as more epochs are run through. And then at one point, the model has learned so much from the samples that it really doesn't learn that much anymore. And this is called when it converges. And then you should probably stop training around this point because you won't really benefit from using all that computation anymore. So that is really how we train an AI model. Now, going back up to the next point, this is how we train the AI model. So let's go over to another point, which is fitting, which is another thing we'll see when training an AI model. So we have underfitting, overfitting, and a good fit. These are 3 different cases that you might see during training. So whenever you do training, you have a constant battle between underfitting and overfitting, and then what you do want is a good fit, like you see right here. So let's take underfitting first. So let's say you have a bunch of data points. These are each samples. So this is just a sample, and this is what you know is true. What you want the model to predict is something down here, where it's pretty stable and can generalize to the data points. Right here with underfitting, you see that the model totally don't get that it is supposed to go up down here. It just continues down in a linear path. So it obviously hasn't found out what the pattern in the data is, and that is called underfitting. So when the loss doesn't really decrease a lot because it just stays high, it means that it is underfitting. So when you see it stay high like this, instead of going down like here on the good fit, it is underfitting, and you should probably reconsider whether you want to add more parameters. So the next case is called overfitting. So when overfitting, you have a model that maybe has too many neurons and too little data. There also might not be enough noise in the data. And these conditions can make the model able to learn all the nuances of the training data. So up here, so you see the training data goes down because it's super specific to the training data. You see how it fits perfectly. So that is pretty good for the training data, but it's very bad at generalizing what it has learned to the validation data. So that is why this validation data goes up, because the loss gets worse for the validation data because it can't generalize what it learned from the training data to the validation data. And then just as up here with the underfitting, the model is pretty much useless because you can't use it to generalize to other cases other than the training data. So that is another case. The last case is called the good fit. So that is where we have kind of a balance. You have enough parameters for the model to learn the patterns of the data, but you also do not have enough parameters or neurons in the model for it to be too specific to the data it is being trained on. So what you ideally want to see in this loss graph is that both your validation loss and also your training loss moves down simultaneously and just decrease over time as epochs move on. So as you run the sample data through the model over and over and over again. So that is what we want to do when we train a model. Now I have a couple of strategies down here for when you see any of these two cases, because when you do train a model, you are going to see these cases all the time. So whenever you do see these are the tactics you can use to avoid underfitting and overfitting when you do see them. So when you're underfitting, the model is probably just too simple. So imagine you have a really hard math problem, but you get a baby to try and do it. Like the baby is just too simple and it will not be able to learn the math problem. That is the same you have up here. It is just not smart enough to be able to learn the pattern of the data. So you can make the model even bigger by adding more neurons into the model. You can also maybe find out that the model is not trained enough. So maybe if you just train the model for one epoch, you don't really give it time to learn the data. So you might want to look into that as well. Lastly, if you have a too small of a learning rate, then it'll learn too slowly and it won't really improve over time. Also, if you have a too big of a learning rate, it might overshoot like we saw before as well, and it'll never find any good solution because it doesn't really find the bottom of this minima. Sorry, the minima of this graph, which is the bottom. And both this too small and too big learning rate results in a high training loss, so that is the underfitting. And now moving on to overfitting, as you see over here, this is where the model is super specific to the training data, but it doesn't really generalize to the validation data. So the model, when overfitting, is maybe too complex because you have too little data compared to how many neurons you have in the model. You might also not have enough data, so either you can have too many neurons or you can have too little data. You might also train too long. So as you see over here, the validation loss actually goes down at the first part, but then it starts rising again. So the optimal point to stop training is right about here when it starts rising again, because when it starts rising again, you see the loss gets worse, and that is not what we want. We want to stop it right before it starts rising again when the loss is at its lowest point. So maybe you have trained it for too long and then it started overfitting because of that. You can also use something called regularization tactics. So right here you see that the model is super specific to all the data. So what if you change this data a little bit every time so it doesn't really get a chance to memorize the data? That is one thing you can do. This is called regularization tactics. You can do this by adding noise or constraints. So you can add something called a dropout layer inside your model, for example. And this will help prevent overfitting. So this is just some of the knowledge you need to know before we start training the model. So far, when we go over here, we can see that we have just worked with the simple inputs. So right here, the input is just a number 2 or number 3, and the output is also just a simple number. But in real life, when you want to train a model, you might want to pass in a video or an image or text or something more complex. So let's talk about how we can represent data when training AI models. So to hold data, we use something called tensors. So a tensor is just a multi-dimensional array that holds data within our program. And you can think of these as just arrays where you just add more arrays inside of them to just nest the arrays and create more complicated or complex data structures. So a single number would just be a 0D tensor that just looks like this, just a single array basically. You can also have a vector that you might know from mathematics 2, and that would just be a 1D tensor because it has these numbers. Then you can also have a normal matrix, that would be called a 2D tensor, and then you could have a 3D tensor that would just look like this. So if you want to add more dimensions to your tensor, you can just add more arrays inside of the array. So this is how you can represent more complex data than just a single number. So let's take a video, for example. How would we take a video and represent that with tensors? So a video consists of frames, so just still images. Each still image has multiple channels, so a red, green, and a blue channel. And then each frame also have multiple pixels. So let's say we have a 4x4 image. This is a pretty small image, obviously, but just for the example. So this is how we could store that in a tensor. The video would be stored like this. So we say the video is equal to, and we just say torch.tensor, and then we store the video in this root array. And then the first frame would be stored in the following arrays right here. So This contains 3 different channels. So first of all, we have 3 frames. This is frame 1. We then have frame 2 right here. And we have another frame down here. So this is how we store each frame. And then inside each frame, we do have 3 channels. So we have this channel, the blue channel. We have this channel, which is the green. And we have this channel, which is the red. And then for each channel, we have a width and height. So the width can maybe be represented by having 4 elements inside of this array. Whereas we have the height being represented by having 4 of these width arrays inside of this array. So that is how we can store all of these different data inside a more complex data type inside PyTorch, or just whatever library we use to do neural networks in. And then if you go down, we can see that if we want to store text, for example, we can tokenize text, and there's a bunch of different tokenizers. One is called BERT tokenizer, and we'll see how that works when we create our model. But you can tokenize text to store that in a data format recognizable by the computer. And with audio, for example, this is how you would represent audio as a scientist. So you just take the sound or the strength of the audio signal on the y-axis, and then you have time, for example, on the x-axis. So if you yell very loudly, then the strength is very high, whereas if you just whisper, then you might have a very small signal like right here. So that is how you would represent audio. So in audio, you can also have an array where you store the different strengths of the audio over time. So when working with this data, when you do want to pass it into a neural network, then you need to define your input layer. So the input layer is how many neurons you have in the layer where you input your data. And this should match the format of whatever data you want to pass into it. So if you have a specific video format that you would like to have the neural network understand, you'll need to define the size of this tensor, and then make sure the input layer, so the amount of input neurons, also match that tensor. And then you can modify how many tensors are worked with inside of these hidden layers, and also what output you get from it. But you can then work with different data types using different tensor sizes. So that is basically just how we represent data inside PyTorch, or just in deep learning in general. We use tensors, which are just multi-dimensional arrays. Great. So let me just talk about what we are going to build. So as explained in the start, we are going to build a sentiment analysis model. So we pass in a video as the input to the model. The model will then output the sentiment and also the emotion. So if it's negative, positive, or neutral. And then also the emotion. So if it's joy, sadness, super happy, or something like that. And we will use this dataset called the MELT dataset from in here, which you have probably downloaded by now. And this dataset contains a couple of different things. So it contains videos, so these videos right here. It also contains the transcript of that video, and it also contains the audio of the video. So those are the features whenever we train the model, so the inputs for the model. And then the labels, so what we want the model to output is going to be the emotion, and then also the sentiment. And that is what the researchers behind this dataset has done for us. They have labeled all this training data with a surprise, positive, neutral, anger, negative, etc. for all of these training samples, such that we can train models on them. And because we have 3 different features, we both have the video, we also have the transcript, and we also have the text. We work with what we call a multimodal AI, so an AI model with multiple modalities. So going down, we need to break down these things into what we can actually put into the model. So the model should at the same time understand both what is a video, what is a transcript, and then also what is an audio signal, and how can we combine these and then learn from what this video is to how can we label the video with a positive, joy, surprise, negative, etc. So we can break this down. The features will contain a video, so we can break this into frames in a video. So we can have this stored the same way we do over here, basically, where we store the different frames inside a tensor. We can also encode the text with a tokenizer, so this will be the transcription. And then for the audio, we can take the audio signal and encode that inside a tensor, which we can also pass into the model. We can then combine all of these into a single tensor and then just input that into the model. So by giving the model both all the frames and also the transcript, along with also the audio signal, we give it a better chance of actually understanding the context of what we're trying to get it to do. It's just same as if you had to label a video with a joy, positive, so with an emotion and a sentiment from only looking at the transcription, that would be harder for you than if you also had the frames in the video and the audio signal, so if you could see the entire clip. It's the same as if you only could look at the images, then it might be hard for you to hear if somebody are negative or neutral or positive in their voice. So all of these things combined will give the model the best chance it has to understand what it is supposed to label. So that is why we build a multimodal AI, because we pass in multiple modalities, so multiple different kinds of inputs into the model. When training these multimodal AI models, we have a couple of different options. First of all, we can train a model from scratch. Second of all, we can also use something called transfer learning. So when training a model from scratch, we basically just convert all of these different data types into tensors, and then we put those tensors straight into some layers, and then we have those layers output some outputs. So that is what we do when we train from scratch. So we just make it ourselves from scratch, and it's a simple model, so we have full control because we do everything ourselves. We can also optimize the model for our specific task. It is also pretty small compared to this other option. And then what we can also do is run the data instead of just putting it straight into some layers that predict something. We can run the data through some pre-built models that will then extract some extra meaning from this data, which we can then run through these layers. So we can benefit from models that people have actually created already and get better results from that. So when we use extra models inside of our architecture, that obviously means we have a larger model size because we have multiple more models inside of our model. And it also means that we need to find models that actually fit our task. So there might exist models, but they don't really fit our use case. I'm sure that there are some models that fit our use case, though I know that. But for some use cases, that is not the case. So when we use training from scratch, we require more data because we have to train the model with a lot of data to learn to teach it everything from scratch. And this also means that we need to give it more training time, and then it also might underperform compared to this other option over here. So when we're using transfer learning, because we use these extra models in the start to understand the meaning of these things, we get better initial performance because we can benefit from using these existing models other people have trained. We can also use less data because those models that we do use from other people have been trained on a lot of data before us. And then we also can use architectures that are already proven inside of our model to make sure that we get even better results. So how would this transfer learning look for us when working with text and video, for example? So if we just took the text, for example, and converted it into a tensor and ran that through the model, what we would see is the model trying to understand the raw data and then predict something from that. So without a pre-trained model, so when just training it from scratch, there is no difference between these two scenarios. So imagine you have a bank with the money and then also a riverbank. Those two things are two completely different things. So you might say a fish swam by a riverbank, and that makes sense, but you can also say a fish swam by a bank with money, and that doesn't make sense at all. So a bank right here and right here are two completely different things, but they might be encoded in the same way with a tensor. So both is a bank, since a bank is encoded the same way. So a bank just contains 4 letters, so those 4 letters will be the same anyways, regardless of whether it's a bank with money or a riverbank. So when just taking text and converting it into a tensor and passing that tensor into the model might not know the difference between a riverbank and a bank with money, so it will lose some of the context that is actually stored within the text. If you do use a pre-trained model that has been built for this, the output of the pre-trained model will then reflect what kind of bank it is, so more context is preserved. So what I mean by this is that the model has been trained to distinguish between a bank with money and a riverbank, so the output tensor of that pre-built model will then also contain some of that context, so more of the context of the actual text will be preserved within the data that the model outputs. And that is because those pre-trained models that we will use will have been trained on a bunch of data before for specific use cases, so it is obviously good from the start and knows a lot of things without us even having to train the models. So that is the specific use case I want you to know for working with text and also using this transfer learning. So another example with working with a video, for example, with pre-trained models could be this. So imagine you just convert your video into frames and then the frames into tensors that you pass into the model. So the model might only see the brightness goes up and down, but the pre-trained model might be trained to identify that a person is nodding with the head while smiling, and it might know this because it can detect emotion, it can detect smiling from facial features, and it can also detect that the person is nodding from a specific sequence of actions. And these things are features from the video that the model will be able to extract from the video frames, so it won't just see the brightness going up and down, it'll actually extract what is happening inside the video and then preserve more context of the video, thereby giving us better accuracy with our model. So these two reasons are why we specifically use transfer learning, so using these pre-built models instead of just training everything from scratch. Great. So how can we do that? So a simple architecture could be that we take our video and break it into our frames, and then we can use something called ResNet 3D to just encode the video. So what it'll do is ResNet 3D is just a model that has been trained already, which will extract the context of the video. So like we see right here, person nodding with the head smiling, for example, that will be stored inside of the tensor that this model will output, so it'll preserve more context from the video. With the text, we'll run it through a model called BERTS. This is also another pre-trained model that will be able to distinguish between a bank with money and a riverbank, for example, because we won't really be able to do that unless we train on a lot of data and help the model understand the difference between these things. For the audio, our audio encoder is just going to take the audio and just convert it into a tensor, and then we can just take that tensor and pass it into the model in raw data format. So now we have 3 different data modalities we need to work with. We have the output of this ResNet 3D model, we have the output of this BERT model, and we also have this raw audio that we need to pass into the model. All of these needs to be passed into the model at the same time. So how do we actually do that? So what we need to do is just combine these, and we do this by something called fusion. So we fuse all of these data types together, and then we pass that fused data into the model at one time. So there is a couple of different ways of fusing data together. We have something called late fusion, early fusion, and then also something called intermediate fusion. So it all depends on when you want to combine the data. You can combine the data before passing it into the model. You can also run it through some models like this and then pass that into a fusion model. So there's a couple of different ways of doing that. So I'll just walk you through what options we have and why we've picked the one we have. So what we'll do is something called late fusion. So late fusion works like we see right here. We have 2 modalities. These are our 2 modalities, for example. This could be video, and then also the transcript of the video. We'll run each of these into 2 separate models, 2 separate pre-trained AI models, and then the result of each of these will run into another AI model, which we will train ourselves. We'll call this model the fusion layer, and from this we can then do some predictions. So this fusion layer will then learn the relationship between modality 1 and modality 2, along with predicting what the sentiment and the emotion is. The next way of doing it is down here with early fusion. So here with early fusion you have the 2 different modalities. So this could be a video, for example, and this could be the transcript of that video. We then manually extract the data from that video, so we could manually find some way to extract the different colors of the video. We could also manually find a way to extract the motion of the video and also do some object detection. And then we could store all of these different data from the video inside of a tensor, and then we could use that as the input to another model. So instead of just taking all the raw data and passing that into a model, we just manually extract the data about the video that we're interested in, and then train a model on that data. And we then just do the same for the text down here as well. So this is called extracting features from the modalities. So after extracting these features, we can then take each of these features, run them through another model, which we'll train ourselves, and then we'll just concatenate this data inside of another tensor, and then we can run that through a model which we'll train ourselves, which will then learn the relation between the different modalities, and then that can then make a prediction of what the model should predict, so the sentiment or the emotion. And then the last option is called intermediate fusion. In intermediate fusion, we just do a mix of both. So we take both modalities and then we extract the features, so the exact things we want to extract. And then we run those things through two separate AI models. So this can be a pre-trained model, but it can also be a model you train yourself. And then we take that and run it through a fusion layer. So we run it through a model and concatenate everything. And then we run that through another model, which will then learn the relationship between all of these things and then predict what the emotion and the sentiment. So this requires a bit more things because you have to both extract the features, run it through a fusion layer, and run independent AI processing for each of these modalities. This is like a lot more steps compared to just the late fusion up here, where you just use pre-trained models and then that's it. So we'll use late fusion because it is simply just the simplest way of going ahead. So I would just like to start simple, and then if there is a reason to go even deeper and go more advanced, you can always do that. And it is super simple because you can just use these pre-trained models from BERT, so BERT and then ResNet, which will just do all the hard work for you with preserving the context from the video and also the text. So it's simple because feature extraction happens implicitly inside these models, whereas down here, both in early fusion and in intermediate fusion, you need to extract the features yourself, such as object detection, motion vectors, etc. Whereas this ResNet model, for example, has already done that for you because that is what it has been trained to do. Also, it is more robust to missing data because feature extraction is automatic. So it has been trained on a bunch of data and seen a lot of things, these two models. So they will be pretty robust because it has been trained on that much data. Whereas down here, you'll need to extract the features yourself. So you need to train this model on the features you have extracted. So what you basically do is build the understanding that these models already have. And that of course gives you more control, but it also makes it harder for you if you do not want to do that from scratch. And that is not something we are interested in right now. So some of the drawbacks, just so you know it, is that we have more parameters inside the model because we both run this model right here, but we also run these two pre-trained models. So we do have quite a lot of parameters. We do not train all the parameters, but we do run inference for both these two machine learning models that has been pre-trained and also the one we're training ourselves. So the model will be slower compared to just training everything ourselves with early fusion down here, for example. And because the transcript and the video is very related because the transcript is the transcript of the video, there might also be some relationships between that data that might be missed because it is processed independently. So the text will be processed independently by this model and the video will be processed independently by this model, and then only the result of these models will be processed together in this fusion layer and combined. So if any data is lost inside any of these models, then we'll never know because it is not processed together from the start. It is processed independently and then fused together afterwards. So here is an example I can give you. It's like watching a movie with a friend and you both watch it separately in different rooms. So this is ML Model 1 and ML Model 2. You watch the two movies and then later you combine your opinions. That is what you do here with the fusion layer. So you actually are able to combine your opinions just fine, but you did miss out on the experience of discussing the movie together in real time. So that is what you miss out on if you just combine everything from the start. This is a pretty powerful approach and it is very simple too, so that is why I will go with it though. Going down to early fusion, this is super efficient because you can have full control over it. You only have to train your own model and not use these other pre-trained models. And then also that makes it faster. So one of the drawbacks is that it is more sensitive to missing data. So because these models up here have been trained on that much data, they are pretty robust. But if you train a model from the ground up, you'll need to train it with as much data probably as up here to make them just as robust. So if you just have less good data, then you might not get very good results training everything from the ground up like you do here with early fusion. Another thing is that you train the model with defining the data yourself. So this feature extraction might extract the RGB values for the video specifically. So the model will be trained on expecting that these RGB values will always be there. So because it is not as robust as up here, if you suddenly have a video where the RGB values are missing, then the model might act up and not give you very good results because it has been trained to expect exactly that from the beginning. So if you do not have that, it will not be very robust. So it is more sensitive to missing data. And now intermediate fusion down here, it combines the benefits of both because you get to define which features you would like to look on specifically right here. And then also you get to run it through the pre-trained models, which will preserve some of the context. But more components also requires tuning because it is a bigger model, and it also requires even more computations because you have even more components inside of this model. So it is just a way, if you want to really be specific about how you want to do it, then you can go with intermediate fusion, for example. I'll just go ahead and go with the late fusion because it is the simplest and probably also the most robust for starters in our use case. Cool. So this is how we're going to do late fusion. So we're going to take the video and we're going to encode it, which means we're going to turn it into raw data. And we're going to do that with the ResNet 3D pre-trained model. We're then also going to take the text, so the transfer of the video, and run it through the BERT pre-trained model. This will encode the text. We'll then also take the audio and run it through a audio encoder. And the output for each of these encoders will then be a tensor of batch size, because we take a couple of samples at a time and not just one sample, and then also 128. So the tensor will look like this. So the tensor will be the exact same size as in the output for both the video, text, and audio encoder. That means we now have 3 tensors which we need to combine before we can pass it into our model. So what we do is that we concatenate the data. So we just create a tensor of batch size, and then we just append the data basically. So we can say this one first, this one afterwards, and this one afterwards. So we just get 128 times 3. So that will make a tensor of batch size, comma, and then 3 times 128. We can then run that through a fusion layer, which learns the relation between each one of these modalities. So the video, the text, and the audio. And then from that fusion layer, we can branch out into 2 more layers of neurons. The first layer is the emotion classifier, and the next one is the sentiment classifier. And the reason I have 2 of these is because we want to separate the sentiment classification from the emotion classification, because it is not the same. The emotion classification should choose between 7 different categories, so joy, sadness, for example, whereas the sentiment classification should choose between 3 different categories, so negative, neutral, or positive. So these will be separate predictions, and this is what we call task-specific heads, because each of these predicting layers will have a separate task to do. So that is how we're going to build up our model. So let's take a look at what we can do now to get started with coding. So going up here to the plan, first of all, we can download the dataset, which you have probably done by now. Otherwise, you can pick up the video again when it is downloaded. Then the first thing we're going to do is just use something called the Dataset class. So we'll be working with a library called PyTorch. PyTorch, like this. And this is one of the most popular machine learning libraries used in the world. And then inside this PyTorch library, we have something called a dataset class. So a dataset class is a way for us to organize and manage our data. So the MELT dataset, which we have just downloaded, we can load it into the dataset class. And it then allows us to efficiently load, pre-process, and also serve this data in batches. So that really helps when with training the model and also inference later on. After creating this dataset class we can use for training the model, we can then create the different encoders. So down here, we'll need an encoder for the frames or the video. We'll need an encoder for the text and also an encoder for the video, for the audio track. Then we can create the fusion layers, which will learn the relationship between the different modalities, so the text, audio, and video. And then we can train the model based on the architecture which we have built. Next up, we can evaluate the model, and then we can deploy the model whenever we feel like it is good enough. So let's go ahead and get started with creating the dataset class and then building out the model. Now that the dataset has been downloaded, we can go ahead and open up a new terminal again. I just closed the terminal, but my dataset is downloaded right here. So what we can do is just, I'm on Mac, so I want to extract this tar.gz file. So I'll say tar-xzvf like this. Then I can say meld.raw.tar.gz like so. And this should extract out the dataset to my local machine like this. So if I just press enter, we can just see what happens. So now it should be extracted. So I see that it contains 2 more files, so I'll just go ahead and do that for those as well. So I'll say meld.raw like so. And then I'll just run the same command. So I'll say def.tar.gz. like this. And then I would like to say test as well, test.tar.gz, like so. And then lastly, I see we have this train.tar.gz. So I'll say train.tar.gz. And this one should take a while because it contains all of our training data. So it might just take a while. After this, we'll just set up the folder structure. So I'll say new folder under this melt.raw. This one will be called dev. So I'll just say new folder and say dev. Then another one, I'll call it train. Another one, I'll call it test, like so. And now I can take this dev send emo and also this dev splits complete and drag it into the dev folder, say move. I can also just take the test sent and output repeated right here. And I'll just drag that into the test, say move. And then I would like to take the train sends emo along with the train splits, like this, and move it into the train folder. And then this dev.tar.gz along with these two, I'll just take those and delete those. And now we have the dev. So for the dev, we have the labeling of all the data along with all the video clips. And for test, we also have all these video clips along with the labeling of all the data. And then for train, we also have all these video clips along with the labeling for all that data. So that seems to work fine now. I'll just take this folder and call it Dataset. And then I won't really need this melt.raw.tar.gz, but I'll just leave it as it is in case I accidentally delete this dataset folder and need to extract it again. So now I'll just go ahead and create a new folder called training. And then inside this folder, inside training, I would like to create a new file called melt.dataset.py, like so. And then also, before we implement this, I can go into the dataset. I'll just take dev for now and just open up the following Excel file or CSV file. And then if I press this, we can see that we see a snippet of an episode from Friends. So it is about 2 seconds long. And then this folder contains all the different videos from Friends that they have labeled. And then we can also, under this CSV file, see all the labels. So up here we have the headings, so what this data actually is. So this is the number, so 1, 2, 3, 4. And then we have the utterance, so that is the transcription basically. Then we also have the speaker, which is Phoebe, and then the emotion and sentiment, so sadness and negative. Then we have dialogue ID, utterance ID, season, episode, start time and end time, like so. And then we also have the video clips for that specific one, which is probably this one, yeah. So that is how the data is structured for us. We have the video clip, and then we also have the labels for that video clip, so sadness and negative. So now we just need to go ahead and create the data loader, and then we can use that to work with the data. So inside this melt data set, we can go ahead and implement that now. Now, before moving on with the implementation, I would like to quickly go through how this works with the diagram, just to make sure that you are 100% on the same page as me with why we do implement this class. So when training the model, the program is going to pick out samples from the training data, but each sample contains some information from both the CSV data, so the CSV data file from the training data, and also the video folder containing all these MP4 videos. And as you might see, these are two completely different types of data. So we will going to be needing both the frames from the video, along with also the audio from the video, along with also the utterance from the video, so the transcription, and then also the emotion and sentiment labels. And for each sample we're going to process, we'll need to pick out all of these different elements and then train the model with each of those samples. So what we want to be able to achieve is to have some kind of variable or class called training data, for example, training data. And then this class should contain all the different samples. And when we grab one specific sample, so sample number 0, for example, then we get out the CSV data, so the utterance for that sample, along with the video for that sample, and along with the audio for that sample, and also the emotion and sentiment label. So instead of manually having to do these things all the time inside the code, we would like to just contain this into a class called the dataset class. So this way we can automatically just get these out. So if I say training data 1, then it'll automatically pull the sample out of the training set, with the utterance, the video, the audio, etc., like I explained before. So this is how we can just very simply pull out the different samples from the training data. So how we're going to do this is in the following way. Down here in the dataset class, I'll just explain how it is supposed to work. So the purpose is to be able to load the pre-processed samples one by one whenever we train the model. So the input to this class whenever you instantiate it is going to be the file path to the CSV file, along with the file path to the folder containing all these videos, and then all the samples can easily be loaded from that class. So when the class is first instantiated, we're going to load the CSV file into a property on this class, so an instance variable. So this will contain all the different rows. So this is an utterance, for example, oh my god, he lost it, along with the person who said it, along with the emotion, the emotion and then the sentiment, and then also where it's from in the video. So all of this is stored inside the CSV file. So we're just going to go ahead and load in the entire CSV file and store this in the dataset class. We're also just going to create the mappings. So if it says negative, we're going to map that to a number 0. If it says neutral, we're going to map that to a number 1, and do this for all the different labels. And this is where we can pass numbers into the model whenever we train it and run inference on it, instead of passing these labels directly into it. And I want to be able to expose two methods down here. I would like to override a method called length. So that's whenever you run this normal length function in Python. So if I do say length and then pass in the myDataset, which is just an instance of this dataset class, I would like it to count how many rows are in the CSV file path and then return that amount of rows as the length. And next up, I would like to be able to take care of the example I gave you just before, where you pull out a single element from this dataset. And we can do that by overriding this method called getItem. So whenever we pass in a number like this is just going to be an ID or an indexing number. I would like to use this specific number to find the row up here and then process the audio and the video and also the text tokenization for that specific row and return that as that specific sample. So if I pass in 0 right here, we're going to go ahead and find row number 0 up in the CSV file. That is going to say, oh my god, he lost it, along with having these two emotions and sentiments. And then down here, we can see exactly what it is going to do with that row. So we're going to do a couple of things. So the sample will contain text, video, and audio, and the label for that sample will then be the sentiment and also the emotion. So to process the text, we're just going to load the text directly from the row. So we already found row number 0 right here, and we can get the text from it as so. And then what we want to do to be able to work with the text is tokenize it. So we're going to tokenize it with a bird, which is a tokenizer that is accepted by the pre-trained model that we're going to use. So this will take care of handling the text. Next up, we're going to handle or process the video feature. So first of all, we're going to take the video up here. It has an utterance ID and also a dialog ID, and we can use those to find the exact video inside this video file path right here. So this video file name is going to contain the utterance ID and also the dialog ID, so we can then identify the video from that. Next up, now that we have the video, we can then extract the frames from the video. So a video is just a series of images, so we just extract all those all those images from the video. And next up, we can then take the RGB values for each channel in those images and normalize those. So we take the ranges 0 to 255 and normalize those down to between 0 and 1. And the reason we do that is because standard activation functions just work better with normalized values because it's more consistent and also more stable. So now that we have the normalized frames for the entire video, we're going to create one tensor, so one data format containing all the different frames, and then we're done with processing the video. Next up, we would like to process the audio feature. So from this video, which we have already found, we can then take the MP4 file and convert that into a WAV file. So this is just an audio file with no video inside of it. We can then extract that audio from that video by doing this. And then we can have the waveform like we see right here. So by default, the audio in a video is just expressed with a waveform graph. So you have some signal strength right here, and then you have the time. But what we want to do is create a MEL spectrogram, because a convolutional neural network, which we're going to use for processing the audio, works better with MEL spectrograms than it does with just this normal waveform. And this is going to say MEL spectrogram and not MEL spectrogram. It's also more compact than the normal waveform, so this MEL spectrogram, and thereby also more efficient when running the neural network. And now we have the audio done. So now we can just finish up with telling you about how we are going to process the labels. So for the labels, we can see up here on row number 1 that we have these two emotions, sentiments and emotion. We have sadness and negative. And from these, we can use these mappings we have created. So we can take negative, for example, and associate 0 with that. And we can then take sadness and associate 5 with that. So now we have also mapped the labels right here to some numbers we can use for the model. So now we have processed both the features and also the labels, and we can then create a dictionary containing all of that info. And this will be a dictionary containing all the info for the specific sample number 1, and then just return that whenever we call this getItem method. So what we'll end up with is something like this, just a dictionary with the text, the audio features, video frames, the labels, so emotion, and then sentiment. So now that you know the purpose for creating this dataset class, which is being able to load one sample at a time in a pre-processed way, we can now go ahead and implement the class. We can start off by installing some of the packages we might need before we just implement this, because we will need some of the libraries before we can create the dataset. So first of all, we'll need something called Torch. This is the PyTorch library. So I'll say pip install PyTorch, or just Torch actually, not PyTorch, and just wait for that to install. And then right after doing that, we can install something called Torch Audio. This is what we'll need to work with audio with Torch. We can also just install Torch Vision. We might need that. And then also we can install transformers, like so. There's also another important library called pandas, which we'll most likely also need to read the CSV file. So I can say pandas, like so. Now in here I'm going to create a class called meld dataset, like so. And we're going to inherit from a abstract class called Dataset, and that comes from PyTorch. So I'll say def init and just create a pretty simple constructor for now, saying just print hello and nothing else. And then to get this dataset abstract class, I'll say from torch.utils.data. We can import the dataset. And then what we can then do is just create a simple way of testing it out down here. So I'll say if name equals main. So if we just run this Python file as it is, that will execute the following code right here. Then we can say meld equals meld dataset, like so. And because we aren't passing anything into the constructor, we should be able to just do this. Now I'll go ahead and press this button and say run and debug, say Python debugger, and then Python file. And we can just go ahead and see what actually happens. So this should instantiate a new class, and then just close down the program because that is the last thing that happens. And then in the constructor, when it's instantiated, it says hello. Great. Now, because the dataset contains a video directory and also a directory containing the CSV file, I would like to load both of these into the dataset. So to do that, whenever I construct a new dataset and whenever I instantiate one, I would like to pass in the CSV path and then also the video directory, like so. And then down here, we can go ahead and just pass these into the constructor like this. So if we just use the development dataset, I can say the same folder as we are, or actually not, the one right outside of our folder, and then dataset, like this, development. Then I can say development, just see, I can just copy this entire name, like so. That should be the CSV folder path. Then I can go ahead and say dataset, development, and then the video path should be def splits complete, like so. So that should point to the video path right here, whereas this one should just point to the CSV file right there. So what this does is that it takes paths relative to where it already is. So this is being run from inside the training folder. So these two dots and this / should go outside this folder to the root, and then go outside and then inside this dataset folder, like this, inside the def folder, and then take the following CSV file and also the path to the videos. Great. We'll now load the CSV file with pandas. So up here I'll say import pandas as PD. And then down here in the constructor, I can say after this print hello, I can just go ahead and say self.data equals, so I'll just set a property on the instance whenever I create an instance of this class. Then I can go ahead and say pd.readCSV and then pass in the CSV path. And now if this works properly, we should be able to print out self.data.head like so, or we can even just print out the length of self.data like this. So I'll just save this and then just run the code again. So you can either run the code with debugging here, we can set debugging breakpoints, or you can go ahead and say, and navigate into this folder, so cd training, and then you can say python meld dataset.py like this, and that should also run the code. So let's go ahead and see if it actually loads the code, loads the CSV file like it should. So yeah, it does definitely load it, because we see that it says 1109 records found inside the CSV dataset like this, and that seems about right, 1100 something. Perfect. So now we know that it can find the paths correctly, so that is good to know. Next up, I would like to just store this in an instance variable as well. So I'll say self.video directory equals video directory like so. Then I would like to tokenize the text. So I can go ahead and say import, or actually from transformers import auto tokenizer like that. And then what I can do is say self.tokenizer. So this is what we'll be able to do to tokenize the text. So this will not tokenize the text in itself. It will just allow us to use this bird tokenizer, which we talked about in Excalidraw whenever I explained the architecture. We can also just create the maps the model will use to map between the numbers, and then also the labels that we are able to read as humans, so for emotion and sentiments. So I can say self.emotion map, like so, and then this will be equal to the following. So I'll say anger, that will be number 0, then going to the dataset, and then we also have this readme file, then we can search for anger, like this. It's also up here somewhere, like that. Then we can just copy the following ones, just so I can see exactly what they are, like that. So anger will be 0, and then I can say disgust, and then we also have fear, joy, neutral, sadness, and surprise. So that is going to be the emotion map. And then the sentiment map is a little bit easier, because that is just negative, positive, and neutral. So self.sentiment map like this equals a map with a negative, 0, neutral 1, and positive 2 like that. And that should be it for the constructor. So I can just go ahead and run this to see if it generates any errors. It probably shouldn't, because it is super simple. But what we can also just implement in the meanwhile is a override this method. So whenever you run the following, let me just go ahead. Whenever you run the following code, so length of something, and then you put in a class, you can then override how this length method works. So by overriding this, so by def and then putting on these 2 underlines right here, you can then override how this length method works. So what I want to do is just say, whenever we call length, I'll just return the length of self.data, which we set up here from the CSV file from pandas. So that is how I want the length method to work. I also want to override the default get item. So def gets item like this. So I'll pass in self and also an ID of the item I would like to retrieve. And then I can go ahead and just say print hello for now, like this. So normally in Python, if you have an array, so hello equals apple, for example, and banana, then if you go ahead and say print hello 0, then you just get apple. If you say print hello 1, then you get banana out. But what if you have multiple data sources? So I want both the text from the transcript right here, for example, I want this utterance. I also want the frames from the video, and I also want the audio from the video. That is not something you can just do just by going ahead and doing that. I need to override and custom implement how I want that to be done. So that is why I override this get item, because if I then do the dataset like this, and then say get item like so, then I can get out the ID of the specific data sample that I would like to, and all the processing will then be done for me. And the processing I would like to be done for me is to first of all tokenize the text, and then also load the video frames from the video, so the specific images, and then lastly the last modality is audio. So I would like to load the audio as a data format that we can use when training the model and also when running inference on it. So first up, inside def, we need to figure out the structure of how these are named. So it says dia 0 and then utt 0. So that is probably, if I go up, that is probably the dialog ID and then the utterance ID. So I can go ahead inside this get item, and then I can define a variable storing where the specific video file name is at. So I can say file name equals, then I'll just put in a multi-line string like so. Then I would like to retrieve a single row from the CSV file. So a single row would be something like this, for example, along with this. And this will contain the dialog ID as well as the utterance ID. So I can go ahead right over that and just say row equals self.data. And because we have the CSV file loaded into pandas, we can say data.ilog. This will locate by index. So it'll fetch a single row from the CSV file based on an integer index like this. Now we can go up ahead and say dia and then pass in the row, and then we want to pass in this dialog ID right here, this header, and then also this header. So let me just go and copy that dialog ID, and then I can just copy this, and then we will say utt for utterance, and then we'll pass in the utterance ID like so. And then I can go ahead and say .mp4. So this should match the file path that we might encounter. So right here we have dia, that is this one, and then we fetch the rows. So if you get this row, for example, then we would like to find that row's specific video. So each row has a specific video. So this one has 0 and 0, and that points to 0 and 0 right here. So that is the video we would like to fetch for the first row, for example. So that is why we build it up the following way, the video file name. So we have the dia, that must be the dialog, and then the utterance right here. We pass in the numbers and then .mp4 because it is an mp4 file right there. Great. Now we can define the full path to the actual video file name. So I can go ahead and say path equals, and then os.path. We'll need to import os though, so I'll say import os. So os.path.join, which will join together two file paths. So this will be self.video directory and also video file name, which is the file itself. So the video directory just specifies the following directory, but we also want to append this mp4 file to it. Good. Then we just want to make sure that it actually exists if you run a command like this. So I'll go ahead and say video path equals, and I can then say os.path.exists, pass in the path, and then I can say if video path equals false, because this is a boolean. We can then just throw an error. We'll just say raise file not found error like this, and then say no video found for file name, and then I'll just go ahead and put in path like this. Like this, great. And what does it say right here? So I can then just remove this and we should be good. So if we actually pass this if statement, I can just go ahead and say file found, and then down here I can go ahead and try and run this code, because right now we try and fetch the first row inside this. So we should try and fetch the following row right here from the def dataset. So let me just go ahead and run the file and just see what happens. Because if the file is not found, we should see an error. Otherwise, we should see file found. So we do get an error. So if we just try and print it out correctly, so right now we are missing the following to insert this variable. So let me just try and run it again. So now we should actually be able to see the path. So now we see that the path is broken right here in the middle. So that's kind of weird because I think it's the formatter that breaks it. So if I just go ahead and remove the following and then run it, now it says file found. I do want to make it a multi-line string though, because it is going to give a problem whenever I run it on the server for training. So let me just see if I can get it to work. So let me just go back again. Sometimes you have to fiddle a little bit with this. So if I add them now, great. So if I go ahead and do this and then press save, then the line will break. If I then add the 2 extra marks after that, then it actually works as it should. It's because the formatter breaks the line in a weird way, so that is just an unfortunate situation, but it doesn't really matter at all. So now it works and we see file found, and that is perfect. Next up, we can go ahead and tokenize the text. So the utterance right here, because that is a format that the that the neural network can understand. So I'll go ahead and say text inputs like so equals self.tokenizer, because we set the tokenizer up here in the constructor. And then what we can do is just pass in the row, and we'll take utterance from the CSV file, which is the text, and we then want to say padding, max length, truncation to true, and then max length to 128. And then we would like to return tensors as PyTorch tensors, like this. So let me just explain what all of this does. So neural networks needs fixed sizes. So the model expects consistent input dimensions. So this means that we would like the input for it to be 128, regardless of what the utterance actually is. So if it is too short, we will pad it. So that is some special characters that will be inserted up until it is 128 long. If it is more than 128 tokens long, it will be truncated down to 128. Since we're working with PyTorch, we would like to return PyTorch tensors like that. And then what I want to do actually is try and say print text inputs, and then go ahead and just run this code. Then we can see what it actually prints out. So it looks like it has padded all the way from here to here. So this is not something we understand as human, but it's something that this tokenizer has made that the neural network is able to understand. So that is great, because that means we can actually move on to the next part. So next up, I would like to load the video frames from the video. So I would like to say video frames equals self and then dot load video frames. And I would like to just implement this method with you. So this will be a little bit more complex than just the tokenizer here. So we have the video path with the video. And then to extract the frames, we'll use a library called OpenCV-Python. So we'll say pip install OpenCV-Python like this. Great. And now I can just go up. I'll just do it right on the constructor. Create a new method called def load video frames, exactly like that actually. I would like to load in the video as cv2.video capture. So up here I would say import cv2, and then I can say capture equals cv2.video capture. Pass in the video path, and then what I can do is just put it in a try catch. So I'll say try, because when loading a video, if the video is corrupted, for example, then I would like to be able to handle that. So I'll just say print for now, and then try except, exception as E, and then I'll say raise value error. I'll pass in video error like so, and then say string error. So if an error do occur, I would like to print that error. Great. And then this obviously needs to be a normal raise like that. And then I can say finally, and then cap.release. So when this code has been run, we then release the resources from the video capture. Good. So what I then want to do is say if, and this should obviously be inside the try catch. So if not cap.isOpened, so we open it up here, and it should do that automatically, but we just want to make sure. Then we say raise value error cannot open video, so video not found, cannot open video, something like that. And then what I can do is just say try and read first frame to validate video, like this. It's just to make sure that people understand what I'm doing. So read and frame equals cap.read, like so. So this one just returns true if the video is actually successfully read, and this one will just return the frame itself, so the video frame. Good. And then if none of these are true, so if the video is not found, then I'll say if not read or frame is none, like so. Then I can say raise value error, and then again video not found at that video path. So now we should be able to make sure that the video is actually loaded and it does actually exist. So now we're going to loop through all the different frames by reading them like we did right here, and then we can just load them out. So I'll say while length of frames, and that is a variable I'll create up here. So I'll say frames, where we can store the frames in, is less than 30. So I maximally want to fetch out 30 frames from the video and not more than that. So 30 frames is about 1 second at a standard frame rate. So if the video is longer than 1 second, it will probably be truncated, and that information of the video will then be lost and not run into the neural network. This means that we might miss important frames from the video, so it's not very ideal for long videos because we are losing this information, but at the same time it's also more memory efficient because we don't have to process all these frames through the neural network every time we train it or run inference, so it means we use less memory, and we also do faster processing. It also means that we have a more consistent input size for the model, and it should also be enough to capture some temporal information about the context of what the model is trying to infer. So we'll just go ahead with 30 frames for now, and just if it's not enough, we can always up it, but it's a good starting point. We also only want to read the frames if the capture is still open, so if cap.isOpened still returns true. If that is the case, we then want to check if the frame has been read or not, along with getting the frame. And we can do this by saying cap.read, like this. So this cap.read method automatically keeps track of which frame we're at. So if you just keep calling this, it's just going to keep taking the next frame, and the next frame. So remember how we said try and read the first frame to validate the video? So we just validate the video, but it actually means that we skip the first frame. So I want to reset this index before starting the actual reading of the frames. And to do this, I'll go ahead and say reset index to not skip first frame, like this. Then I can say cap.set, and then I can say cv2.cap prop pos frames at 0. This will reset that index, so we do not skip the first frame. Now I can go ahead and say if not read. Then I am just going to break the loop because the frame was not read. Maybe it was the last frame last time. Then I can say frame equals cv2.resize. So what I want to do is just always use 224 by 224 for the width and the height of the frames that I put into the neural network. This keeps it consistent because we always need to put in consistent values into the neural network, so the same width and the height. And it also makes sure that we can do the processing a bit faster, because putting in massive images will take a lot longer and use a lot more memory. So this is a fine starting point for now. So regardless of what size it is, we'll just resize it down to this size. This will make it more pixelated and make it lose some information. But like the case up here, there's trade-offs, so it should be a fine starting point to just resize it down to that point. Now I can say frame equals frame divided by 255.0, and then frames.append to just append the frame we just extracted from the video to the list of frames up here. And the reason we're dividing by 255 right here is to normalize each of the RGB channels. So a frame will have an RG and B channel probably, and this will be between 0 and 255. So it might look something like this, 255, and then 128, and then 0, for example. And then because we normalize it, that means that they will be constrained to between 0 and 1, because this is the maximum value, and that is what we divide with. So this will be 1, this will be 0.5, and this will still be 0. So this is what the normalized values will look like, whereas this is what it will actually be before it is normalized. So we just normalize the values to make it easier for the LLM to work with. And as far as I know, this is standard practice in the computer vision. Good, so down here after the finally, what I would like to do is just say if the length of the frames is 0, then I'll just raise a value error and say no frames could be extracted. Like so, just so we know. And then otherwise, if a video has less than 30 frames, I would like to pad it, so put in some dummy frames. And then if the video has more than 30 frames, I would like to truncate that such that the video we run into the neural network will always have 30 frames no matter what. The frames I would like to to pad with if it has less than 30 frames are just black frames, so just the RGB values of 0 basically. So I'll just go ahead and say pad or truncate frames, and then if length of frames, if the length of frames is less than 30, then I would like to just pad it with empty frames. So I'll say frames plus equals, then I can go ahead and say MP, so numpy, so we just need to import that as well. So let me just see if I installed that. I'll say import numpy as np, and we did install that, so that is perfect. And then down to here, I would like to use the first frame as a template frame, so I can say zeros like, and then frames 0, like so. So I'll take the first frame, so we already have some frames, we only need to pad with a couple of frames perhaps. So I'll take the first frame, and that frame will have a specific shape, just like all the other frames, and that shape is what I'm interested in. So I'll take that shape from the first frame and then create another object exactly like that shape and fill it with all zeros. So now I have a dummy frame that is filled with only zeros in the exact shape I want. Now I just need to find out how many we need of those. So I'll go ahead and say max frames, which is 30, minus the length of frames. So if we have 20 frames, we need to pad with 10 frames because the max frames is 30, for example. So this way we can create one dummy template, and then we can multiply it by the amount of dummy templates we actually need. And then we just add that to the array of frames. We can also say, okay, if we need to truncate instead, then it is an else statement. So if it is under 30, then we just say add these dummy templates. Otherwise, we truncate it. So we say frames and then equals frames. Then I can go ahead and truncate it like so to max frames, which is 30 like that. And then lastly, because we have this frame, we now just need to return it because we have this method. So I'll just go ahead and say return torch.float tensor. And we just need to import torch quickly. So import torch like that. So this will just create a tensor that can store floats, and then and floats are just decimal numbers. So I can say in numpy.array, then I can pass in the frames, and then I'm just going to go ahead and say, let me just go ahead and go outside this, say permute 0, 3, 1, and 2. And let me just explain why I do all of these things. So first of all, this frames array is just an array of frames, but we would like a single data structure to encompass all of them. So what I want to do is just turn them into a single numpy array that contains all of the frames in one array. So this will be done with numpy.array, and then I will turn those into a float tensor. So this is just the torch tensor model like we talked about in Excalidraw earlier, and these are floats, so it can be decimals. And then before the permute, let me just go ahead and do this as well. So before the permute, what the structure is the following. We have the frames, then we have the height, the width, and the channels in the tensor, like so. And then after the permute, we have the frames, we have the channels, the height, and then the width. So it just reorders the tensor. So it takes what was index 0, so frames, and put it at index 0 again, because we have it as the first argument. Then we take what was index 3, so channels, and put it as index 2, because we set it as argument number 2. We also take what was index 1, so height, and set it as index 2 now, because it is the third argument. Then we take what was this one, so that was width, and set it as the last index now, because that is the last argument. So that is what Torch do. That is what a permute do. And most importantly, the reason we're actually doing this is because the video encoder ResNet, which we talked about in Excalidraw as well, which we're going to use, expects the following order in the tensor: frames, channels, height, and width, and not frames, height, width, and channels. If we just pass this in, it wouldn't really work. We just need to reorder the tensor like this, and then it'll work with the encoder we are intending to use. So that is the entire reason for using this permute right here. Now, if we then go down to where we called this method, we should now be able to just print out the video frames. So let me just go ahead and do that and just see how it looks. So I'll just go and say Python melt dataset like this, and just wait for it to finish. It'll take a little while because now it has to load all the video frames from the video. So that's a little bit of a heavier operation compared to just tokenizing the text. Now, let me just see what it is actually complaining about. So it says it expects an integer and not a boolean. So let me just go ahead and search for video capture like this. And now we can see that we passed down this video path. So let's see what video path actually is, since it's apparently a boolean. So video path is actually a boolean because this exists returns a boolean. So let me just go ahead and rename this to exists, so it's a little bit easier for us to see what is what, and then pass down the actual path like we are supposed to. And then we can try and run it again, and then we should definitely not get the same error. So now we say, what does it say? Type error, this is not supported while length is less than 30. So let me just see. So it should be length of frame, like this, is less than 30, and frames up here. Great, so we'll only take the first 30 frames. And now let me just go ahead and run it again. Cool. So now we see some printouts. So these are just all the different frames that are being printed out. So this is how the frames are being represented and what we input into the neural network. This is totally not understandable for us, but apparently the neural network understands this because it is all numbers. So that is perfect. Great. So you see how it prints video frames right here, like it's supposed to. And then because we don't return anything right now in this get item, we just print out none, because this will return none when you pull out an element like this without returning anything in the overridden get item. So we just need to do a couple of more things, and then we can return what we are supposed to do. We are, for example, going to return the audio features, which will extract with the audio encoder. For the audio encoder. So this will just be the raw data from the audio, which will then be able to be run into the audio encoder later on in the model. So let's just go ahead and implement that. So right under this load video frames, I'm just going to go ahead and create another method. This will be called extract audio features. We'll just pass in the video path like this. And then I would like to first off get the audio path. So what I'm going to do is I'm going to take the MP4 file, then run an FFMPEG command, which is a library I can use to extract audio from a video. This will create an audio file on my system for each time I run this. Then I can load that audio into the memory and then delete that file again. So that is the way that I'm going to handle getting the audio out of the video. So the audio path will just be the same as the video path, just with a WAV extension instead of the MP4, because it will be placed the exact same place. So now we have both the video path and the audio path, and I can go ahead and say try, and then accept. I might want to just say something like print, and then I can go ahead and say accept exception as E. So here is how we're going to run the FFMPEG command to extract the audio from the video. So I'll say sub process, and this we need to import. So I can say import sub process like this, hop down to where we were, which is right there, sub process.run. So what this does is essentially just run a command in the terminal for you. So you can just run a terminal command through the code basically. And that is exactly what we're trying to do. So I want to pass in the different parameters. So this is going to be FFmpeg. And then the next flag is going to be -i and then video path like this. This will pass in the flag with the video path, so where we want to get the video from. Then I would like to put in VN as well, like this. So this means no video output, audio only. Then I can put in NODEC, which is just something I used back when I wrote some of this code. And then I can put in AR. This sets the sample rate of the audio, so I'll just set this to 16,000 because that is what I want to use later on with Torch. Then I would like to put an AC to 1. This will set it to only one channel, so mono audio. You can also have headphones where you have audio in both ears, for example. This will be mono audio though. So lastly, I can put in the audio path like this. This is where we want to extract the audio to. And then I can just put in a couple of more things. So right after this one, I can put in check equals true. So what this will do is it'll raise a error if the command fails. Then I can also put in st standard out, and I'll say subprocess.def null to hide all errors. All outputs, and then also def null here to hide all errors that might occur whenever we run this command with FFmpeg like this. And this should then create an audio file for us in our system. So I can just go ahead and check that out actually. So right now we do not have any audio files right here. But if I go ahead and just run this, so I'm just going to go to the get item, comment out this one, and just call it the following instead. And then we should be able to actually create this audio file. So let me just try and run this and see what happens. So it creates an audio file just like it should. So that is great. I can just go ahead and close this folder again. And then move on. So now that we have the audio file, I would like to load it in with the Torch audio library. So I'll say import Torch audio. So I'd like to load it into memory instead of just being a file on my computer. So I'll say torch audio.load to load a file. I'll pass in the audio path, and what I'll get out from that is the waveform along with the sample rate like this. And then one very important note with FFmpeg is that you need to install FFmpeg on your local system as well. This is not a library you just install via Python. This is a command a library you need to install to your local system, such that you're able to say FFmpeg down in the terminal if you wanted to. So let me just show you how you can go ahead and do that. So on Mac, if you're using Homebrew, you can say brew install FFmpeg. That is one way of doing it. Additionally, you can also go to Google, search for FFmpeg, install. You should be able to see some different packages you can install here for both Linux, Windows, and Mac. I think I just installed it with Homebrew, to be honest. But you can also just see if you can find any guide for your specific system or operating system. It shouldn't be very hard to install. You should basically just be able to go in here and just install one of these, depending on your system, and just have it work out of the box after that. So I'm just going to go ahead. So we load in the audio path, so the audio file, then we get a waveform and a sample rate out. So I just want to make sure that the sample rate is actually 16,000. And the sample rate is the amount of audio samples captured per second. So 16,000 just means 16,000 samples per second. And it's pretty standard for speech recognition with neural networks. So it's a very common number to encounter whenever you're working with audio. So if it is not 16,000, then I'm going to go ahead and resample it. So I'll say resampler equals torch audio dot transforms dot resample like this. And then I'll just say sample rate 16,000. That way it'll always be turned into 16,000 sample rate. Then I can say waveform equals resampler waveform, and that way set the waveform to what it was before. Oh, sorry, not what it was before, the new resampled waveform. Great. So after this little check, I'm going to go ahead and create something called a MEL spectrogram. This is just a 2D representation of audio with time on the x-axis and frequency on the y-axis. And it's very standard to use in speech recognition with neural networks. So first we define how the MEL spectrogram should look. So we'll say MEL spectrogram. And then we can pass in the sample rate, which is 16,000, like this. And the other configuration values will be n-mels, which will be 64. I'll then also fill in n-FFT, and this I'll set to 1024, like so. And then I'll put in hop length, which I'll set to 512. Let me just go ahead and close this up. And then we can use these configuration values to generate the actual MEL spectrogram from this waveform. So I'll go ahead and say MEL spec equals MEL spectrogram, and then just pass in the waveform, which we got from loading the audio file up here. Great. Then under that, we can go ahead and normalize this MEL spectrogram. So I'll say normalize. Then I can just go ahead and use the following formula: the MEL spectrogram minus the mean of the spectrogram. And then we take that entire term and divide it by the standard deviation of the spectrogram. And then the MEL spectrogram have been normalized. And then of course, neural networks need fixed input sizes. So just like we did for the video frames and also the text tokens, we'll need to either truncate or pad the length to make it fixed. So if I go ahead and say if MEL spec, like so, dot size, and then I take the second index like this, and say it's less than a max length, and I'll just say 300 for now. So this will be the time steps. So if the time steps is less than 300, then we can go ahead and define a value called padding. So I'll say 300 minus MEL spec dot size 2. So if we have less time steps than the required length of 300, then we calculate how many time steps we need to insert to make it 300. Then we can go ahead and insert them by saying MEL spec, like so, equals torch.nn.functional.pad. Then we can put in the MEL spectrogram along with the following values. So we'll say 0 and padding. So we'll fill out how many time steps we do need with zeros and insert them into the MEL spectrogram. And now we have padded the MEL spectrogram. Now I can go ahead and say else. So that is if we are more than 300 time steps, and in that case we'll need to truncate. So I'll say MEL spectrogram equals MEL spec, and then I can go ahead and do the following. So this means we keep all the channels, this means we keep all the frequency bins, and this means we keep up until 300 time steps, but also not more than that. And then I would like to be able to handle two different kinds of exceptions. So right now we just define this basic exception as E, which will just catch all exceptions. But I would like to catch one a little bit more specific first, and that is the one calling FFMPEG right here with subprocess.run. So I can go ahead and say except, and then subprocess dot called process error as E, like so. And I'll just need to call it the right name, and then I can go ahead and say raise value error. And then what I want to put in is audio extraction failed. So I know that it's specifically this FFmpeg command that failed, and then we can just pass in the error like we just did here. And it should be called process error like so. Now under that we'll just keep this except exception as E, and we'll just say audio error just to catch all general exceptions. And then what I would like to do as well is put in a final statement, and that is something that will always be executed regardless. So I will say if O is the path that exists, and then audio path, then we'll just go ahead and remove that audio path. So this audio path, it comes from up here. So what we do is we actually extract the audio from the MP4 and then create a specific file for that. But if we just keep doing that, we'll just have as many audio files as we have video files, and they will also take up space on the device when you're running the program. So we'll just go ahead and just delete that audio file, and that way this folder out here will always stay as it is after running the script, because all of these files being generated will be deleted afterwards. So that is exactly why we put in this statement down here. And now we can test out if this works by going down to this extract audio features, and then we can go ahead and print that. So I'll just go ahead and say audio features equals self.extract audio features, where we pass in the path. And then I'll just go ahead and say print audio features. And now let me just go ahead and run the script. So I'll say run in debug and then press the Python file. And then we'll just wait for this to finish. So right now it says it cannot find this script, CSV file. So I'll just try and run this in a new terminal without being in the debug mode. So right now we should be able to say Python melt dataset.py. And then let's just see if it prints something out. So scrolling up right here, we can go up and see the following. Let me just find the error message. Couldn't find an appropriate backend to handle the URI and the format. So what we need to do is under torch audio, so self.extract audio features, and then torch audio.load is where it leads back to. So this will need an audio backend. So what this means is that it needs some kind of library to use to extract the audio with. So what we'll go ahead and do is just install one with pip. So I'll say pip install and then sound file. This is one of the backends it can use to extract audio. So we'll try and install that and just see if that works. And then let me just go ahead and run this again. So Python melt dataset. And we can then see if it works. So now it works without giving any errors. So that is pretty good. And we also don't have any remnants of WAV files left behind. So that is also great. I can see though that it prints out none twice. So the first time it prints out none is, let me just see, is right here, or that is one of the times it prints out none, and this is the other time it prints out none. So this seems to be none. So let me just go ahead and actually see why it doesn't return anything, and that is because we forgot to put in the return statement. So right after this, padding and truncation, I'll just say return mel spectrogram, like so, press save, and then we can just run it again and see if we get anything meaningful out of this audio extraction. So now we get out a tensor containing all the audio in a mel spectrogram format that has been truncated to being a fixed width or fixed time steps amount of 300 time steps. So it seems to work fine as it is right now. And then we can go ahead and implement the next part. So now we have this extract audio features, and we also have extracting the video frames. And then under that, we can just go ahead and take these emotions and sentiments, so sadness and negative, and map them to numbers like we talked about in the diagram using these maps up here. So I'll go back down and just say map sentiment and emotion labels like this. And then I can say emotion label equals self.emotion map. And then I can pass in the row.emotion, and then I'll just say .to lower in worst case if it's something else than lowercase. And then I can just do the same for the sentiment. So I'll say sentiment label equals, and then I can say sentiment map. And then I'll pass in the sentiment. So what this will do is it'll take the sentiment column from the CSV file, so this one or this one, depending on whether it's emotion or sentiment, convert that to a lowercase word. So if this was sadness like this, for example, then it wouldn't work, but now it would work. So it'll always convert it to a lowercase in case it is not lowercase. And then we'll take that and map it to a number based on the emotion map or sentiment map up here. So if negative would become 0, for example. Great, so now we have the labels as well. Now we can just start creating the return statement containing all of this. So I'll go ahead and create one called text inputs first of all. And then this should contain an object with something called input IDs. The input IDs should contain the text inputs and then input IDs like so. And then I can go ahead and say dot squeeze, like this. So this input IDs is one of the two things that is returned from the self.tokenizer whenever we do tokenize the text. And then we remove single dimensions by using this dot squeeze because it is not needed. And then we can go ahead and do the same for attention mask, which is the other component that is also returned when tokenizing the text. This will also contain one dimension in the tensor of just one, and we'll just remove that tensor as well with dot squeeze. Sorry, not tensor, dimension. And then we would like to also just return the video frames. So right now we return the text, which is used as the text feature in the model. And then we just need to return the video feature, and that is going to be called video frames. Here we'll just return video frames like this. Then we'll also return the audio features. So this will just be audio features. And then because it is a full sample, we'll need to return the labels as well. So we'll have emotion label, and we'll just go ahead and turn that into a torch.tensor and use the emotion label as the parameter for that. And then do the same for the sentiment label. So before doing this, these were just numbers, but now because the neural network expects torch.tensors, so tensors as the inputs, we'll need to turn these single integers into tensors, which we can input into the model. And then hopping all the way up here, I would like to be able to handle both inputting a number input, so an integer, and also inputting a tensor with this index. So these are two different cases which I would like to be able to handle. So I'll say if is instance, and then idx torch tensor. Then we'll need to just take the number out of that tensor. So the IDX will just be the number inside the tensor. And then we'll just go ahead and say row equals this, like we have done before. So we'll just go and create some extra spacing here, like this. So if it is a tensor, we'll just pull the number out of the tensor and then use that ID as the number, which we use to find the row in the CSV file with. Good. And then I would like to just implement some basic error handling as well. So I'll say try, and then take all of this and just indent it by 1. So like this, I press tab once, and then I can go ahead and say except down here, and then say exception SE, and then we can go ahead and say error processing, and then I would like to just include the video path. So I can go ahead and say video path, or just path actually, and then we just put in the error as well, and then we can just return none if that were the case. So we'll just go ahead and do this now, and now we should be ready for testing this out. So going down here, we can just try and print it like we did already, and just run this entire file, and then let's just see what happens then. So scrolling all the way up, we see a couple of things. We do see we have text inputs containing all of the text. So we have input IDs, we also have attention mask, and then we have the video frames containing the tensor with all the different video frames in the video. Going all the way down, next thing we have is the audio features. So that is the audio features. And then we also have the labels for the sample, so the emotion label, and then also the sentiment label. So this will be 5 and 0. So this corresponds to the mapping table all the way up here. So this will probably be sadness, and then 0 for negative. Great. So now we should be able to load samples one by one with this dataset class. And now that we can use the dataset class to load samples one by one, we can also use something called the data loader up from torch.utils.data data loader, and we can use this to load in multiple samples at once. So this is just called batching, and then this is used for training. So we'll just go ahead and create another method down here called def prepare data loaders, like so. And this function should create a dataset for each of these different cases. It should create a dataset for def, test, and also train. So this means we can pull out samples from either of these whenever we need them. So I'll go ahead and say train CSV, then also train video directory. Then I would like to also do the same for def and test. So I'll just make a enter right here, say def, and then def, and then do one more line and just call that test and test, like so. And the last thing I'll just put in is something called a batch size. So the batch size will be 32, which means we'll train the model with 32 samples per per batch, and this means we just train it with 32 samples at a time. So inside this prepare data loaders method, what I'm going to do is go ahead and say train dataset, and then I'll just pass in this one. We can do the same for the def dataset and also for the test dataset. So this means I create an instance of this class up here for each one of these. So now I can pull out a sample for train if I need it, and then when I need to test the dataset, the model, I can then pull out a sample from the test dataset easily. Good. Then I can go ahead and say train loader, like this, equals a data loader. I'll pass in the train dataset, like this, and then under that I'll just put in the batch size, and then I'll set shuffle to true, and then these two I'll just remove for now. And then shuffle to true means it will shuffle the different samples, so it won't just take them sequentially when taking these trained samples. It might take this one first, and then this one, and then this one afterwards. It won't take this one, etc. So this is good for adding some variety when training to prevent overfitting, for example. Good. And then whenever we need to run the def set, we can say def loader equals data loader. We'll pass in the development dataset. We'll just set shuffle to false by not passing it in. And then we'll just put in the batch size as well. And then lastly, we'll just do the same for the test loader. So we'll pass in the test dataset along with the batch size, like this. And then one thing you might have noticed is that we are able to return none right here. So what happens if you have a batch of 32 different samples, but some of these are none because an error processing occurred, and then some of these contain the actual sample like it should? Well, then the neural network training will probably fail somewhere in the code. So what we would like to do is just filter out all of these samples which are none. So how we can do this is by using something called a collate function. So I can say def collate function. We'll put in the batch and then say filter out none samples, like this. So all the samples where none was returned, we'll just filter out those from the batch so no errors will occur. Then I can go ahead and say batch equals list, and then filter, and then I can say none, and then batch, like this. This will then filter out the none values from the batch and create a new list with those values. Now we can just return those. So I'll say torch.utils.data.dataloader.default collate, and then I can say batch. So we'll then have the batch returned again without these none functions anymore. And then we'll just need to pass in this collate function in all of these data loaders. So collate function equals collate function. The same for this data loader down here, and also for the last data loader. And then down here, wait a second, we just need to return these three first, because we need to prepare the data loaders and then return those. So down here we can then just call this instead. So I'll say train loader, def loader, and then also test loader, like so, equals prepare data loaders. And then I'll just pass in all the different paths. So this will be just dot, and then data set. Or what was it before? Let me just see. This was the path. So let me just go ahead and revert that again. So I'll just go ahead and say this is the path to the CSV file. And then this will be the path to all the video clips. This is going to be the following path right here, like this. So dataset, def, and then to the video path. I'll just copy this, and now we need to pass in the def. So now we have train and train now, and then we need def and def. So this one up here actually needs to be train. So I'll say train, and then train here as well. And then we need to call this train splits, like so. And then this is the name of the CSV file for train. Great. And now we just need the test set, which is the last one. This will be output repeated to test splits for the video directory. And this will be the CSV file path, like so. Good. And then because the batch size has a default value 32, we'll just leave that out for now. And then just go ahead and print out some of the values for this, just to verify that it works. So I'll say for batch in train loader, and then I can say print batch, and we'll just break after the first value because it's just for verification purposes right now. So I'll say break like this. Then I can say text input. And up here, we can say text inputs like so. Then we can just also go ahead and say frames.shape. We can just go ahead and do the same for the audio features. We can also just print out the emotion label, like so, and also the sentiment label. So let me just go ahead and try and run this code. So I'll go ahead and say python melt dataset.py and press enter. And now it says that we can't find the following directory. So because we are inside training, this file is inside the training folder, we'll just need to change the directory to inside that folder. So I'll say cd training, and then just run the exact same command, and we can then see if all of these are correct. So it says we are missing test CSV and test video directory. So this is the last two ones. So I do see that we actually made a mistake here. Test and also test. And then we also need some commas right here. So we split these arguments apart like so. And now let me just see if that works. Yeah, something is at least happening right here. Great, and now we do see some printouts, which seems to come from down here. So we do have the input IDs containing the text and also the attention mask. Then we have torch.size, that is the shape of these two features. And then we have the emotion labels and then also the sentiment labels down here. And then before finishing up, if we just scroll up, we see this warning being printed out all the different times that this code is being run. So it says to disable this warning, you can either avoid using tokenizers before the fork is possible, or explicitly set the environment variables tokenizes parallelism to true or false. So I'll just go ahead and set this to false up here. So how I'll do that is just scrolling all the way up, and we have OS imported already. So I'll say os.environment like this, and then I'll just set tokenizes parallelism to false like this. And now if I do try and run the code again, we hopefully do not see this error anymore. So python melt dataset, and then we'll just wait for it to finish. And now we ran the code, and we do not see all the errors anymore, or all the warnings, sorry, but we do see the printouts like we are supposed to. So now we're actually done with this implementation of the melt dataset, and we can move on to the architecture of the model. So earlier on, we were talking about how we are going to process the three different modalities independently. These two will use pre-trained models, and for the audio, we'll train the model ourselves. The output of these three models will then be concatenated into a single tensor, and that tensor be put into a fusion layer. This fusion layer will learn the relation between these three modalities. We'll then take the output of this fusion layer and pass it into two different classifier models. This one will output the emotion, and this one will output the sentiment. And with that in mind, we can now move on to how we'll actually build out each of these and what they will specifically contain. So hopping down, we're going to work with three different types of layers. The first one is called trainable layers. We'll be working with a linear layer, and a linear layer is what we call a fully connected layer. This means that every neuron in this linear layer is connected to every neuron in the previous layer. This is one of the simplest forms of trainable layers, and it is great for tasks such as classification. For a linear layer, you define the amount of input neurons and also the amount of output neurons. This then means that the linear layer can learn the relationship between the input neurons and the output neurons. So if you have a linear layer, for example, that takes a bunch of inputs, so a lot of neurons as inputs, it can boil that down to maybe only 3 emotions and output one of those 3 emotions. The next layer we'll work with is called conv1d, and this is a convolutional layer. It is great for learning patterns in sequential data such as audio over time. A convolutional layer like this processes sequences or time series by applying filters that move across data to find patterns. So a layer like this is good for finding local patterns in sequences, while linear layers are better at detecting global patterns in data. So these layers will contain neurons that we'll be able to train. The next category of layers is called functional layers, and these are layers that do not learn. Here we will start out with the ReLU layer, and the ReLU layer adds nonlinearity. So remember back in the initial explanation where I explained that adding non-linearity makes the network even smarter. So that is what we're doing with the ruler layer. So let's say we have a tensor containing a bunch of numbers like this. What it'll basically do is just take all the negative numbers and make those 0. So it'll be non-linear now. The next layer is called the dropout layer, and this layer prevents overfitting in the network by randomly turning off neurons. This forces the network to not rely on specific features, and that can help prevent overfitting. So let's say you're studying for an exam in the real world. So if you are reading a book and some of the textbook pages are randomly hidden, then it'll force you to learn material from multiple sources and not just from a single page, which you'll have to remember. So this means you won't be able to just remember a single page, and thereby your overall understanding will be even better. So that is kind of the same concept we're applying with the dropout layer. The next layer is called max pool 1D. So what this layer does is that it only keeps the strongest features. If you set this value to 2, which you are able to do with this layer, it'll take only the strongest value for each pair of 2. So let's say we have this tensor of 4 different values. What it'll do is take the 2 first values, compare those, and now 2 is the biggest, so that's the one we'll take. It'll also take 3 and 4 and compare those, and 4 is the biggest, so that's what we'll take. So we'll end up with the following array right here instead of this one. This means that we'll only keep the strongest features and work with them instead of all the features. So if we, for example, have an audio signal with a bunch of different fluctuations, instead of keeping all the data, we'll only keep the strongest peaks because those are probably what matters. So if there is silence in the audio, for example, that's not a very strong peak, so that will be filled out. This will make processing in the neural network more efficient because there is less data to process, and also keep the most important features. The next layer is called adaptive average pool 1D, and what this does is that it averages the last dimension. So regardless of the input size, what it'll do is just take the average of those and output the average as a single number. This is helpful for getting tensors that match when passing data on to other layers in the network. The last types of layers we'll work with are called normalization layers. And training in the neural network will become more stable if data has been normalized. So for this one, for example, we have 1, 2, 3, and 4, and these are normalized to values that are even smaller. So what this layer does right here is just take the values from the last layer and then normalize those to normalized values, which will make training even more stable in the neural network. Now you know which types of layers we're going to work with. I can start by explaining out the architecture. So earlier on, I explained this simple architecture where we have the encoders. So we have a video and also a text encoder using pre-trained models. And then we create this audio encoder ourselves. We then take the output of all of these and concatenate it into a new tensor. We can then run this tensor through a fusion layer that learns the relation between these modalities, and then take the output of that and use that into other layers that will then classify the emotion along with the sentiment. So breaking this down to an even more specific architecture, we can then start to figure out how we're going to implement it in the code. And this I have done down here. So I've taken all the encoders and put them into this big box, and then can start by explaining them one by one. So first of all, the video encoder is going to use this pre-trained model called ResNet 3D 18 layers. That is a small ResNet model that helps us understand the features in videos. That has been trained on tensors with the following format: batch size, channels, frames, height and width. So first of all, if we do not have this format, we'll need to reorder the tensor to have the following format before we pass our input into this pre-trained model. So first of all, we reorder the dimensions. And then we can then pass in the video frames with that as that reordered tensor. And this pre-trained model will then process those features. It will then also output a specific number of features, which I don't really know. And then we can then take that amount of features and pass that in as the amount of input features in this linear layer, which will then be mapped to 128. So this linear layer will then learn the relationship between this amount of features and this amount of features, and then make the size smaller. So this one is probably way bigger than 128. So it will compress the output of this data down to 128 in a tensor. We can then also add another 2 layers, ReLU and dropout. This one will introduce some nonlinearity to make the network even smarter. This one will prevent overfitting by using this dropout. And after that, we'll have an output tensor of size 128, which will be sent over to this other part, which will concatenate the data. So that was the video encoder. The next encoder is going to be the text encoder. So when tokenizing the data, we used the BERT uncased tokenizer, and the output of that tokenizer was input IDs and attention mask. And the same guys behind that tokenizer is also the guys behind this BERT pre-trained model. So it fits right into the input as this model. And this model will then help us understand each word in that text. So the output of this model will then be 768, and it will be stored in something called the pool output, which is a part of the output from the model. And this pool output will then be kind of a summary of the entire sentence we pass into the model. We can then take this entire sentence and then convert it from 768 to 128, just like we did before up here. So this will then be a projection layer. We will project from this number to this number. So we'll basically make the summary smaller. And we'll then take the output of that and pass it all the way into this concatenate data element. Next up, we have the audio. The audio is a little bit more complex because we're making it ourselves, but let me just walk you through it. So first of all, what we'll do is we'll have some audio. This audio will contain lots of detail. So what we'll do is pass it into a couple of layers. These layers will then gradually compress and extract the most important features. And then lastly, it will create a fixed size representation of 128, which we can then pass into this concatenate data element. So breaking that down even more, we have broken this audio understanding into two different parts, a lower order feature detection part and a higher order feature detection part. So this lower order feature detection part will then understand the more lower order features in the data. So that could just be the sound going up and down, for example. We'll then remove some of the weakest data inside the audio signal. So we'll use this max pool 1D, which will only take the strongest signals out of each two. So we'll basically halve the data and keep only the strongest. And the idea is that then after running this reduced data into the same flow, so this convolutional neural network layer, we can then understand more complex patterns inside the data instead of just the ups and downs. So we'll then get the benefit of both the lower level features and also the higher level features such as patterns. And breaking that down even more, this is how we're going to do it. First, we will take the output of the dataset class, which was a MEL spectrogram, and put this in as the input for the convolutional 1D layer. This will have the input size 64 and the output size 64 too. This convolutional layer will be great at detecting patterns in the data, and by setting this kernel size value in the configuration, what we can do is tell it how many elements to look at the same time. So we'll just set it to 3, so it'll look at 3 elements at the time and then detect the patterns between those. The output of this layer we can then run through this batch norm 1D layer to stabilize the output features. We'll then again run this through a ReLU layer to introduce some nonlinearity. We will then reduce the size of that data by half and only keep the strongest signals. Then we'll run through this entire process again with this layer, and this layer just over here. So the only difference is that right here we do not have 64 as the output layer as well, we have 128. And the idea behind this is that if we have even more neurons to work with, the network will more easily be able to understand higher order features and more complex patterns. So the output of this will be a tensor of size 128, which will then normalize. We can then also introduce nonlinearity again. And after doing that, we'll have a tensor that look kind of something like this. We'll have the batch size, like so. We'll then also have 128, which are 128 learned features. We'll then also have some kind of feature length or sequence length, which will probably be time steps, like this. And this time steps can then be different depending on which kind of clips you put in. So longer clips will have more time steps, whereas shorter clips will have less time steps. But this needs to be a fixed length because this linear layer expects a fixed length tensor of 128 and does not expect these time steps. So let's say we have 300 different time steps right here. What this layer will do is take these 300 different time steps and average them down to a single time step. And we can then take this tensor and pass it into the linear layer. We just need to reshape the tensor from this to this with the squeeze command. And this will then preserve the data, but it will then now have the correct tensor dimension, which we can then pass into the linear layer. So that is why we use this adaptive average pool 1D. So regardless of what the inputs are, it will always have a tensor that with only one as the last element like this. We can enable or disable which layers can be trained and which layers cannot be trained. So for example, what we are going to do is disable these two convolutional layers so they can't be trained, but we're going to enable this linear layer to be able to be trained. And the reason is that these layers takes more computation to train and also introduces more nodes into the network. So to keep it pretty simple, we're just going to have this linear layer, which is the one we want to be able to be trained as the only one. So we take this output of 128, pass it into the linear layer, and then we also have an output of 128 for that linear layer. So this layer is only there to add more nodes so it can learn something about the audio. We then pass it into a ReLU layer and then into a dropout layer. And now we then have the different data types, so all the modalities, which we can run into a single tensor, like so. So this tensor will be 3 times the size of one of these, so 128 times 3, and that's why it is 384. And from this concatenated data, we can then take this and run it into a fusion layer, which is right over here. So how the fusion layer works is that we want to have a layer that learns the relationship between the different modalities. So we have text and audio, and we also have the video, but how do these interconnect? And this is what the fusion layer is going to learn. So the input size of this fusion layer should be 384 from this concatenated data tensor, and the output should just be 256. This will then learn the relationship and then pass the result into a batch norm 1D. This layer will then normalize the output of this fusion layer, and then we'll pass it into a ReLU layer and then also a dropout layer like we usually do. The output of this will then be 2 other layers. First of all, we'll have an emotion classifier and then also a sentiment classifier. The reason we make them independent is because this one should only learn about how to classify emotions as best as possible. This one should only learn how to classify sentiments as good as possible. So inside each of these, we have one linear layer that learns the complexity of the features. So it basically just gets to know the features from the fusion layer over here. And then what we can then do with that is pass it through a ReLU layer and a dropout layer like we always do. And then we can introduce a smaller linear layer that just maps to output emotions and output sentiments. So by having 2 linear layers like this, we gradually reduce the complexity by starting with this amount of nodes and going all the way down to 7, which is how many we need for the output. And this is done with the hypothesis that the network is better at learning feature combinations with having these 2 linear layers in comparison to just having one layer that has all of the power. And this architecture is used for both classifiers, both the emotion classifier as well as the sentiment classifier down here. And then what we're going to end up with is 2 different numbers. We're going to have a number specifying the emotion and then also a number specifying the sentiment. We can then pass those into the mapping tables and get the label out. So maybe if we get 1 right here, it'll be neutral. And if we get 3 right here, it's going to be positive, for example. So that is how we are going to be able to use the outputs of the neural network. So this was a walkthrough of how the architecture is going to be created inside the network. And then 3 other things that are very important are the following ones: which optimizer we use, which loss function we use, and which learning rate scheduler we use when working with this architecture. So if you go back to how we explained gradient descent, what we do with an optimizer is basically just gradient descent in a more advanced way. So the most used and also probably the most well-known optimizers and loss functions are the Atom optimizer, as well as the cross entropy loss function. And these are going to work perfectly fine for our case. And generally, you should have a pretty good reason for not picking one of the most well-known optimizers or loss function because you know a lot about neural networks, for example. So maybe you're able to write your own loss function or optimizer, but if you are not, you should probably just use the most well-known and used ones, such as Atom or cross entropy loss. So what the optimizer does is that it optimizes the model parameters using the gradients from the loss function. So the loss function will output a loss that tells us how well the model is doing. And the optimizer will then contain an advanced algorithm that then tweaks the weight values to make the loss as small as possible, thereby improving the model. And it also tweaks the learning rates in the meantime. And the loss function, as you might remember, we talked about mean squared error earlier. And that is good for tasks such as regression, but for using a classification, for building classification neural networks. Another one that's very good is just cross entropy. That is basically the default one when creating classification neural networks. So that is just the one we are going to use. And for the learning rate scheduler, we're going to use one called reduce LR on plateau. So this one will reduce learning rate by 1/10 if the loss does not improve for 2 epochs consecutively. So gradient descent can now be done with smaller steps to get closer to the minimum. So imagine you have a loss graph like this, just like we talked about earlier in the video. So right here, we keep overshooting. So we might overshoot like that, and then we overshoot like this. So we won't really ever find this minimum. So what it then does is it'll reduce the learning rate by 1/10. So now the error will be 1/10 shorter, like so. So now we'll more easily be able to find the minima because of this change. So that is the power of having a learning rate scheduler like this, which can make those changes for us in the learning rate. So now that you have an idea of the architecture with both the optimizer, loss function, learning rate scheduler, along with the architecture itself, we can actually go ahead and go back to the code and start implementing the model in PyTorch. Now, back here in the code, we can create a new file under training called models.py, like so. In here, we can create a class for each encoder, and we'll start out with the text encoder. So I'll say class text encoder. This will inherit from nn.module, and we just need to import nn. So we can say import torch.neural network as neural network. We'll then also need to import something called the BERT model from transformers. So I can say from, like so, transformers, import the BERT model. We can then go ahead inside this and create a constructor. So init, this will then take self and also the pre-trained model. We'll just go ahead and hardcode that. So I'll say super.init, like so. And then we can go ahead and say self.BERT equals BERT model.from pre-trained. And then we'll use the one called BERT base uncased, like so. So what this will do is just take the pre-trained model and load it from your local machine, and if it does not exist on your local machine, it will download it from the internet. So now that we have this model, what we can do is just freeze all the different layers. So I do not want this pre-trained model to be trainable, so I just want to only train my own model. So this model should be used, but we don't want to change the gradients, the weights inside of this model during training. So I'm going to go ahead and say for param, so this is for parameter, in self.BERT.parameters, and then we can loop through all the parameters or all the neurons, and then we can say requires grad equals false. And what this does is that it makes this entire model not trainable, so we'll only use it but not train it. And that is exactly what we want. Going down to the next line, we can just create the projection layer. So I'll say self.projection equals neural network.linear, and we'll then say 7, 6, 8, and 128. So this is what this model outputs, the self.BERT, and then we want to project this value down to 128, which is what we want to concatenate with the output from the audio and the audio and the video encoder as well. So inside a module like this, you define both the architecture of the model, so that is self.BERT and also self.projection, where we define that we are going to use this pre-trained model, as well as this linear projection layer. But we also define what happens during inference. So hopping down here, we can say def forward, and forward is the method that is being called whenever we want to run inference. So when we are training the model, this forward method will be run all the time because we first run forward and then we do back propagation afterwards. But when doing inference, we actually just run the same method, just without doing the back propagation part. So remember how in this forward method, when using this text encoder, we would like the input to be the input IDs. So input IDs like this, and then also the attention mask. And both of these, let me just remove this again. Both of these come from the melt dataset. So when we go up to the return, we have the input IDs and we have the attention mask. And these come from the tokenizer right here. And this is the BERT tokenizer. So see how we import this tokenizer from transformers as well. And then we say BERT base uncased as the tokenizer. So that is why we want these two as the input for the forward method. Then we can say extract BERT embeddings. So that is what the text has been encoded into. So we can then say outputs equals self.BERT. Then we pass in the input IDs, like so, and the attention mask. Let me just go ahead and save that and hop down to the next line. We can then say use CLS token representation, like this. And then we can say pooled output equals outputs dot pooler output, like so. So BERT can train this CLS token to capture the meaning of an entire sentence. So this CLS token, which will then be the pooled output or pooler output, like so. will then act as a summary of the full text, so it's pretty useful for classification tasks. So now that we have the summary of the entire task after running it through the BERT model, we can then also just run the output of that through the projection layer. So I'll say return self.projection, and then I'll run the Polar output through it. So that's basically how we build up an encoder. We define what we want to be able to use, so the BERT model, the pre-trained model, as well as the linear layer. And then down here in the forward method, we just define how we're going to use them. So we run it through BERT first, then we take the Polar output, and then we run that through the projection layer, and then the text encoder is done. And next up, we'll build the video encoder. So I'll go down and say class video encoder, like so. This will also inherit from nn.module, like this. And in the constructor, so in it, we'll just go ahead and say self. We'll go ahead and say super.init to call the constructor of the class we inherit from. And then we can go ahead and define what we call the backbone. So self.backbone equals, and then we'll need some vision model. So this is going to be the ResNet pre-trained model. So we'll say vision models dot, then let me see if it can auto import that. From torch vision, import models as vision models. And what I'll do is just go ahead and say .video and then .r3d18, like this. And then we'll say pre-trained true. So what this will do is just get the pre-trained model, ResNet 3D18 layers, and then we'll store that model in an instance property called backbone. This means that we can just go ahead and call it just like we did up here, where we say self.BERT. Down here we just call it self.backbone instead. But what we do is basically the same. We just use a pre-trained model, both there and also there. This one is just for text, and this one down here is just for video. So after doing that, we'll just go ahead and freeze all of the parameters again. So I can just copy this, and then I can say for param in self.backbone instead of self.BERT, like this. And then for each parameter, we say dot requires grad is false. This means that none of the parameters inside of this model will be able to be trained. This means that we'll have way less trainable nodes whenever we do train it, so training is much faster. And now we can then define whatever layer we want after this pre-trained model. So we want to first of all find out how many output nodes we do have in this model. So in the pre-trained model. And that number we can get from the backbone. So we can say number of features equals self.backbone.features.inFeatures. Great. And now we can go ahead and create a couple of layers we need. So self.backbone.fc equals neural network.sequential. So this will run these layers in sequence. So we'll need neural network.linear. We'll have the input number as the following one and the output number as 128. After that, we will need to run it through a ReLU layer like we explained in the architecture. And after that, we'll just run it through a dropout layer. So neural network.dropout. And we just set this to 0.2. I'll just go ahead and save this. And then right under the constructor, I'll define the forward function. So define forward, which will accept self and then also x. And then x is of course this entire tensor that contains all the video frames in one tensor. So I can go ahead and say x equals x.transpose 1 and 2. So remember how in the architecture we talked about how we needed to format all the frames into a format that this pre-trained models actually accept. So that is what we're doing now. So what we're doing is we switch the frames and channels inside this tensor. So basically what we do is we say batch, let me just make this a comment, batch size, frames, channels, heights, and width, like this. And we turn it into another reordered tensor with batch size, channels, frames, height, and width. So we just switch around frames and channels. So now frames is number 2 here, and channels is before frames. Good. And now that we have this video frames tensor reordered, we can then go ahead and run it through the backbone. So I can say return self.backbone x, like so. So what we do now, here is how it works. So you see how we can define this fc variable up here that is a part of the backbone. So this model R3D18 has a modular design, and the final layer in this model is a fully connected layer that can be replaced. So by setting all the parameters to not being able to be trainable, and then after that we define these other layers, only this linear layer right here would then be trainable. So we basically just keep the entire pre-trained body from this model and then only replace the classification head, which is the following one right here. So after this model has been run, then it is run through our own code right here, and then that result will then be returned as the inference result. And the alternative to that is just what we did up here, where first of all we run it through the pre-trained model, and then independently from that we can then define a projection layer, which we then run the output of this model through. So that is another way of doing it. So this is just an inbuilt feature from this model R3D18. So that is why we're using it. So going further down, we can just create the audio encoder. So audio encoder, which will again inherit from nn.module. We will create a constructor. So def init, like so. And then we'll pass in self. And now we would like to just call the constructor of the class above it, so it's parent. Then we can go ahead and say self.convolutional layers, which is an instance variable we will create. Then we can say neural network.sequential, so we'll run these layers in sequence. First of all, we would like to put in the convolutional 1D network. So this will have 64, and the kernel size of 3, like we talked about in the architecture. Then we put in the batch norm 1D with 64. This will normalize the output of this convolutional layer. After that, we'll put in the ReLU layer. So ReLU, this will add nonlinearity to the network. Then we can put in nn.max pool 1D, where we put in 2 as the parameter, so it'll reduce the data and then only keep the strongest signals. Then we can say neural network.convolutional 1D again. And then we'll put in 64, 128, and kernel size 3 again. So these will be the lower level features, like we explained in the architecture. These will be the higher level features, like so. Then after that, we just do the same batch normalization, just with the new size instead of 64, and then ReLU after that. And then what we want to do is just put in a neural network.adaptive average pool 1D, like so, where we put in 1, like this. And this will then take the average of all the time steps, which is the last dimension in the tensor. So now that we have defined all these convolutional layers, we can go ahead and freeze all of those because we do not need to train those. So we'll say for param in self.convolutional layers the parameters, and we'll just set requires grad to false for all of those. Great. After that, we'll just create the projection layer, which will be trainable. So I'll say self.projection equals neural network.sequential. I'll pass in neural network.linear with 128 to 128. Then we'll pass in neural network.ReLU, like so, and neural network.dropout, like this. We'll pass in 0.2 as the value, meaning it'll randomly drop out 20% of the nodes in the neural network. So up here, we'll detect patterns with this convolutional neural network, but we won't train it. And then down here, we'll take the result of all these patterns that has been detected, run it through our projection layers, and we'll then train this linear layer right here. And this should then be able to output something about the audio, which can predict the emotion and the sentiment. So we'll then just implement the forward function as well. So I'll say def forward, and then self and x. Then we can go ahead and say x equals x.squeeze 1. So what we do here is remove the single channel dimension that will be part of the MEL spectrogram as the input. So the MEL spectrogram will have an input that looks something like this, batch size, and then it'll be channel. So one channel, and then it'll be 64 MEL frequency bins, and then some amount of time steps, 300 for example. And then what we want to do is just remove this one right there. So we can just go ahead actually and create a method down here or not a method, a way for us to test it out. So I'll just go ahead and say batch size like this equals 2. Then I'll say x equals torch dot, and we just need to import torch from up here. So I'll just say import torch like that. Then down here I can say torch dot rand number like this, put in batch size, then I'll just put in 164 like so, and 300 as the time steps, just to simulate what the input would be for this forward function right here. So this is a dummy mel spectrogram basically. Then I'll say print, and then I would like to do this, say input shape like so, and then I would just like to print out the shape of this dummy mel spectrogram. And if we then go ahead and say x squeezed like so, squeezed equals x dot squeeze like so, x and then 1 like that, then we can just print out the same thing again, so the squeezed shape. So I'll just go ahead and try and run this code like so, python models.py, and just wait for it to finish. So we do get this input shape, torch.size, we have 2 as the batch size, then we have this 1, 64 and 300. So what it does is it just removes this dimension right here and makes it the size that we actually want. So that is exactly why we use this squeeze command. So if I just delete this and hop back up, I can just explain a little bit more. So the reason why we need this format right here as the input for the convolutional layer is the following reason. Right here we have the batch size, that doesn't really matter that much in this explanation, but these are the channels. So these are the frequencies in the sound in the mel spectrogram, and this is the time component. So this will be the x-axis, so it will be on the horizontal axis, and this will be the y-axis, so the vertical axis with the frequency, so low frequency or high frequency. And this convolutional layer will then slide over this time frequency, so it'll slide over the x-axis and then find patterns in the y-axis. So that is how it works and why it needs specifically this format. So if you gave it this format, it would then not know what to do with this one and think that the one would then be this component right here. So that is why we need to put in the correct format. So continuing with the implementation, we have squeezed this dimension. Then we can go ahead and run it through the conventional neural network layers, so these ones. So what I'll do is say features equals self.convolutional layers, and I'll pass in x from up here. And then I can go ahead and say return self.projection, passing the result through the projection layers. So I'll say features.squeeze -1. And the reason I do squeeze it is because the output of this features, so I'll say features output, will then be batch size, and it'll then be 128, like so, and 1. And the reason this is 1 is because we use this adaptive average pool 1D, which will then take the average of all the different numbers in the last dimension. So this will then just be num, this will then just be 1 because it is a single number that is the average of all the different numbers. We'll then just squeeze that and then run that through the projection layer like so. So this layer will learn, and we can then return the result of that in the forward function. Now that we're done with the encoders, we can go ahead and implement the fusion layer and also the classification heads. So what I'm going to do is just hop down and create a new class. I'll call this Multimodal Sentiment Model, inherit from neural network.module. I'll create a constructor, so init, and then I'll pass self into that. In here I'll just call the super, so the parent constructor, like this. And I can just go ahead and create an instance of each of these encoders. So I'll say self.textEncoder, and that will be equal to a new instance of the text encoder. I'll just do the same for the video encoder and also for the audio encoder, like this. And now we can just go ahead and create the fusion layer. So I'll say fusion layer, and then up here we can just say encoders. And the first thing in the fusion layer is just saying self.textEncoder fusion layer, like this, equals neural network.sequential. In here, we'll pass in a neural network.linear first of all. This will be 128 times 3, because each of these return 128 in their forward functions as the dimension. And then the output dimension will then be 256. So we'll compress it a little bit. This will be 384, and this will be 256. So we will compress the data a little bit. Then we'll normalize the output of that layer. So we'll say neural network.batch norm 1D, pass in 256. We'll then pass in relu to make it not as linear, and then we'll pass in a dropout layer to prevent overfitting. Great. So that is the fusion layer. Now we can just create the classification heads. So classification layers, or just heads. So this is the head of the model. So what will actually do the predictions. So this will then be self.emotion classifier, like so. And this will be neural network.sequential to run these in a sequence. Then neural network.linear will pass in 256 and squeeze that down to, or compress that down to 64. We'll then say neural network.relu, like so. Then we would like to pass in a dropout, neural network.dropout, like that, with a value of 0.2, like this. And then lastly, we'll just put in another linear layer, like we talked about, that will compress the data all the way down to 7 different options between 0 and 7. So this should be the emotion classifier, like this. And then we can go ahead and say self.sentiment classifier as well equals neural network.sequential. This should be neural network.linear, 256, compress it down. So we'll actually just copy all of these layers since they will be the same, apart from this last linear layer, which will compress it down to 3 different options: negative, positive, or neutral. Up here, the different options will then be positive, negative, anger, sadness, I think it is, and then what else? I think it's anger or something. So options like this that describe the 7 different emotions. Great. And then that will be the entire architecture of the model. So now I just need to define the forward function. So I'll go down and say def forward, like so. I'll pass in self, text inputs, video frames, and audio features, like this. So these are all the inputs for the model. Then I'll go ahead and say text features equals self.text encoder. And then I'll say text inputs, like this, text inputs, and that should then be input IDs. And then this needs to be inputs. Then I also need to just copy that line and say attention mask. So this text inputs will come from over here in the dataset. So this will be the text inputs, and we can then get the input IDs and the attention mask, like so, and just pass that in as the inputs to the text encoder. So this one receives input IDs and attention mask, like so, and uses those for inference. Great. So right beneath this text features, we can go ahead and say video features equals self.video encoder, and we just pass in the video frames. For the audio features, we just do the same, pass the audio features, so the audio input, into the audio encoder, so we can run those through the pre-trained model. Then we can just, after doing that, concatenate all the results. So I'll say concatenate multimodal features. Then we'll say combined features equals torch.cat, which will concatenate them. We'll then say text features. We'll say video features. And we'll then say audio features, like this. And we'll just set the dimension to 1, like so. So what happens here is that first of all, whenever we do inference on the entire model, what we do is we take the inputs, so the text, video, and audio, which are the model inputs, we run those through each of their encoders. So this one will trigger the forward method in the text encoder. This will trigger the forward method in the video encoder, and the same for this for the audio. So now we have the inference for the different encoders. And now we just need to combine these results into one tensor storing everything. So the first dimension will be batches. So it will be batch size. And the second dimension will then be the features, like so. So that's why we set dimension to 1, because if we set it to 0, then it would stack the batches, and we do instead want to stack the features, because this is index number 1. So with these combined features, we can then run that through the fusion layer. So I'll say fusion layer, or I can even just say fused features, like so. And I can go ahead and say self.fusionLayer and just run that through the forward method in the fusion layer. So that is the following layer right here. Now that we have run it through the fusion layer, we can just take the fusion layer's output and run that through the individual classifiers, so emotion and sentiment classifier. So I'll say emotion output equals self.emotion classifier, and we'll just pass in the fusion features or fused features. And for the sentiment output, I'll go ahead and say sentiment classifier like this, and also pass in the fused features. So these two outputs will then just be the numbers and the last output of the model. So this emotion classifier head will then output either sadness or anger, and this one will then output either a negative, a positive, or neutral, and this one will obviously have a little bit more options than just these two, but this will then output two numbers, and now we just need to map those numbers to whatever we want to have those numbers represent. So remember up here, those numbers were the following ones: 0 was anger, 1 was disgust, etc. So we just need to take these maps and just use them in here as well to map from number and then back to label. And we will just do that after this. So first of all, I'll just return the results. So emotions will then be emotion output, and sentiments will then just be the sentiment output. So now we can just run inputs into the model, and we should see all of these actually run. So the text encoder, the video encoder, and also the audio encoder. It should run through those, then through the fusion layer, then through the two classification heads, which will then output two numbers. To just test out that everything works before we move on, we can just go ahead and create a main method again. So if name equals main, like so, then what I'll do is just do some code in here. So I'll say dataset, and we'll just want to test with a real sample. So equals melt dataset right there, and we just need to import that like so. And then inside this, we can just reference the training set. So we reference the set right here. So that is what we load into this dataset class. Now this one should be train splits. Let me just check. It is great. So after that, we can just get the first sample. So I say sample equals dataset 0. Then I can just initialize this model we are testing. So multimodal sentiment model. Then I can say model.evaluate to set it to evaluation mode, so we will not train it. And then I can go ahead and say text inputs equals input IDs. So what I'm doing is just taking the sample text inputs. So up here, what we do return is text inputs with input IDs and attention mask. And then we just need to wrap those in a way that we can pass them into this multimodal sentiment model. We'll just take and prepare the video frames as well. Video frames equals sample, and then audio features. Audio features equals sample, and then audio features. Great. Then we can go ahead and say with torch dot inference mode. Additionally, you could also say no grad, but yeah, I'm pretty sure they changed it to inference mode now. Both do work though. And then we can go ahead and say outputs equals model, text inputs, video frames, audio features, like that. And then we can say emotion probabilities. This will be torch.softmax, like so. first dimension like this. This will be sentiments and sentiment probabilities like that. And then after that, we can just go ahead and print out the results. So print, and then predictions for utterance. Under this, I'll just need these two mapping tables up here. So emotion map. So I'll just go ahead and paste these in like this. And then I'll just remove this self. Now I do need to reverse these, so I'll need to say 0, negative, 1 neutral, etc. And the same for over here. So I'll just comment this out and say 0 anger, 1 disgust, etc. Like this. And now we should be able to say for index and probability in enumerate emotion probabilities, and then we can just print out these, and then we just need to print it out for the sentiments as well, like so. And now if I go ahead and just open up a new terminal and say Python models.py, and we just need to, of course, change directory to training, like this. Then what we see right now is there's no module called training. So hopping all the way up where we imported, it does say training.melt dataset. Maybe we can import it straight away like this, because we're in the same folder. And now it seems to work. We just need to let it finish. Great. So for the first sample, what we see is the following. This is the one, a 5-second clip. And it says also, I was the point person at my company's transition from blah, blah, blah. And then it says neutral, neutral. That is what it is supposed to be. So that is the label. And then down here, we have neutral right there. And we have neutral right here. It did guess negative as the most probable sentiment, emotion. So that is definitely not correct. But this model has also not been trained. But now at least we do know that it works, which is very nice to know. So the output of a model will not be a single label like this. It will be the probability for each. This means that we'll have the probability for each sentiment, and then for each emotion, and then the emotion will just be the one with the highest probability. But we'll also do the same for emotion. So that is how it works with the output for a classification problem like this. Next up, I'm going to create another class called Multimodal Trainer. So I'll say class Multimodal Trainer, like so. And the purpose of this class is to just handle all the model training. So it'll handle the training loop, update the model weights, track the losses. It'll also do validation and testing on the datasets. It'll also optimize the neural network, and additionally also log the logs from the neural network to somewhere where I can read the logs. So inside the constructor, which will just be def init, I can go ahead and pass in self, and then the model, and then also train loader and value loader, like so. Then I can say self.model equals model. I can say self.train loader equals train loader, self.value loader equals value loader. So this is what will be run whenever we train the model. Now, first of all, when training a model, I would like to log the dataset sizes, because that could be pretty helpful in debugging purposes. So I'll say log dataset sizes, and then what I want to do is just say train size equals the length of train loader dot dataset. And I'll just go ahead and do the exact same for the size of the value dataset right under that. And then we'll just print out the dataset sizes. So I'll say print dataset sizes, like so. And I'll just print this on a new line, and then I'll say print again. And then I'll say training samples, like so. And this should just be train size, like this. Then I'll go ahead and say validation samples. And I'll also say batches per epoch. So print f, like this. And this will just be the length of the train loader. And and then I'll just go ahead and do that as well. So by using this comma right here, if it were to print out 10,000 for example, this would just instead be 10,000 like so. So it'll look way nicer when it is being printed out. And then we can go ahead and add in the optimizer. So up here in the init class as well, or the init function, we can go ahead and say self.optimizer, like this, and then saying torch.optim.atom, like so, passing in an array, and then I'll say go like this. This just needs to be fixed, so I'll just do this, and then just say weight decay, and then just set this as the weight decay. Great, so let me just talk about learning rates for a little bit. So with learning rates, these are kind of the values that are considered high or low, just so you have some reference to what it is. So very high would be something like 1, high would be something like 0.1 to 0.01, and then medium would be 1e in -3rd, low would be something about 1e in -4th, and then very low would be something like 1e in -5th. And then with that in mind, we can just go ahead and set the learning rate for each of these encoders, fusion layer, and also classifiers. So the learning rate for this one is going to be 8e -6th, like this. And below, we're going to set it to -5th. Below that, we're going to set it to -5th as well. Below that, we're going to set this to 5e -4th, so 5 right there. And below that, for the classifiers, we're going to set the learning rate to 5e -4 as well. Down here, we're going to set it to 5e -4 as well, like this. And this weight decay down here is a regularization technique. So a regularization technique is just a way to help prevent overfitting in this case. So what this will do is encourage smaller weights and then improve generalization for the model. So there is no definite answer to what your learning rate should be. So when you write a model from scratch, you can try and pick a learning rate between the low and the medium value range. And then based on whether it learns too slow or the loss is unstable, you can increase or decrease it. So if the loss is unstable, you can try and decreasing it by 10x. And if the learning rate is too slow, you can try increasing it by 10x. So learning rates are what we call hyperparameters. So there will be values that are better than others, but often if you have a model architecture that works, often you can tune these hyperparameters after that. So you can train 10 different models with 10 different learning rates and then see which learning rates works the best for this model. So when building this model, I just tried out different learning rates until I found some learning rates that actually work for me. So there might be learning rates that are way better than these ones, but those were the ones that work for me and for the results, which you'll see later on. So that is also why I can't give you a specific answer to why I picked just those. I picked these by experimentation, picking some medium to low learning rates, and then trialing my way forward until I found someone that fit fine for my purpose. And now we can implement the learning rate scheduler. So I can say self.scheduler, like this, equals torch.optimizer.learning rate scheduler dot reduce learning rate on plateau, like this. Then I would like to put in the self.optimizer as a parameter, like this. Then I would like to put in the mode, and the mode is going to be minimum. So what that'll do is that it'll reduce the learning rate when loss stops decreasing. And then I'll put in factor of 0.1. So it'll reduce it by 10x by multiplying it by 0.1 whenever we have 2 consecutive epochs, and those epochs will be set here. So when we do have 2 consecutive epochs with no loss improvement, we multiply it by 0.1, and that way we can change the learning rate to prevent it from plateauing. So preventing the loss from plateauing, sorry. And then just to implement the loss function, we'll just go ahead and say self.emotion criterion equals neural network.cross entropy loss. The only thing we'll define for this one is a hyperparameter called label smoothing, like this, and we'll just set that to 0.5. And this again is a value I found works well for the specific neural network by trial and error, not something that I can definitively say this is the best value because of this math. So that is why I picked this specific value in case you are wondering. So the next one is going to be sentiment criterion. So this loss function is going to calculate the loss for the entire neural network so we can see how good it performs. And this way this loss can be used to improve the model weights by the optimizer. And this label smoothing works by slightly altering the true labels in a classification task to prevent the model from becoming too confident. So instead of assigning a label a probability of 1, you assign it slightly less, such as 0.9, and then distribute the remaining probabilities. So this would be 0.1 across the other classes. And this helps the model generalize better and also reduce overfitting. So for this sentiment, for example, this can be negative, positive, and neutral. So let's say that it guessed neutral. Then neutral would be 100% certain, so we would allocate 100% of the confidence towards neutral, but with label smoothing, we would instead say 0.9, and then distribute the rest, so that'll be 0.05 here, and 0.05 here as well. So because it is less confident in neutral, so instead of 1, it is 0.9, it'll generalize better. And you can then play with the values, such as this one and this one, to figure out which ones works the best for the model accuracy. So let's go ahead and create the next method to train a single epoch. So I'll go ahead and create a new method called train epoch and pass in self. Now, first thing we want to do in here is just call self.model.train like this. So we just need to spell it correctly. Otherwise, this is correct. And then we can go ahead and create a dictionary storing the losses for each batch we are looping through. So I'll say running loss equals, and then total 0, and then also emotion 0 and sentiment 0 like this. So this will store the cumulative loss which we'll add to it whenever we run through a single batch and train on that. So we can then go ahead and say for batch in self.train loader like so. We then first of all move both the model and also all the tensors to the same device. So what you can do in PyTorch is you can have your tensors on either the CPU or the GPU, so you can have them on different devices and you can move between these. So we want to make sure that all the tensors we're going to need which will also work together, is stored on the same device. So first we'll say device equals next, and then self.model.parameters to device, or .device, sorry. So what we'll do is just find out what device the self.model.parameters are on, and that is the device we're going to put all the tensors, so the text inputs, the video frames, etc. on. So we'll then say text inputs equals, then I can go ahead and say input IDs, and we can get this from batch, text inputs, and then input IDs, like so. And we can then also say to device. We'll just go ahead and do the same for attention mask and save that. So in here, if I just search for attention mask, we can see that this is why we have the following indexing that we have here: text input and attention mask. So we have text inputs and then attention mask right here. So that is why we get these values by doing that. Good. Next up, we can just define the video frames. So I'll say video frames equals batch, where we get the video frames, and we then also say .toDevice to move it to the same device as the model parameters are on. We can then go ahead and say audio features equals batch, and then we get the audio features and say .toDevice. Next up, we can go ahead and get the emotion labels, like so. And this will just be emotion label .toDevice, and we can then lastly get the sentiment labels, like so. So now that we have all the different tensors on the same device as the model parameters, so they will work together, we can go ahead and just calculate the gradients, for example. So what will happen in each batch is we'll do a forward pass, we'll also calculate the gradients, do a backward pass, and then track the losses and step through the optimizer. So those are some of the different things we'll do right here in this for loop. So first of all, we'll need to reset the gradients from the last run or the last iteration in this for loop. So I'll just go ahead and say self.optimizer.0grad like this. So what happens here is basically just we zero the gradients and reset them. This way, none of these gradients will carry over from the last iteration in this for loop, so we can start over fresh by calculating the new gradients. So first we'll do a forward pass. So we'll just run inference on the model. So we'll say outputs equals self.model, and we'll pass in the text inputs, the video frames, and also the audio features. So these are the inputs for the model. Then right below that, we'll just calculate the losses because we have now run inference on it. So we can say calculate losses using raw logits like this. Then I can say emotion loss equals self.emotion criterion, and we pass in the outputs and then emotions and then also the emotion labels like this. So raw logit is basically just the direct output from the final layer, so it's unnormalized classes. And this emotion criterion up here is just the loss function for the emotion. So what we want to do is pass in the outputs, so the inference outputs. So this is what the model guessed, and this is what the actual values should be from the training data. And the loss function will then compare these two and find out how well the model performed and calculate the loss from that. So let's just go ahead and do the same exact thing for sentiment. So I'll go ahead and say sentiment loss equals sentiment criterion, which was the second loss function. We'll just pass in sentiments instead, and then also sentiment labels. And what we want to do is then just find out the total loss. And the total loss will be emotion loss plus sentiment loss, exactly like this. And after calculating the losses, we can go ahead and calculate the new gradients because we zeroed all the gradients up here. So we'll just say backward pass and then calculate gradients like this. So this is just the derivative of the loss function with respect to all the different weights. Then I'll say total loss dot backward like so. And now we have calculated all the new gradients. Then what I want to do is just implement a little feature called gradient clipping. Going back earlier in the video, you might remember the gradient descent example. So the gradients we calculate are just the slope of the loss function, telling us in which direction we should change the weights to decrease the loss. So the larger the gradient, the more aggressive the change in the weight will also be, because a steeper slope means the loss function is more sensitive to weight changes. So to prevent aggressive changes, especially in the start, where the curve might have an even deeper slope, we'll scale down the gradients if they become too large. And we'll do this with gradient clipping. So I'll say torch.neural-network.utils.clip gradient norm. Then I'll pass in self.model but parameters like so. And then I'll set max norm to 1.0 like this. And this should take care of the gradient clipping for us. So I'll say gradient clipping just for reference. Great. This value you can obviously also play around with to find out which value works the best for you. This is just the default value I used for training, and this worked fine for me. So now I'll go ahead and step through the optimizer. So I'll say self.optimizer.step like this. So what this will do is optimize the model weights using the gradients, and then using the optimizing rules from the Atom optimizer. So Atom optimizer will take care of this for us. And then what we can do is just go ahead and track the losses. So I'll say track losses like so, and then say running loss. And then first of all, I would like to track the total loss. And this should be plus the total loss.item. And I also want to track the loss for the emotion and the sentiment. So this is for emotion and this is for sentiment. So going up to these losses, these are just the losses that we calculated from the forward pass. And these should improve over time as we do the backward pass and calculate the gradients, and then also step through and update the model weights. So now we can just go ahead and hop outside this for loop. So now we have looped through all the batches and we have optimized the weights for all the batches. And what I would like to do is just return a dictionary containing the average losses over all the batches. So I'll go ahead and say return and then return a dictionary. Then I would like to say, first of all, for key and value in running loss.items like this. Then what I can do is go ahead and say key. So I'll create a new key inside this dictionary, and that should be the value divided by the length of self.trainloader like this. So by dividing each loss with the amount of batches, we can then find out the average loss per batch for both total, emotion, and sentiment. So that is the logic behind this return statement. Whenever we run through a single epoch, like we do up here, what we do is we train the data on some batches or some samples from the training dataset, and then we also find out what the losses for that training dataset is. But every time we have run an epoch, we also want to validate how well the model does on the validation dataset. So we have done it on the training now, so after each epoch we also want to go up to dev and then test it on the validation dataset to check if the model is overfitting or not, for example. So going down, we can create a new method which we'll call validate. So we'll call it validate, pass in self, and in here we set the model to self.model.evaluation mode. We can then say validation loss, and this will also just be a dictionary with the total loss, emotion loss, and the sentiment loss. We then also would like to store all the emotion predictions and labels along with all the sentiment predictions and labels. And the reason we want to do that is to be able to calculate the accuracy and the precision of the model. And I'll come back to exactly what those are in just a second, but first of all we'll just store them to start with. So I'll say all emotion labels or predictions, like so. This will just be an array. Then I can say all emotion labels. This will also just be an empty array. We'll just do the same for sentiment, so sentiment predictions and sentiment labels. And what evaluate does up here, so self.model.evaluate, is it'll change the model behavior to disable the dropout layer, for example, because we do not need those whenever we evaluate. What we then need to do is say with torch.inference mode. And what torch.inference mode does is that it'll make computation faster by calculating the gradients every time we do an inference on it. And now that we're in inference mode, we can then go ahead and say for batch in self.valueLoader, like this. And inside here, we can just first of all find the device. So the device will then be the exact same thing as we did before. So next, self.model.parameters. Just did a lot of things right there. So self.model.parameters. So we'll just find the device from where the model is located. So if the model is currently on a GPU, then we save the GPU in the device. And if the model is currently on a CPU, then that is what we save in this device variable right here. Next up, we can go ahead and find the text inputs and the video inputs, just like we did before. So we'll just copy this exact logic and paste it in right inside this loop right here. So it'll look something like this, like that. Great. So now we have all the features and also all the labels, and we have moved those to the correct device. Then we just need to go ahead and first of all do the forward pass and then also calculate the losses after that. We do not need to reset the gradients because we have not calculated the gradients anyways. So I'll go ahead and do a forward pass like this. We pass in the inputs for the model, and then we'll just calculate the losses on the validation dataset like this right after. And after we've done that, we can go ahead and collect all of these losses and put them into the following arrays right here. So first we can take the following. We can go ahead and say all emotion predictions dot extend. We'll extend it with outputs of emotions like this. So what we basically do is that we save the indexes of the emotions with the highest probabilities. So the output of emotions might be something like this. So we have an array of different batches, an array of different samples. So for each sample, we might have something like this, 0.1, 0.8, 0.1. That is the first sample. We might have another sample that is 0.7, 0.2. 0.2 like this, and then also 0.1. So if this is what we pass into the following, it'll then take these numbers, find the highest one, so 0.8, take the index of that, and in this case it is going to be 0.7, that is the highest. So the predictions will then have the following appended, like this, and we'll then have 1 as the first index, because that is the highest one right here, and then 0 as the second index, because that is the biggest one right here. So this will correspond with the maps from up here, which also uses indexes to track which label it is. So if it is negative, then it'll be neutral, if it is neutral, that is the correct one, then we'll have index 1, and we can then compare this index 1 with index 1 down here to see if that is the same. So that is how we are going to compare what the actual sentiment and emotions are, and then compare those to what the model predicted to calculate the accuracy. So that is why we take this argmax right here. So now that we have all the emotion predictions and the indexes of those, we can go ahead and take all the emotion labels. So I'll say all emotion labels like this, and then I can say dot extend. And what I want to do is just say emotion labels dot CPU dot numpy. So we want to store them on the CPU because that is where we will do the processing. And then we also want to convert it to a numpy array because the library we'll use to do the processing, so calculating the precision and the accuracy, will use a numpy array. So let me just see why this one is not saying it correctly. So it needs to be labels and predictions like so, and now it should work. So if I just go ahead and do the same for sentiments, I can say all sentiment predictions like this dot extend, and then right here I can just do the exact same, just with sentiments instead of emotions, and I'll just do the same for the labels too. And then lastly, I'll just track these losses in the array up here, in the dictionary called validation losses. So I'll just go ahead and say track losses like this, and then validation loss, and then total plus equals total lost item. And then I'll do the same for emotion and the same for sentiment like that. And then outside this for loop, so right outside this for loop, and then actually outside the inference mode as well, we can go ahead and calculate the average loss for each batch. So I'll say average loss equals, and then key is going to be the value divided by length. So I'll take, let me just go ahead and do it in another way. I'll say for key and value in value loss dot items, and then the key is going to be either total emotion or sentiment, and the value is going to be the loss. And we would like to find the average loss for each of these per batch. So I would like to say key value divided by length of self.value loader, just like we did before, for key and value.loss. So what we do is just find the average loss per batch for each of these, and we store that in this average loss dictionary right here. Now we can just compute the precision and accuracy like this. So to do this, we'll just need to import a couple of libraries up here. So first I'll just import a library, or install a library, called scikit-learn or scikit-metrics. So I'll say pip install scikit-metrics like this, and I just need to put in an extra L and also an S right here, and now it should work. So let me just wait for it to install, and now it is successfully installed. And then what I can do is go ahead up here and say from sklearn.metrics import precision score, and then also accuracy score, and we can then use these two helper methods to calculate these automatically, instead of having to do it manually. So going down here again, we can then calculate the precision and the accuracy. So we can say emotion precision equals precision score, and we can then say all emotion labels, pass in all the emotion predictions, and then just say average weighted. And we'll just do the same for the sentiment prediction, precision. So that'll just be all sentiment labels and all sentiment predictions. And I just want the emotion accuracy as well. And the accuracy score will be all emotion labels and all emotion predictions. And lastly, the sentiment accuracy, we just do this. So an accuracy score tells us the overall correctness of the model. So that is going to be the right corrections divided by the total predictions. So that would be something like, I got 90 out of 100 questions right. And then for the precision down here, it is going to be the correctness or the precision of the positive predictions. So we'll say true positives divided by all predicted positives. So when I predicted happy, I was right 80% of the time, for example. So that is what the difference between precision and accuracy is. So we'll look mostly on accuracy, just to find out if the model is good enough that we can actually use it for something. So with these values, we can go ahead and just return the average loss, like this, along with the dictionary containing emotion precision, emotion accuracy, sentiment precision, and also the sentiment accuracy. Then one last thing I would like to do inside this validate function is the following. I would like to just step through the scheduler. So I'll say self.scheduler.step, and I would like to pass in the average loss total. And the reason we are stepping through the scheduler in the validate method instead of in the train method is because the validation loss is a better indicator of model performance than the training loss is. So this will help us prevent overfitting by reducing learning rate when the model stops improving on the validation set and not on the training set. And what it did again was that it would adjust our learning rate if no improvements had been seen for 2 consecutive epochs. So now we have successfully implemented a method for validating the model performance on the development or validation dataset. And this will be run every time we have run through a single epoch up here with the train epoch method. What we would like to do though is do all of these things again, just after running through all the epochs, so when we are finished training, to test the model on the test dataset. So we use the train dataset to test the model, to train the model, and then we track those losses. Then we use the development or validation dataset to track how the model is performing on unseen data during training. And then we would like to test it once to just evaluate the general model performance on some other unseen data it has not seen before on the test dataset. And we'll need to do the exact same things as inside this validate method, except for a couple of things. So I'll just make this method support both cases. So I'll pass in a data loader so we can differentiate between the validation dataset loader and then the test dataset loader. Then I would also like to pass in the phase, so that is going to be either validation or it is going to be test. So right now this is also called validation loss. So if I just find that and then replace that with losses, like so, we can then hop down to where it says losses and just replace that with a more general word for losses. And then we of course also only need to step through the scheduler if we are in the validation stage. So if phase equals validation, then we step through the scheduler. Otherwise we'll not do that. And then instead of the value loader right here, we can just pass in the data loader, which we will get from our arguments up there, like so. So this should be fine for now. In this way we can use this method, I'll just call this evaluate instead. We can use this evaluate method for both the validation case and also the test case in the end. So data loader isn't being used right now, and that is because we are putting in self, and that is not correct. So we just need to remove self dot those 2 cases, and now that should work fine. Perfect. So what we're able to do now is that whenever we want to train our model, we create a new instance of this multimodal trainer where we pass in the model, the train loader, and also the validation loader. And these we can get from in here, from calling this method prepare data loaders, which will return the train loader and also the development set loader. So passing those into this class right here, for each epoch we would like to run, we just call this method. So if we want to run 20 epochs, for example, we call this 20 times. And then after each time, we run this evaluate method as validation. And then after running all those epochs, we can run the evaluate method as the evaluate instead. And then in the meantime, you can track all of these numbers about how the model is doing during training. So this means that we can create some nice graphs, for example, about how the losses are doing, and also if the accuracy is improving overall. So we have all of these numbers right now, but we don't really have a way to visualize them with any graphs. So what I'm going to do is use a tool called TensorBoard. So I can say from torch.utils.tensorboard import summary writer. Let me just see. I should be able to access it like that. Great. And then when we do initialize this multimodal trainer or instantiate it, what we would like to do, or this is not the trainer, this down here is the trainer. What we would like to do is just create a directory for where we want to store the logging files, and then we can then open up a dashboard called TensorBoard and show those log files. So first I'll just create a timestamp that is supposed to be the name for the log file. So I'll say timestamp equals datetime, and we just need to import datetime up here. So I'll just create a new line and say from datetime import datetime. Going back down, I can say .now, and then .strftime, like so. And then what I would like to format is going to be %b, and then also %d, like so. And then I would like to put in hour, minute, and then seconds. So an example of this would then be December 17th, and then 14, 22, 35, like this. So you get the date, and then you get the hour, you get the minute, and then you also get the seconds in the day. And this should then be part of the file name, so we can see which date the logs come from. So I then want to create a base directory where we want to store the log files. So this should then be, if we are running on training, what we can go ahead and do is put it onto OPT. So this is in Linux, and then machine learning, output, TensorBoard, like this. And we do this if the following environment variable is set. So sm model directory in os.environment, like this. Otherwise we just put it in runs, and we just need to go ahead and import os from up here, like this. So whenever we upload a training script to AWS SageMaker, it'll inject this environment variable into the script. So this way we can know whether or not we are on SageMaker or whether or not we are running the script locally. So if it is on AWS, we would like to save the log files to this directory. Otherwise, we just save them in a directory called runs, right here in our local directory folder structure. So the log directory will then become log directory equals formatted string, like this, and then base directory /run, and then we'll put in the timestamp. So the name of the log file will then be run _ the timestamp. And we can then instantiate a new instance of this writer. So I'll say self.writer equals summary writer, where we pass in the log directory as where we want this writer to log to. Then I can go ahead and say self.global step equals 0. And this global step is just a way for us to know at what epoch we are currently at whenever we do the logging, so we can associate specific values with specific epochs. So we can say, okay, this loss is at this epoch, for example. So down here, we'll go ahead and set this global step in train epoch. So after each batch has been processed, we'll just say self.globalStep plus equals 1, like this, and save. And now that should be fine. Then I'll just go ahead and create a new method down here, and I'll call it a log metric. So log metrics, I'll pass in self, then the losses, like so, the metrics, which I'll set to none as a default, and then phase, and I'll just set the phase to train, like this. Then I'll open it up and say if phase equals train, then I'll just say self.current train losses equals losses, like so. So I should be able to compare the training losses with the validation losses. So this is for the training phase, and this else statement is going to be handling the validation phase, like this. And then I'll go ahead and just use this current train losses whenever we are ready to do that. But first of all, I'll just define that up in the init function up here. So I'll just initialize it to the value none. So self.current train losses equals none. So it'll at least be initialized down here. And then whenever we call this log metrics method, then we'll set that to the current training losses. And this way we can compare the validation and training losses right here. So first I would like to log the total training loss. So I can say self.writer.add scalar, like this. I would like to log it under the name loss, total, train, like so. Then I can pass in self.currentTrainLosses, get total, like this, from the dictionary. And then I can say self.globalStep, which is the epoch we are currently at. So what this addScaler method will do is that it'll add a single numerical value that changes over time. So this could be loss or accuracy or learning rate, for example. And in TensorBoard, this is going to be visualized as a line graph where x-axis is the training steps, so the epochs, for example, and then the y-axis is going to be the scalar value. So in this case, it is going to be loss. So we can then visualize these different losses, such as train or validation, for example, and compare these to see if the model is overfitting, underfitting, or what is just going on. So next up, I would like to add the validation loss. So I'll go ahead and say, just copy this line actually, and then loss total validation, and this should then be validation, like so, with this being losses and not current training losses. So losses will be the following variable we set. Just let me see, right there. So it'll be something like this, where we have the total loss, and that will be the total validation loss. Now, going back up, we are now able to log the total validation loss. This just needs to be total instead. And now that we have the total losses, we can go ahead and just log the emotion losses specifically as well. So this will be emotion instead of just total. And I'll just put in total right there as well. And then, emotion right there as well. And then emotion here as well. And we'll just do the same for sentiment too. So it'll look something like this. Sentiment, like that, and also right there. And now that we have the losses down, we can just go ahead and log the accuracy and precision as well. So if metrics, metrics can be none because it is not everywhere where we might want to log the metrics, then I can say self.writer and then add scalar, like so. Then we just put in a formatted string with phase, emotion, precision. Then I put in metrics with emotion, precision, and then self.globalStep as well, like so. And then I'll just go ahead and do that for these 4 different ones. So I'll say emotion accuracy and emotion accuracy here as well. And then I'll just copy this accuracy and paste it down right there and right there. And then just call this sentiment precision instead. And sentiment accuracy. So now what we have is we are also logging the emotion precision, the emotion accuracy, sentiment precision, and sentiment accuracy like that. And now we should be able to call this log metrics method wherever we want to log these numbers. So every time we have trained an epoch, for example, so that is going to be down in train epoch, then under these losses, we can go ahead and say self.logMetrics, pass in a dictionary, and I'll say total is going to be total loss.item, emotion is going to be emotion loss.item, and sentiment is going to be sentiment loss.item. And whenever we have done this evaluation, then down, whenever we have calculated the precisions and accuracies, we can then also just log these. So I'll say self.logMetrics. I'll pass in the average loss, because that is what we have up here with average losses. And then I can pass in the emotion precision, emotion accuracy, sentiment precision, and sentiment accuracy. And the phase will just be the same phase as up here. So default validation, otherwise you can override it. And then this will then be the losses. So the first argument, and then the metrics will then be the second argument. So because the argument is supplied, it'll then also log the precisions and accuracies as scalars. To test out the logging, I'm going to go ahead and create a new file in here called testlogging.py. Inside this, we'll just create a mock instance of these different classes we'll need to just test out the logging. So I'll say def test logging. This will just be a single function, and we'll just run this function if name equals main. So if we run this file like this, then we'll just call test logging. In here, I'll just create a mock data batch first of all. So I'll say batch equals named tuple. And this named tuple should contain a batch with text inputs, video frames, and audio features, but not these two labels though. And we can just import this. So we can say from collections, import named tuple, like that. So from, and then under this batch, I can just go ahead and say mock batch equals, spelled correctly though, mock batch equals a new batch. And here we set the text inputs to be input IDs, and the input ID should just be torch.once. So we'll just import torch like this. So we can go ahead and say torch.once, and we'll just put in a 1 like that. And then also a tension mask, which will also be torch.once. So we'll just fill out with the ones in all these tensors to just make a bunch of dummy data basically. So this torch.once just returns a tensor filled with scalar value 1 with the shape defined. So that is perfect. Then we just need to create a mock loader as well. And that is going to be a data loader. So we can say from torch.utils.data import data loader like so. And then we just say import data loader, and we put in the mock batch like this. Great. Then I can just go ahead and initialize the model. So I'll say model equals, and then we're just going to need our model. So I'll say from training.models import multimodal sentiment model and multimodal trainer. So model is going to be multimodal sentiment model like this, and trainer is just going to be multimodal trainer, and we put in the model, the mock loader, and then also the mock. So for this multimodal trainer, we have the train loader and the value loader. So that is why we put in both of these mock loaders at the same time. It is just a mock loader after all. Now we're just going to simulate some training losses. So we'll say total is 2.5 or something, and then emotion is going to be 1, and then sentiment we can just set to 1.5, it's fine. And then I'll say trainer.log metrics, train losses, and we say phase equals train like this. Now we can just simulate some validation metrics. So this says validation losses, that is fine. And we then need some validation metrics too. So let's see if we can figure that out. We have emotion precision. That is just going to be, let's just say this. And then we have emotion accuracy. That is just going to be something else. Then we have sentiment precision and sentiment accuracy like that. And we can just go ahead and say trainer.log metrics again. We put in the value losses and the value metrics, set phase to validation. And then we can go ahead and just run this. So I'll open up a new terminal in the root. Then I'll say Python test logging.py like so. And let's just go ahead and see what happens when we do that. So it is running and nothing is really happening right now, but I'll just wait it out. So it says no module named TensorBoard. So I'll just go ahead and say pip install TensorBoard like so. And let me just see if that installs properly. And it did. So now if I just go up and run the same script again and just wait it out, we can just see what happens. So it can't find the module melt dataset. So maybe if I move this into training, the paths will be a little bit easier for it to understand and remove models like that. Then I can say cd training and then run the same script again. So python test logging.py. And now it says multimodal trainer has no attribute losses, but we do see this run folder being generated though with an events file, so that is pretty nice. And looking into the error, if I just copy this self.losses, we can see that it's inside models.py at line 200. So that should be right about here. So we see that it says self.losses, but self.losses isn't really a thing anymore because we're passing losses in right there. So we're just going to use losses instead. Hop back to the test.logging, run it again. And now we see the following. It just works without any errors. And inside this runs, we have another folder right now. And what we can then do to start the dashboard to check out these run files is the following command. TensorBoard ---- or -- log directory. And then we just put in the log directory. So that is going to be runs like so. And then we can just try and run that command and see what happens. So now it is exposing a port on localhost, so 6006, and we can just go ahead and open that up in the browser. So I just opened up TensorBoard right here in the browser, and we're able to see these two runs that we created before. So the first one was invalid because it only finished half and then an error occurred, but the other one right here should work fine. So what we can do is we can see the loss and we can see the validation. So the loss is ordered under loss, emotion, and train, and the validation is ordered right here under validation and accuracy. So we can see these different scalars, which are just graphs over time, and we can see the values over here on the y-axis. So that is the power of having TensorBoard. We can really visualize the data like so. So under scalars, for example, we can also see all the scalars like so, and now we can see the scalars in another way. So that is why we're using TensorBoard to just visualize that. So when more data comes in, we'll be able to see the loss as a graph that hopefully goes down, and we can then compare the training loss, for example, to the validation loss to see if we see overfitting or not. And down here in the validation accuracy, we can then also see how accurate the model really is. And when the model is used for testing, so when evaluating the model after training it, we can go ahead and see if the accuracy is good enough for us to use the model. So this is TensorBoard, and that was also a little explanation about why we're using it. Now we're back in Visual Studio Code, and we can go ahead and remove the runs folder, which I just did, and then close down the terminal. One thing we can do before moving on to the training is just counting how many parameters we have in the model. So I'll just create a little script called count parameters like so, .py. Then we can go ahead and create that file, and then create a new method in here called count parameters like this. We pass in a model. We'll then just create a parameters dictionary like this, and then say text encoder 0, video encoder 0, audio encoder 0, and just do this for all the different layers. So this will be Fusion layer, and then also the emotion classifier, and then lastly the sentiment classifier. Then we can say total params like so equals 0. Then we can say for name and parameter in model.named parameters like this. Then we just go ahead and let this auto complete, and then we down here just take this and move it up. So for name and parameters, we say if parameters dot requires a grad. Then we put in this code, and then we say parameters count equals this. This way we do not have to do this every single time. Like right there, and the two last places like so. And then after doing that, we can go ahead and just return parameters dictionary along with total parameters like so. And now we just need to create this if main. So if name equals main, then what we'll do is say model equals multimodal sentiment model, and we just need to import that, of course. So up here we'll say from, and then models, import multimodal sentiment model like that. Now we can say params dict and total params like so equals count parameters, but we pass in the model. We can then say a parameter count by component, and then this will be for component dot counts in parameters dictionary.items. We can just print out these, and let me just go ahead and print them out in a nicer way. So I'll go ahead and say 20s, and this should be formatted as a decimal number, and then parameters like so. And now if we just go ahead and down under that, just print, we'll just put in a new line, total trainable parameters, and this should then be a string like this. Now we can right click this training directory, say open an integrated terminal, then say Python count parameters.py, and we should then be able to see how many parameters there are in total. And it says something about this param count not being there, so we just need to indent this once more. So we only want to count parameters that requires grad, and this means we only want to count the parameters that is going to be trained. So when using all these pre-trained models, for example, so going up here. So when using these pre-trained models, what we do is we set requires grad to false. So this means that we will not be able to train these pre-trained models, but only these layers, for example, linear, that we define ourselves. So we do not want to train all of these pre-trained models as well, only the models that we are able to train. And this way we can actually estimate how many models we will be able to train, and then also how big the model is based on that. So let me just go ahead and say Python count parameters.py again, and just wait for this to finish. And we can see that we have about 313,000 trainable parameters. So if we didn't have this requires grad, then we would probably have many million of parameters, because that is how many parameters the pre-trained models do have. So if we just go ahead and do this again, let's just see how many parameters we now have. 142 million parameters. So the text encoder is suddenly over 100 million parameters, because this bird model, so birds, has all of these parameters that has been pre-trained for us. And all of these parameters we do not have to train, because we just froze the model with this code right here. But our model that will be trainable will therefore be much smaller, because we froze those. So having a model that is this big, so for example, if we didn't freeze all these pre-trained models, it would be way slower in training, like way slower. This is a magnitude larger in node counts. So that is why we disable training the pre-trained models as well. If you have too many parameters compared to how little data you might run the risk of overfitting your model. So that is why it's very important to know kind of how big your model is compared to how much data you have. And if you look online, there are all kinds of thumb rules for how many parameters you should have based on how many samples you have in your datasets. So you can check that out online. Otherwise, this was just a small helper script to help us determine how many parameters we do have, so you have an understanding of how big the model actually is. With everything in place, we are now able to create the script we can use to train the model. So under training, I'll create a new file called train.py. So inside this, let me just find it, models.py file, if we go all the way down, we have the multimodal trainer, where we can actually just call this train epoch to train the model. So we just need to do that and a couple of other things. So we'll be training on something called AWS SageMaker, like this. And SageMaker will allow us to train in a pretty simple way, and it's very powerful. So when we do upload our script to SageMaker to train the model, what it'll do is inject some environment variables into our script that we can use when training the model. So we'll just start out by getting those. So I'll go ahead and say sm model directory. So dir is OS, and we'll just need to say import OS like this. Now I can go ahead and say os.environment.get. And then I would like to get the following one right here. And then I would like to provide a default value that is just going to be the dot, so the current directory. Then I would like to get the channel training as well. So sm SageMaker channel training. And this is also going to be from SM channel training. And the default path to this should be OPT, machine learning, input, data, and then training like so. And then I can get the SM channel validation like this. And this will just be the following path right here. Now I can get the SageMaker channel testing. This will just be test like so. And this will be the following path, so test. We will also get a warning in SageMaker, maybe even an error, if we do not set this environment variable. So this is something I've done before when training. And the following environment variable we want to set is PyTorch, quota, allocate, and then conf. And we'll set this to expandable, segments is true, like so. So this just needs to be quota and not quota. So this should work fine now. Then I would like to create a method to pass arguments we'll receive from AWS. So this will be called pass args, like so. And here we'll say parser equals arg pass, and we'll just need to import args pass. So we can say import args pass like this. Dot, and then argument parser to create a new instance of that. Great. And lastly, we can just say parser.add argument. And the first thing we'll receive as an argument in the training script is going to be the number of epochs we will run. So we'll say the type is going to be an integer. And the default should just be 20 epochs. We'll then also say parser.add argument. And then we'll receive the batch size, which will be, we'll just set it to 16 as the default. Then we'll receive a learning rate. We'll just set this to 0.001 as the default. And this, because it is a decimal, we'll need to set this to a float. Then we'll need to define the data directories like so. And just spell it correctly. Directories. Great. And then I can say parser.add argument and train directory. So train directory is going to be a string, and the default value is going to be the value from up here. So SM channel training like this. Right under that, I'll add a validation directory. This will be SM channel validation. I'll then also add test directory, and this will be test like so. And next up, I would like to add the model directory. So where the model should be stored, and this is just going to be model directory. And this will be SM model dir. So we allow for both using environment variables. So for example, this one, AWS.environment.get, and then we get this SM model dir. And this is one that should be injected by SageMaker. If it is not injected, then we will just use this default value. So we have defined default values for all of these. And then we also allow for passing in arguments. So we have this pass args method. So you can pass in how many epochs, the batch size, and also the learning rate you want to use. And we have set default values for those. But additionally, you can also pass in these arguments right here, and they'll then override these environment variables or default to them if they are not specified in the arguments. So what we just need to do is go ahead and say return parser.passArgs like this. Great. Now let's just create a main method like so. And then go ahead and say if name equals main, then we just call the main method right like that. And then we do want to make sure to install FFMPEG. So I'll just make a comment of that. So install FFmpeg, because we'll need to do that to run it in SageMaker, because we have installed it on our local computer, but the SageMaker computers do not come with FFmpeg installed. So we'll need to make sure to install that before we can actually train the model. And the reason for that is that inside this melt dataset, we have this FFmpeg command that extracts the audio from the video. So that is very important. Now, what we can go ahead and do is just say print available backends. Audio backends like this. And then I would like to just say print string and then just import torch audio like this. And then I can say torch audio dot list available backends or audio backends, sorry, and then print that out. So this torch audio is what we use to extract the waveform from the audio files. So I can just go ahead and search for torch audio like this. And then you see after we extract this audio file from the video file, we go ahead and say torch audio.load the audio path, and then that'll extract the waveform and the sample rate for us. And remember how we needed to install a library for this to work because it said we got an error with a missing backend. So that is exactly the library we need to make sure actually is there on the instance. So for debugging purposes, we'll just print out available audio backends just to make sure that this won't fail without us knowing, because then it'll be even harder to debug. So I'll then say args equals parse args. So we'll then get all the environment variables or passed arguments from this method right here, which we can then use when training. Now I can say device equals torch. We'll just need to import torch too, like so. So I can say torch dot device, like so. Then I can say quota if torch dot quota dot is available, like so. So if we do have a GPU available, then we obviously want to use the GPU because it's way faster. Otherwise, we'll say else CPU. So we use a CUDA CPU or GPU if we have it available. Otherwise, we use the CPU. So the CPU is just a fallback. So when training on a local machine, for example, my computer do not have a GPU, but only a CPU. So this would fall back to CPU for my machine. And then we also want to track how much of the GPU's memory is used, such that we can up how much the batch size is in case that we do not utilize the full GPU memory. So we can go ahead and say track initial GPU memory if available, like so. And then we'll say if torch.cuda.is available, like that. Then we'll just print out initial GPU memory used, like this. And then I'll just go ahead and say torch.cuda.reset peak memory stats, like that. And then I'll say memory used equals torch.cuda.max memory allocated. And this will be in bytes. So I'll just go ahead and turn it into gigabytes. So 1024 to the third, and we'll divide by that. And this we can then insert into this formatted string right here. So we'll say memory used to F, and then we'll print it out in gigabytes like this. So now we print out how much memory we use with the GPU initially, and then we'll also keep doing this when training epochs. And now we need to prepare the data loaders from this melt dataset. So in here it says prepare data loaders, and we'll need to get out the train, def, and the test data loaders. So let's just go ahead and do that. So we already did that right here. So I can just take this and copy it. So right there, I'll just go ahead and call this prepare data loaders, and we'll need to import this method right here. And since we're in the same folder, we can just go ahead and remove this .training because melt dataset is in the same folder as train.py. So now we have that imported. And we just need to reference the correct paths. So I'll just start with train CSV, and I'll say os.path.join args.train directory with train send emo.csv. Then for train video, train video directory, it'll be args.train directory and train splits. So this will lead us to train and train splits right here. And the other one right above it will lead to train send emo. Now, next up, we'll need to do it for the def. So def CSV will be value directory, and then def send emo. So value directory will be this one, and def send emo will be the CSV file. So we'll say def video directory and point to def splits complete. Great. And next up, right beneath that, we can go ahead and do it for test. So test CSV, and then test video directory. And then we can go ahead and say batch size, and this will just be arguments.batch size like this. And now for debugging, let's just go ahead and print out the training CSV path. So I'll just go ahead and create a formatted string like this, and then say training CSV path. And I'll just start out with it being just a single quote, and then os.path.join. And I can then say args.train directory, and then train send emo.csv. And then right under that, now I just saved, so I'll just put 2 more of these in. Great. Then right under that, I'll just do the same. So I'll say print, and then training video directory. And I'll just put in the train directory along with train splits and just save that. Put in 2 more of these, like so. And now this should work. So this is just for debugging purposes, such that when we look through the logs, we can see if these are actually correct or not. Next up, we'll just take the model and instantiate that. So model equals multimodal sentiment model. And this we can just copy, go up here and say import. Or we can even say from models, just import this right here. And it needs to be multimodal, like so. Great. And now we can just transfer that to the device that we're actually working with. So up here, we chose this device, either the GPU, if it's available, otherwise the CPU. So we need to transfer both the model and also all the tensors to the same device as I explained earlier. So that is exactly what we're doing right here. Then we'll just instantiate the trainer as well. So the multimodal trainer. So right under this model, I'll go ahead and say trainer equals multimodal trainer. I'll pass in the model, then the train loader, like this, and then also the validation loader. So we have that from, this is going to be validation loader instead. So this is what the model needs to train, the training data and also the validation data. And then afterwards we can use the test data to test out the model. So as we're training, if the current validation loss is better than the last checkpoint or the last epoch, we'll then go ahead and save the model. And to keep track of this, we'll just create a new variable called best validation loss. This will be a float that is having the default value of infinite. And then we can just go ahead and create this metrics data dictionary as well. We'll store the train losses. This will just be an empty array, like so. We'll also store the validation losses, like so. And we'll then store the epochs lastly, like this. And this should obviously also be an empty array. And then now what we can do is just run through each epoch. So what we'll do is say for epoch in, and then what I want to do is just say range args.epochs, because this is a number we receive from the arguments. And this we can then loop through like this. And we can install this library to show us a progress bar down here in the terminal. So this will be tqdm. So I'll say pip install tqdm. And it is already installed, so that is great. So I can go ahead and just wrap this range in the loop with a tqdm, like so. And then we just need to import this as well. So I'll say import tqdm, hop all the way down, and then right after this range, I'll say description, and then epochs. And this will then give us a progress bar about where we are down in the terminal whenever we're running the training job. So inside this loop, the first thing we want to do is call trainer.train epoch, like so. So if I just press F12, we can see that this is what we use to train one single epoch and optimize the weights. This will then return something, it'll return a dictionary, and this will be called the training loss. So hopping back in and going all the way down, these will be all the losses, the total emotion and sentiment losses for this single epoch on the training data. We can then also say trainer.validate, or it is going to be evaluate. That's what we renamed it to. And the phase should then be validation, like this. So hopping into validate, it is going to be evaluate is going to be validate by default. So we'll actually just remove this argument right here, like so. And we also need to pass in the data loader. So this will just be training on training data, but we need to pass in the validation data, so the validation loader, to be able to evaluate it on evaluation data, on validation data. Right here we do not need any arguments, so that is perfect. And then under that we can just go ahead and say track metrics. We'll then say metrics data, train losses.append, and then we append the train loss, and I want to append the total, like so. I also want to append validation losses. So VAL losses, this should be VAL loss and not train loss. And this one is going to return validation loss and validation metrics, like so. So going into this, hopping all the way down, we'll have a loss and we'll have some metrics. So that is what we're going to call this, the loss and the metrics. And then we'll also just append the epoch. So I'll say epochs, and this will just be the epoch, like so. And up here, if we hover the epoch, it's just going to be any, but what it is going to be is just a number, because this will be a number which range will help us loop through. So going down, we can say log metrics in SageMaker format, like so. And then we'll just go ahead and say print json.dumps. So we just need to import JSON. So we'll say import JSON like that. And now we'll just print out all of this info as well. So it's both in the tensor logs, in the TensorBoard logs, as well as in the terminal. So let's go ahead and put in an object called this metrics. In here, we'll just put in an array of objects. The first object should be the following one. So I'll put in a name. The name should be train loss, like so. And the value should just be train loss total. I'll go ahead and copy that. Call this validation loss. So this one should just be val loss instead. Also total. The next one should have validation emotion precision. And this value should then be val metrics and then emotion precision. We'll then also want emotion accuracy, also right there. We'll take these two and copy these and call the first one sentiment precision, this one sentiment accuracy, and then just do the same over here. Great. And then for each epoch, I also want to track how much GPU memory I'm using. So that is just good to know to optimize how much GPU I am able to use, so by increasing the batch size, for example. So if the GPU is available, I'll go ahead and just say memory used and do the exact same calculation as before, and then just say peak GPU used, like this. And then under that, I'll say save best model. So this metric we used up here, the best val loss, we'll just use down here. So what I'll do is say if, and then I'll say validation loss. And then what I'll look for is total is less than the best validation loss. Then I can set the best validation loss to the new validation loss. So if the current epoch has a better model than the last model, then we'll just set the new loss to the best one. And then what I'll do is go ahead and save the model. So I can go ahead and say torch.save. And then I can go ahead and say model.state dictionary, like this. And then os.path.join, like this. And then I'll say args.model directory, because this is where we want to save the model to. So model dir. And then I'll say model path. So we'll append model path to the model directory, and this is where we will say save the model to if it's the best model. So this loop up here, this for loop, will loop through all the epochs and train the model. And then after training the model, we can then evaluate it on the test set as well. So to do this, we'll hop outside the loop. So right out here, and then we'll say after training is complete, then evaluate on test set. And then I can just print that out so we know it in the console as well when debugging, evaluating on test set, like this. And then I can say trainer.evaluate, and we'll pass in the test loader. And then this phase should just be test. So we'll just set the phase to test instead of being validate. And lastly, I can just go ahead and see what it returns. It's going to be test loss and test metrics, like this. So now we have the test loss and the test metrics. And we can just append that to this metrics data up here. So what I'll go ahead and do is just say metrics data, and then test loss equals test loss total. And now we can just print out an entire JSON directory like this again. So let me just go ahead and remove these values, except for the first one. And I would like to call this one test loss. The value should be test loss total, like so. Under that, I'll print out test emotion accuracy, like this. And this will then be test metrics. And then it should be emotion accuracy, exactly. And then what I'll want to print out now is the sentiment accuracy right there. And then I can just take these two and copy those. And then we can just do the same for precision. So instead of accuracy right here, I'll just put in precision. Like that, right there and right there. And that should then be it for printing out the metrics about the test run, so the evaluation on the test set. And I do see a small spelling error right here, so it should be precision and not precision accuracy like that. Great. So we still need to go up and install FFmpeg up here. And I also see one thing, I see it says parse arg. It should say parse arguments like this. So I'll just correct that spelling error. And then it actually also says learning rate right here instead of learning rate. So this should just be learning rate. So learning rate like that. The learning rate isn't used inside this code though, so it shouldn't really do any difference. Great. So we'll just need to create a little script for installing FFmpeg on the machine in the cloud, such that it also has FFmpeg available whenever it's supposed to extract the audio. So I'll go under training, say new file, call this install ffmpeg.py, like so. In here I'll start by importing subprocess. This is a command that lets us run code in the terminal on the computer we run the script on. So I'll say def install ffmpeg like this, and then what I'll do is just say print starting ffmpeg with a uppercase installation, like so, just in the log so we know that it is starting to install. Then I can go ahead and first of all say subprocess.checkCall. So checkCall will raise an error if the command fails to execute. So then I'll say system, so I'll just import system. Then I can go ahead and say system.executable. I can then put in -m pip install, and then I would like to just install pip first. So just remove this and then install, and then I would like to put in the upgrade flag like so, along with pip like this. So we'll just make sure that pip is upgraded before trying to install this library. We'll install in just a bit. Then I'll just go ahead and copy this line, and then down here I will just say setup tools instead of pip. Great. Now I can go ahead and try and install this library called FFmpeg with pip. So I'll say try, and then subprocess, and I'll just copy this entire thing right there. Remove one indent, and then I would like to say -m pip install and then FFmpeg. So I'll say FFmpeg Python like that, and then I can go ahead and say print installed FFmpeg Python successfully, just so we know that. Otherwise, we'll just go ahead and say accept. And then we'll just print out failed to install FFmpeg Python like that. And I'll just say via pip, just so we know that we try to install it via pip right here. And then under this, I'll go ahead and put in another try except. So inside the try, we'll first try and download the FFmpeg static build that you might have downloaded whenever you install FFmpeg on your local computer. So this is another way we can install it. We can then say subprocess.checkCall, like this, pass in the commands. So we'll use vget, and then we'll just pass in the following one. This is the UL to the static build, so this is the UL, and then /FFmpeg /releases, and then this release right here, FFmpeg release, and then AMD static, and then tar.xset like this. And we'll then clone this down to the following path, so we'll say -o, and then put it into the temp, and then FFmpeg temp folder, and then we'll say FFmpeg like this, .tar.exe in our local computer, exactly. And now that we have downloaded the static build of FFmpeg down to the cloud computer, we can go ahead and just extract the binary. So I'll say subprocess.checkCall, and then we can go ahead and extract it in the following way. We'll then just find the extracted directory. So I'll say results equals subprocess.run. And then I would like to put in the command, which is going to be find, and then the temp folder, and then the name is going to be FFmpeg. And then I would like to say type, so putting a type flag along with F right here. Then I can capture the output. So I'll set this to true and would like to capture it as text like this. Then I can say FFmpeg path equals results.standardout.strip like so. And now we have the path of where FFmpeg is installed. And we can then take this directory and copy it to the path variable. So I'll say subprocess.checkCall. And then I can go ahead and say cp, and then FFmpeg, like so, path, and we'll just copy where we extracted it to a place in path, and this means we can run FFmpeg from everywhere in the terminal. So if we open a terminal in one location, we can run FFmpeg, and if we open another terminal in another location, we can also run FFmpeg. So that is why we first extract it, and then we move it, so we copy it from wherever we extracted it to, and then all the way over to this user path. Now, what I can go ahead and do is just make this executable. So I'll say subprocess.checkCall, then I can say chmod, and then +x, and then we can reference this FFmpeg binary inside the path directory, and then it should be executable whenever we just say FFmpeg in the terminal. So now we can go ahead and say print installed static FFmpeg binary successfully, like this. And then for the except, because we did put it inside a try up here, we would like to catch the following, just exception, so just a journal exception, SE, and then we can go ahead and say print failed, and we'll just make it a formatted string actually, failed to install static FFmpeg, and then we'll just put in the error message right there. Great. Now we can just verify the FFmpeg installation as well. So I'll just put this inside a try, say results equals subprocess.run. We'll then just say FFmpeg, like so, along with the version. So this just corresponds to going to integrated terminal, saying FFmpeg minus version, and then we'll just get out the version of FFmpeg right here. Great. So that is what we would like to receive. Then I can say capture output true, text true, and then also check true like this. So this will just make sure that an error is going to be raised if this command fails. And then what we can go ahead and do is say print FFmpeg version, like so. And then we can do another print and just say results.stdout. And then if it does succeed, we'll just return true. Otherwise, we'll say except. And we would like to catch either subprocess.called process error or a file not found error, like so. And what we would like to do is just say print FFmpeg installation verification failed. Great. And then we'll just return false in this case, just so we know from where we call the script that it was not installed correctly, like that. So going back into the train.py, what we can then do is just remove this command and then say if not install FFMPEG, and we'll just need to import this from up here. So I'll go ahead and say, I'll just import it down under this one. So I'll say import FFMPEG and then, from install FFmpeg, import install FFmpeg, like so, because the script is called install FFmpeg, and so is the name of the method. And then what we can do is just scroll down and say if not install FFmpeg, then we'll say print error FFmpeg installation failed, cannot continue training, like this, because we do need FFmpeg for anything to work, because every time we pull out a sample, FFmpeg is used to extract the audio. Then we can just exit the training script by saying sys.exit, like so, and just put in 1. We'll just need to import system from up here, so I'll say import system, like so. So what this does is it says if not install FFmpeg, and when this is being evaluated, it will call this install FFmpeg command and then try to install FFmpeg. If it is installed, it'll then just say true, otherwise it will return false. And then if it returns false because it is not installed, it'll just exit the entire training script and stop the training. Good. To get started with the training, we'll go ahead and create a new file out here in the root folder. We'll say new file right there, call it train SageMaker, and then .py. In here, we'd just like to use a library called SageMaker. So I'll say pip install SageMaker, like so, and then just wait for that to finish. And then while doing that, we can go ahead and say from SageMaker, like so, and then .pytorch, and this should register in just a second. Maybe if I say SageMaker again. Let me just close down this one, close down the file, press save, go back. From SageMaker, great.pytorch, import, and then we'll say PyTorch. We'll then also just say from SageMaker.debugger, import TensorBoard output config, like this. What we can then do is say if name equals main, like so. What we'll then do is just call a new method, which I'll just create up here. So I'll say start training, and then just make that a method, like so. And then I can just copy start training and call it down here if I do run this file. Great. First of all, I would like to create a TensorBoard config instance. So I'll say TensorBoard config, and we'll create a new instance of this one. So I'll say TensorBoard output config, and I'll pass in an S3 output path. This will be a bucket. We do not have this bucket yet, so we'll just say bucket name for now, and then we'll say /TensorBoard, like so. We'll then also put in a container local output path. We'll then pass in the OPT machine learning, like this, and then output, and then TensorBoard, like so. We can go ahead and create something called a PyTorch estimator. So I'll say estimator equals PyTorch. This will define all the configurations for our training job. So I can say entry point. The entry point will be train.py. So the following file up here, train.py. We'll then say source directory, and that will be training. So the following folder. So inside the training folder, we'll have train.py, which we can use to run the training script. We can then just pass in a role with the sufficient permissions, and we'll create this role in just a bit. So I'll just say my new role for now. Then I can say framework version. I would like to use 2.5.1. Then Python version, and I would like to say Py 3.11. Then I can say instance counts, like this, and this should just be 1. I can then pass in instance type, like this as well, and this should be ml.g5.xlarge. So this will have a great graphics card for the price, which will be able to train super fast. Next of all, I would like to put in the hyperparameters, and the hyperparameters should be batch size, like so, and this will be 32 samples at a time, and then epochs, which should be 25. So we'll just run 25 epochs. Lastly, I'll just pass in the TensorBoard config, and this will just be equal to TensorBoard config like this. And with this configuration, we can go ahead and start the training. So I'll say start training, and then we can say estimator.fits, and then pass in the paths for the training sets, the validation set, and also the test set. So I'll say training, and then this is just going to be our bucket. So the same bucket as up here, for example, and then slash training. Then we'll just call this data set slash train. This one down here, I'll just call dataset slash def. And down here for the test, I would like to say test like so. And we'll then have an S3 bucket, so just a cloud storage service that stores our dataset, and we'll put that into 3 different folders, so train, def, and test. And whenever we run this training script on this instance right here, it'll pull down the dataset from the S3 bucket and then start training with that dataset. So before we start to train, let's set up all the infrastructure we need in AWS, such that we have the right roles with the right permissions, along with also the bucket that we need to be able to train. So here is a brief overview of how we are going to set up the infrastructure in the AWS. We'll use 4 different services. We'll use EC2, so this is a compute service where you can rent a cloud computer in the cloud, so in AWS. This is a storage service, S3, where you can have a bucket, so basically a file system on the cloud. This is SageMaker, so this is for doing AI related stuff, so for example training or hosting endpoints. And then we'll also use IAM, and this will be used to create users and also roles with the sufficient permissions to use all of the other things. So here is how it goes. First of all, we'll use this EC2 instance to create a new instance, and that instance in the cloud we can use to download the dataset directly from Melt into an S3 bucket. So instead of downloading the dataset to our local machine and then uploading from our local machine to S3, so this includes downloading 10 gigabytes and then uploading 10 gigabytes, and that is not good at all because it takes a long time. We'll go ahead and create an EC2 instance and then download this through AWS, so we'll keep the dataset inside the AWS environment and thereby use the super fast internet speeds that AWS has to offer, and thereby we can download the dataset almost directly to an S3 bucket. So that is what we're going to do. So we'll use an EC2 instance to download the dataset and put it into a bucket. Next up, we'll have this bucket right here. So this bucket will call something like sentiment analysis SaaS, for example. Inside this bucket, we'll have a file structure. This file structure will contain a dataset folder. Inside the dataset folder, we'll have def, test, and train, and these will each contain the CSV files we have in our local machine as well, along with a videos folders containing all the MP4 files. Next up, we'll also have something called the TensorBoard folder. So this is what we saw on our local machine for keeping all the log files related to TensorBoard. So when the training job is running, it'll put TensorBoard log files into this folder in the bucket right here. We'll then from the bucket need to set up some settings, for example some cause settings. So we'll set up some allowed origins, methods and headers, etc. So we'll be able to access this bucket from the front end later on, for example. Next up, we would like to use the SageMaker service. The SageMaker service will be used for a couple of things. First of all, we'll need to create a training job. So this training job is basically just like an EC2 instance, but it only runs for the duration that we do the training. So for a training job, you need to just upload some code, and this code will then run. So this is what we set up just a second ago. You then get to choose the instance type, which we did right here. And we chose an instance type. It should be ML, by the way. And this instance type right here will have a large graphic card, so it trains even faster. So when this training job is running, what we'll do is to get it to run, we'll upload the code by running this file called train SageMaker, which we just created on a local computer. This will upload the code to an S3 bucket, so probably not our S3 bucket, but another S3 bucket. And SageMaker will then create a Docker file from that code on the S3 bucket and run that Docker file. And when this is run, it is then called a training job. So the first thing it'll do after that is then pull the dataset from an S3 bucket, which we downloaded over here. So we have this dataset already inside AWS, and then we'll just download that down to our training job, and then the training job will run with the training data. When we then save the model inside the code during training, it'll then save that model file down to an S3 bucket such that we can use it later on when we want to run inference on the model through an endpoint, for example. And that is the second thing we'll use SageMaker for. So SageMaker will also be used for the endpoint functionality that it has, where you specify a script it can use to run inference. So it works kind of like a training job, where you have some local code that can be used to run inference. Then you run a script locally, which will upload it to SageMaker, and SageMaker will then handle all the logistics of creating an endpoint for running inference or with your model. So we'll use SageMaker for training and then also for running inference later on. Then we'll use the service IAM, and we'll use it for one or a couple of different things. First of all, we'll create some roles. So we'll need to create a front-end user whenever we want to invoke the endpoint. So when we do host our model, we'll need a user to be able to invoke the endpoint. So this just specifies which permissions we do have. We'll also need a role to deploy the model to an endpoint. So when we have finished our training, we can then run a script which will deploy our model over to SageMaker. And this role will need the sufficient permissions to deploy this model. We'll then also need to create another role which is able to, for example, access the S3 bucket over here. So this training job will assume this role whenever it does the training. So this role right here will need to have all the permissions that this training job is supposed to be able to do. So that is why I said with this role. So the training job will run with the role right here, and then we'll give it Amazon SageMaker full access to do all the things SageMaker needs to be able to do, as well as just give it access to an S3 bucket such that they can pull the dataset right here. So those are the three different things we need from IAM: one user, and then two different roles to be able to deploy and then also train the model. So what we can do after setting up all this infrastructure in AWS is the following. We'll be able to run a training job. So on a local machine, we can run the file train SageMaker.py. This will bundle up the training folder on a local machine and upload it to an S3 bucket. SageMaker will then build a Docker container from that S3 upload, which we just did automatically. And then train.py will be executed automatically inside the Docker container on SageMaker. And this will then be called a training job. When this Docker file has stopped running, it'll then also stop the training job, and you'll not get billed for any more compute power than that. Next up, what we would like to be able to do is just see the TensorBoard logs. So inside this Docker file, when it runs the training script, it'll create a bunch of different logs, and these will be the TensorBoard logs, which we can use to see if the model is performing well. So maybe it's overfitting or underfitting, and we can see that from the TensorBoard logs. So on a local machine, we can run a command to clone these logs down from S3 to our local machine, and then we can run TensorBoard, which is just the pip library we installed, and point the dir or the directory to the folder which we just downloaded the logs to, and then we'll be able to see the TensorBoard logs from this training script which we was just running over here. So that is what we'll set up and also what we'll use it for. And with this basic architecture in mind, we'll be able to go into AWS and just set that up right now. So let's just press a new tab right here and then say AWS console. We can then hop over to login and then just log in with our AWS account. So I'll just say sign in with root user email and then just log in. I am now logged in, and first I would like you to go to service quotas right here. Under service quotas, I would like you to search for SageMaker, and we'll need to apply for an account level increase for the specific instances we'll need for training and also for hosting the endpoint. So we'll be using the model ml.g5.xlarge, and we'll need to increase that for both training job usage right here. So you can press the following button and press request increase at account level. Just put in 1 as the quota value and press request, and it should be granted immediately. This means we'll be able to train with a single instance at a time. The same you'll need to do for endpoint usage, so this we'll need for hosting. So you can press the following one right here, ml.g5.xlarge for endpoint usage. We can then as well say 1 right here, and then press request. I have already done that, and I actually have 2 right here. So I am already fit for this, so we can go ahead and go to the next part. So let's search for S3 up here. Then press the following service, and then go ahead and press create bucket right here. What we can then do is create a new bucket under general purpose and go to bucket name. You can call the bucket name something like sentiment, analysis, SaaS. What the exact name is doesn't really matter that much, but it's just something like this that you will remember. We'll then just leave this as it is and then also block all public access. We can then scroll down and press create bucket. And then under this bucket, sentiment analysis SaaS, we'll hop in and press create folder. Under folder, we'll call this Dataset, like so, and then press create folder. Then we'll just leave this as it is for now. We'll also just press create folder as it is as well, and then say TensorBoard, and then just create that folder too. Now I would like to go to permissions and then scroll down to cross-origin resource sharing right here, and then say edit. So the frontend should be able to upload video files to this bucket, which we should be able to run inference on. And to do that, we'll need to enable the frontend to be able to interact with the bucket through the API. So we'll put in this new configuration. So I'll go ahead and put in a square bracket and then a curly bracket like this. And then first of all, say allowed headers. We'll then say all for now. So just put in a star. So under allowed headers, we'll just go ahead and say allowed methods as well. So this will be allowed methods. This should then be another array, and we'll say puts, posts, and get. We can then also say allowed origins right under that. So allowed origins, and we'll just put in the following one, so just a star, and that will just allow everything. We can then also put in expose headers like this, and then just put in a empty array. We can then go ahead and say save changes, and now we should see it being updated down here. I'll then hop into IAM, so I'll say IAM and pick that service. Under roles, we can see that an IAM role is an identity you can create that has specific permissions with credentials that are valid for short durations. Then we can say create role. And we can go ahead and say SageMaker. So I'll just search for SageMaker and then press next, next again. And we'll call this something like sentiment analysis execution role, like so. And then just go ahead and press create role down here. So what I just want to explain is the trust policy. So SageMaker, so the training job, will be able to assume this role. So all the permissions we give the role, SageMaker or the SageMaker training job will be able to do. So that is just what we do with this role right here. Then I can go ahead and say create role. And when it has been created, we'll just go to the second page, find the role down here. Then we can go ahead and say add permissions. So we'll just need to give it permission to read and also to do some interactions with the S3 bucket so we can pull the dataset. So I'll say attach policies and then hop into S3. Actually, I'll just say create inline policy and then search for S3. I would like to use the policy get object like so. And we can then just give it create, read, update, and delete access. So we'll just say get object and then delete object like so. We'll then also say put object like this. And then lastly, we'll say list object, list bucket like this. And then we'll do this for only specific buckets. So if I just go over here and search for S3, hold down command and press this one, we'll just open it in a new tab. We can then go ahead and find our bucket. So this will be the sentiment analysis SaaS. Then we can go under properties, I think it is. Copy this ARN, so that is the Amazon resource name. So all resources in AWS have its own specific ID, and this will be the following one. And if we then go back to the create policy tab, we can then specify that this is the only bucket we'll be able to use this for. So I'll then say add ARNs, and then go to the resource ARN and just press add ARNs like this. And for the objects, it should just be any for now. We should just be able to do this with any object. So going ahead with that, I can say next, and the policy name I'll just call X or maybe sentiment analysis execution S3 policy, something like that. And then I'll say create policy and just wait for that to finish. If I then just go ahead and press this right here, we see that it says modify permissions. And then we do see under resource that it actually has access to all buckets. And that is not what we want. So let me just go ahead and delete this line right here. And then let's just remove this comma too. Then press next. And now we should be able to press save changes like this. So that was the role for creating the training jobs. Now we just need the role for actually deploying the endpoint, which will host our finished and trained model. So I'll just go ahead and close this right here. I'll just copy this role name, go back under roles, say create role, and I'll then say SageMaker again, hop over to next, and next again, paste in this role name, and I'll just say endpoint, deploy, or just deploy endpoint role like this, and then go ahead and say create role. Under the role, if I just go to page 2, so deploy endpoint role, I can just say add permission, attach policies. Then I would like to attach CloudWatch, logs, full access like this, add permissions. Then I would like to also create an inline policy. This should be for an S3 bucket. So what I'll actually do is hop back to continue, find the role we created before, so the SaaS or execution role right there, hop over to this inline policy we created, and just copy this entire policy, hop over to cancel, press continue, go back, and then I'll just pick this role again. So the deploy endpoint role, add permission, create inline policy, and then I can just take this JSON and paste this straight in like this. So now we'll give it the same CRUD permissions for exactly this bucket right here. So put, get, list, and delete for only this one bucket. And then this should narrow in how much permissions it has, such that it can't, for example, ruin the other buckets if it was hacked. So then I'll say next. The policy name will just go ahead and let me just see what we called these other ones. So this one was this policy. And this policy we'll just call deploy endpoint S3 policy, like so. What I can then do is say create policy. And now we have access to SageMaker, we have access to logging in CloudWatch, and we have access to S3 via this custom policy we have made that narrows it down to only the bucket that is relevant to this role. Great. Going back to roles, and then scrolling up and pressing users, we can then go ahead and create a user for the front end. I actually think we'll wait with this one because we need to specify the endpoint that this user is able to invoke, and we do not have this endpoint yet because we haven't even trained the model. So that is why we'll wait with this user right here. So now we have the different users up and running, and we should be able to go back to the code and just specify these roles right here. So they're ARNs. So we can take the execution role, for example, and we'll need to just specify this one in the code for it to work when we train the model. So first of all, we need to specify the execution role right here for the training. So this will be the sentiment analysis execution role. So we can go ahead and take the ARN from that. So copy this one and paste it in instead of my new role. And then second of all, we would like to just put in the correct bucket name as well. So hopping over to S3, just searching for that service, we should be able to find the sentiment analysis SaaS bucket right here. Go to properties and then copy that ARN. And here we'll actually only need the name. So I'll just go ahead and under S3 output path, say S3 and then this colon, and then go like this, two forward slashes, then say sentiment analysis SaaS like this, and then slash TensorBoard. So now I can just take this one, copy it down to right there, and then also right there. And then we should have all the default placeholders out of the way. We have the role as well as the bucket. But before we can run this train SageMaker script and actually run the training job on AWS, you'll need to set up the AWS CLI. So I already have it installed on my machine. So if I say AWS, then this should be a command I should be able to run. So I can say AWS, and then I have a full CLI to use to interact with AWS. So you can go ahead and search for AWS CLI installation. If you do not have it installed, then you can go ahead and say installing or upgrading to the latest version of the AWS CLI. and then install it according to your local machine or operating system. After you have installed it, you can say AWS configure, and this should be, and run this command, and this should be able to let you a region like this, so North Virginia for example, as well as an access ID and also a secret access ID. And these two you can get from either creating an IAM user if you want to, and then under IAM, if you create a new user, I'll just take this one for example, you can then say create access key, so this will then be the access key, and then you should also be able to get the secret key when creating the access key. This will only let you be able to interact with the CLI with the things you have given yourself permission to. What you can also do, which is a little bit more risky, but that is what I do, is press over here. And then you can see a drop down that says security settings or something. And from there you can get the access key and also the secret access ID from the root user. And you can then just use that in the CLI. So that is completely up to you. But either way, you'll need to set up AWS CLI on your computer to continue from now on. So if I hop over to SageMaker like this, and then I go under training on the left side, and then training jobs. I do already have a bunch of training jobs from playing around with training models. So these are all training jobs, but we would like to create one of these, and this should be done by running the following command over here. So I have opened up a new terminal, so I'll just say open an integrated terminal, and then we have this SageMaker.py script. So let's go ahead and say Python, and then train SageMaker.py like this, and just press enter. And then what we should see is the following right here. It'll spit out a bunch of things for us, such as this one, found credentials, and now it seems like it failed. So let's just go ahead and see what it's saying. Scrolling all the way down, an error occurred. No S3 objects are found under the S3 URL. And that is because we forgot to download the dataset to the S3 bucket and then extract the tarball to the train, dev, and also test folders. So let's just go ahead and do that now. So I have just navigated to our bucket, sentiment analysis SaaS, and then I went to the folder dataset. And as you can see, it is empty. So we need the folders dev, train, and test. And we'll just extract these directly from the tarball on the EC2 instance, and then go ahead and upload those to this bucket right here. So let's first go to IAM, and we'll create a role that the EC2 instance can assume. So I'll press roles, create role, and I would like to say EC2 right here, like this. And then I'll just say next. And then for permissions, I'll say S3 full access, like so. And this means our EC2 instance will be able to upload the folders to the S3 bucket. So we'll then press next and just call this EC2 upload role, like so. And then we can just go ahead and create the role. Now I'll then search for EC2, press right there. Then I would like to say launch instance. This instance I'll just call sentiment analysis dataset instance, like so. I'll just select Amazon Linux. For the instance type, the smaller instance you go with, the slower the extraction of the tarball file, so the dataset will be, but the cheaper it will also be. So you can just go ahead and take the T2 micro if you want. It will take a long time to extract these things though, but it is free tier eligible, so you can do that if you want to. I'll just select T2.xlarge because it is a lot faster. Then for the key pair, we will say create a new key pair. We'll then just say sentiment analysis and then key pair. I'll just call this dataset as well. And then just select these options and press create key pair. And this has now been selected and downloaded to our machine. Going further down under configure storage, the dataset will be about 10 gigabytes and we'll also extract it, which means it'll be duplicate. I'll just go ahead and say 50 gigabytes just to be sure, but you can go with less if you know exactly how much space you're going to take up. So now we should be all good, and I can go and say launch instance like this and just wait for this to launch. And now that it has launched, we can say view all instances and then just go ahead and wait for the instance to start up. Right now it is pending and now it is running. So the first thing I'll do is just highlight this instance right here and then say actions, security, and then modify IAM role. And for the IAM role, I'll just say easy to upload role like so and press update IAM role. Next up, we can go ahead and select this one again and say connect. And then we can say connect right there. And the connection will be established. So the first thing I would like to do is just check how much storage space we have. So I'll say df -h like so and just press enter. And we have the 50 gigabytes right here in root is exactly like we configured. So that is perfect. So then I'll go to ahead and search for the meld dataset. I'll then copy this Hugging Face link right here. So copy the entire thing, hop back over here, and then just paste this in and press enter. This will then download the dataset down to the EC2 machine. And when it is finished, I'll just come back to you. So now we are done downloading and I can go ahead and say ls. So we can see that we have downloaded the dataset down to our local system in the root folder. So that is great. The next thing I would like to do is just extract this tarball. So I'll say tar-xzf and then put in this following one. So I'll just copy this, paste it in, and then just extract it like so. And when it's done extracting, I'll just come back to you. So it took about a minute, but now it has been extracted. So I'll just say ls again, and we can see that we have the tarball and we have the extracted directory right here. We can then create the folders for def, train, and test. So I'll say make directory and then def. I'll also say make directory, train, make directory, and test like so. If I press ls, we can then see the directories def, test, and train. If I say ls meld.raw, we can see the contents of this folder right here. So we can see that we have the def CSV file and the test training set, which is also a tarball we need to extract. We only have one tarball for the train and not the CSV file. That will be inside this tarball. We'll then have a CSV file for the test and also that tarball. So we'll need to move the def and def into this folder, test and test into this folder, and then train into this folder. And then inside those folders, we can extract them individually. So I'll say move and then meld.raw like so, /def sense. So I'll just copy this. So I'll just go ahead and do that. And then we can specify where we move it to. So this is where we move it from. And the second parameter will then be def, so where we move it to. We can then just do the same thing for the other thing we want to move. So the tarball right here. So I'll just replace this CSV file with the tarball. And now we move that. Then we can just do the same for train. So I'll just say train and we'll move that to the train folder. And for test, I'll go ahead and just remove this, copy in the CSV file, say test right there, and then just move the tarball as well, like so. If I then say ls meld.raw, we can see that we only have the readme left and all the other files have been moved, so that is perfect. We can then say ls def, and now we can see we have the def.tarball and then also the CSV file. We can then say ls train like so, and then we can say ls test. So we have now verified that we have all the correct files inside the correct folders as well. Now I would like to just extract these tarballs inside these individual folders. So what I would like to do is just say tar -xzf, and then I would like to extract the development one first. So I'll hop into the development folder like so. So tarball and then extract def/def.tar.gz, and we would like to extract that to the def folder. So I'll just say -c like so. So we have def and then the tarball. Let me just see that it matches, and it does. And then -c and then to the def folder. So after extracting, I'll just come back to you. And now that that has been extracted, we can just do the same for train. So I'll just replace this with train and then just copy the train tarball like this and just say train for the folder as well. So train. And now I should be able to just press enter and wait for that to finish as well. And now that the train folder has been, or tarball has been extracted, we can just do the same for test. So I'll just say test right there, and test, and also test like so. And then just press enter again, and just wait for that to finish. And now that that has been done, we can go ahead and just check the contents of each of these folders. So I'll say ls-dev, ls-train, and then ls-test like so. So we have the tarballs, which we'll just need to delete, but otherwise we have the file structures we want. We have the CSV file along with the folders with the movies or the MP4 files. So we can actually just go ahead and say ls-dev, and then dev tree, that's complete, and then we should be able to see all of these clips. So that will contain a lot of clips. So we just need to delete these tarballs now. So the way I'll do this is just saying remove, and then dev, and then I would like to say dev.tar.gz like so. We can just do the same for train. And we can do the same for test as well. Like so. And if I then just say ls-dev, ls-train, and ls-test, we see that we have the test and train and dev structure we want inside these folders. So now that we have the structure we want, we can go ahead and just upload these to our S3 bucket. So the way we'll do this is by saying AWS S3 CP -- recursive, like so. And then we'll upload the dev folder to a bucket in S3 called sentiment analysis SaaS, which is the bucket we created. And then we'll upload it to Dataset under a folder called dev. So this looks perfect. So I'll just press enter and wait for this to upload. So you can see the progress bar right here, and I'll just come back when this has been uploaded. So we have now uploaded the dev folder, and I'll just go ahead and upload the train folder. This will take a while since it contains way more files. So I'll just replace dev with train. So now we just say train right here, and then we point to the train folder inside the bucket as well. So let me just press enter and wait for that to finish. Now we are done uploading the training dataset, and we'll just upload the test training set, which is the last one. So I'll just say test and test right here. So that should be perfect, and I'll just press enter and wait for that to finish as well. Now we have uploaded this dataset as well. So we can just go ahead and go to the other tab, search for S3. I'll just open this in a new tab. Find my bucket, sentiment analysis SaaS, go under dataset, and then under dev, I should be able to see the CSV file along with all the video files which we have just uploaded. The same for test. We see the CSV file along with all these video files. And let me just check train as well, CSV file and all the video files. So that is just perfect. Now I'll just go over to this instance connect and just press this close button. Over here, I'll just say instance states and then stop instance and then just stop. And then I'll just wait for it to stop. Now the instance is stopped and I can just select it again, press instance state and say terminate/delete the instance. So I'll just do that. This will delete the entire instance since we do not need it anymore. And this way we can save the money. So be sure that you actually shut down and terminate your instances, because otherwise they'll cost you some amount per hour, and that is just stupid money to spend. So always terminate your instances when you're done using them. If I just go ahead and refresh over here, it still says terminated, so that is all good now. Alright, so I've opened up the code on the left side and then AWS on the right side. And then I would like you to go ahead and go to SageMaker. So SageMaker AI is the one I would like you to go to. Then you should go down to training and then training jobs. And then we should be able to see all the training jobs again. And remember how it failed last time? Well, now we can at least try again and see if it can find the dataset or not. So I'll say Python train SageMaker.py, run that. And then we can just see what output it gives us. So I'll just wait for this to output something. So now it says starting the training job. So we can start by scrolling up and just see whatever it gives us. So it finds the credentials in our AWS credentials file. So this is what you'll get whenever you say AWS configure. So this will fill out the AWS configure file, and then you'll be able to use the CLI. And then it uploaded these files over here from training, and then it should start the train.py file whenever it is ready. First of all though, it'll need to just create the Docker file which it'll run. So it started the training job, now it is preparing the instances for training. And then what it should do after that is probably download the dataset, and it'll do this all automatically because SageMaker AI does this automatically in training jobs. And that is the power of running a training job over just renting an EC2 instance, for example. You'll be able to just submit a single job, and SageMaker AI will then take care of everything for you and just shut down the instance when it is done. Now it is downloading the input data right now, so this is a good sign as well. And we can also over here see that it says in progress for this training job, which just popped up. So if it hasn't popped up at your screen, you can just go ahead and press refresh. So we see that it failed. So let's just go ahead and see what it says in a minute when it tells us it failed. So training job failed. So as we see, it says unexpected status exception, error for training job. And then the data download failed to download data, access denied. So apparently this user, so our role which we created, is not authorized to perform this s3get object on the resource. And the resource is a specific MP4 file. So let's just go ahead and head to IAM over here. So I'll just say IAM, just open that in a new tab. And then I'll just find my role. So this will be on page 2. And then the sentiment analysis execution role. In here, I'll just pick out this policy, which we created for S3. And then what we can see is we are able to access the buckets, but we're actually not able to access the bucket items. So I'll just go ahead and put in a star like this, which will allow us to do all of these actions on the specific items. So get object, for example, on specific items, which it couldn't right here. So if I go ahead and save this, and then save changes, we can then try again and just see what happens. So I'll just run this command again, hop back to SageMaker, and then we can just see what happens in a second. Alright, so returning back, now it has actually downloaded the input data. So what we just did over here actually fixed the error. So I'll just go ahead and close down these tabs. And now it is downloading the training image. So this is probably the Docker image which it has built to run the training job. So when this is succeeded, I'll just return back to you and then see what the output will be. Alright, so we just got an error. So scrolling all the way up, let's just see what happened. So it ran through a bunch of code and then printed this out. So first it downloaded the input data, it downloaded the training image, and then it started training actually. So it is the code that fails now. Scrolling all the way down, we can see module not found error, no module named transformers. So if you see this error, you can see that we are importing transformers somewhere. So in the melt dataset, this package is not being installed correctly. And then what we should do about this is a very important thing which we forgot. So when this Docker image is being built, which it will run as the training job, it will install all the packages from a file called requirements.txt, like this. So this requirements.txt file will then contain all the requirements the Docker file should install for our script to work. And we actually forgot to just specify this. So I have specified it. So we'll go ahead and say torch equals 2.5.1. And then you can say torch audio equals 2.5.1. And we will also need torch vision. So these are just all the packages which we have pip installed, because it'll also need to pip install this before the training script will work. We'll say 0.20.1. To check your current versions, you can go ahead and say pip show down here in the terminal and then say torch, for example. Then if you scroll up, you should be able to see the version that you use for torch, and then just pick that version whenever you want to install that package. Then we'll need transformers, like so. We'll use 4.46.3. Then we'll need to install pandas. For pandas, we'll need 2.2.3. Then TQDM, so this was for the progress bar. We'll need 4.65.0. For Boto 3, you'll need 1.35.76. Then for Open cv python. We'll just need 4.10.0.84 like this, and then we'll need SageMaker. SageMaker is going to be 2.237.0, then sound file, which is the backend for Torch audio. We'll be needing 0.12.1, and then TensorBoard. We'll be needing 2.18.0, and then scikit metrics for calculating the accuracy and precision of our model. We'll just need 0.1.0 like this. So make sure that you have all the packages that you use throughout your script. So everything you import up here and that you have pip installed, you should go ahead and add inside this requirements if you are going to use it inside the training job. Now we should be all good now. So let me just go and open up an integrated terminal and just run this script again. And then I'll come back whenever we encounter an error so we can fix that, or whenever it works successfully. So just refreshing over here, we see that this one is in progress, and then I'll come back when it is ready. So it just finished downloading the training image, and as we can see, it is running all this code now. So it has downloaded the packages, so downloaded TQDM, which was one of the packages in the requirements right here. So it is actually downloading the libraries which it is supposed to download. Then scrolling all the way down, we can just see that it is downloading FFMPEG right now. So hopping over to install FFmpeg, that is what we defined in this file right here. And then we can just see it throws an error right here. Type error module object is not callable. Otherwise it actually downloaded FFmpeg as it was supposed to. It also printed out the dataset sizes. So we did this right here inside models. So it reached this far in the code. So it actually went into the multimodal trainer and then printed out this before failing. So let's just check out why it is failing right now. Alright, so I just tracked down the error and this is the reason. So if I scroll up a little bit, we should be able to see exactly what the error is. So up here, we can see that we have a specific error message. So we got the Python error message, and that is gives us an error right here. And it says type error module object is not callable. So this TQDM is a module. So if I go to train.py, which is says the error is located in, and scroll all the way up to TQDM, we should be able to see right here that this is a module, and we just import this module. So right now we're trying to call a module, but that is not how it works. We will need to say from TQDM import TQDM like this, and now we are no longer calling the module. We are calling the class, which should be callable like this, and this should fix the error. So let me just try and run it again, and then come back when it is ready. So we just got this error right here, text inputs, key error. So scrolling all the way up, we can locate the error. So inside the train.py, where this code is being called, and that is inside models.py right here. We can just go ahead and search for this, and that is exactly right there. So right here we say text inputs, and that is also how we define it. But what we do right here is actually say text input instead of text inputs, and that is not how we can grab these key values from the batch. We need to say text inputs instead of text input. So we define text inputs in the melt dataset right here when we return it. So we need to, of course, also say text inputs here. So that was just a small spelling error. So I'll just try and run it again. Now it looks like it succeeded. So what we can do is just close down this, scroll up, and just see what the outputs are. So we can see that it started the code. It ran through all the code. It printed out the debug, things such as available audio backends, which we printed out ourselves, along with initial GPU memory used, the training CSV, there should be CSV, not DSV path. It also printed out the dataset sizes. So we have about 10,000 training samples, and then about 1,000 validation samples, meaning we'll put through 313 batches per epoch. And then we have this epochs progress bar right here. So this was the error we had just a second ago. So if I search for TQDM and just find it right here, this is what creates the progress bar. So we can see how the description is epochs, which we see right here. And then we go from 0%, and then all the way up to args.epoch, which is how many epochs we'll pass in. And we are passing in 25 epochs for now. So this progress bar will then progress as the model trains. If we then go over here and just refresh, we should be able to see the training in progress like we are right here. So you can actually keep this terminal running, and it'll just keep running and putting all the logs from the training process down to your local machine. But what you can also do to check the logs is select the training job over here, scroll down and find view logs. And then because we gave it access to CloudWatch, we should be able to see the log stream. So we can just click this one that has been selected for us, and we can see all of these logs stored persistently. So you can always see the logs from your training runs. And this will then also be updated. If you wanted to update in real time, you can just press resume right here, and it'll also retry and fetch the logs just like we see down here in real time. Great. So now you know how to start a training job and also check the logs. And then as you have seen, we have debugged a couple of errors. And this should also give you a pretty good basis for how to approach debugging errors. So what we basically do is if we see an error occur, we scroll up to where the code has been executed. Then we find that error inside the code by search and replace or something like that. We then fix the code and just restart the training job to see if it works now. So for this model, it will run on this ml.g5.xlarge for about 13 hours. So I've ran different types of this model before. So it takes about 13 hours to run 25 epochs. So that is what you should expect for a run. It's just so you know it. And this ml.g5.xlarge model is about $1.4 US per hour, which means that a training run will cost something in the likes of $18 US to train the model. So that is what a single training run will cost you, just so you know it. Now, before moving on, I quickly want to tell you something, just so you don't waste your money. So I just closed down the training run, so I closed down the terminal and stopped the training job. I did that by clicking the following button right here, then actions, and then stop. This stopped the training run pretty quickly. So one thing we need to do is to fix the error inside the model. And inside the model inside the dataset, there is a massive over-representation of the neutral labels. So if I just search for neutral like this, we can just find, I just need to put it in a quote maybe like this. How I referenced in the code, yeah, exactly. So this is what I wanted to show you. So we see all these different labels, and then because there is a massive overrepresentation of neutral sentiments and emotions, the model will learn to predict neutral most of the times because that will make the model correct. So it'll learn that it should just predict neutral because that will make it correct in the most of the cases, instead of actually trying to predict some of these other ones. So we'll get an error where it just predicts neutral every single time. And just the difference between the model with this imbalance fixed and without this fix implemented, I'll just show you after telling you about this. But just so you know that you should stop the training run and so we can just fix this error before we move on. So to fix this error, what we can do is compute some weights for each of these classes, and these weights can then be used inside the loss function. So what we would like to do is for the neutral to weigh a little bit less than negative and positive, for example. So we'll assign weights to each of these classes depending on how many samples there actually are inside the training dataset. So this will ensure that the model pays more attention to underrepresented classes during training, so we avoid this class imbalance. So here's how we can make this fix. I want to go under models, and then I'll just hop under the forward function up here. So that is just going to be right over multimodal trainer, right under this forward function. Then I would like to create a new method called compute class weights. And we'll actually just move this right over the trainer, the multimodal trainer, because we'll use it right down here in the loss functions. So what I would like to do is just create this new method like so and call it compute class weights. We'll pass in a data set, which we can use to compute these weights. So I'll say emotion counts equals torch.zeros. So we'll make it's a tensor for emotions, and we have 7 different emotion labels. We would like to do the same for sentiment counts, which will also just be zeros because we have neutral, positive, and negative. We can then say skipped equals 0 and total equals the length of the dataset, like so. What I can then do is say print, just so we know it for debugging purposes in the logs, counting class distributions, like so. And then what I would like to do is just run through all the samples. So I can say for I in range total. And then I'll say sample and just grab the sample from the dataset. And then after this, we can just fetch the label for the emotion and also the label for the sentiment. And then we'll just like to skip the samples that are none. So if a sample is none, we'll count up skip by 1 and just continue. So we'll skip that. And then if it is not skipped, what we'll go ahead and do is just take the label and use that as the key, so the index for the emotion, and then we'll count up that key with 1. This means we'll have a key for each emotion, so a key for neutral, for example, and that'll have an amount of counts, and those counts we can use to create the class weights. So after looping through all the samples and doing this, we can say valid equals total minus skipped, and then we can just say print skip samples and go ahead and do this. Now we can just say print, and then I'll just make a new line again and say class distribution, like so. Let me just remove this line. Great. Under this, I'll just say print emotions, like this. Right under that, I'll say emotion map, and I'll say 0 is anger, and then I have 1 is disgust, 2 is fear, 3 is joy, and then 4 is neutral, sadness, and surprise. Great. And then I can say for index and then counts in enumerate, and then I would like to enumerate the emotion counts. What I can then do is just print out the emotion map with the index. That means which label it actually is. So if we have 0 right here, it'll print out anger. And then we also print out how many we have. Now we can just go ahead and do the same for sentiments. So I'll say print sentiments, and then we can just make the sentiment map as well. So we'll have negative, neutral, and positive. We'll just go ahead and enumerate it the exact same way and print it out the exact same way as well. Now, this is just for logging purposes, but now we can actually go ahead and calculate the weights. So I'll say calculate class weights. Right here, I'll say emotion weights equals, and then it is going to be 1.0 to make it a float, and then divided by emotion counts. The sentiment weights will also be 1.0 divided by sentiment counts. Now we can go ahead and normalize the weights like this. So I'll say emotion weights is equal to emotion weights divided by emotion weights.sum, and the same for the sentiments. Great. Now I can just return the emotion weights and the sentiment weights, and we can now take the output of this, or what it returns, this compute class weights method, and then use it down here. So what I'll do is hop down to right under this current train loss equals none, and then just say calculate class weights. Then we can just print out calculating class weights as well and say compute class weights, and then just pass in the train loader, the dataset. So we would like to compute these weights for the training dataset only. And then we'll set this equal to emotion weights and also sentiment weights, like this. And then just go ahead and save. Now we can just go ahead and move these weights to the device we're currently on. So either the CPU or the GPU. So I'll say self.emotion weights equals emotion weights, like so, and then dot to device. So we have a device which we're currently using, like this. And this device will just figure out from the models. So we'll say next model parameters.device. So we have the model up here, and we'll just figure out where that is stored. So which device it is stored on. We can just move the sentiment weights as well. So this will be sentiment weights, which will also move to the device and store as an instance variable inside the class. Now let me just print out some more logging. So I'll say emotion waits on device. And this I'll just format like so. And then say self.emotion wait.device. And I'll just make an S with this one, so spelled correctly. And then I'll do the exact same for sentiment. Sentiment waits on device. Just to make sure that it is actually on the device we want it to be on. Now we have the weights calculated and we can use them down here in the loss function. So I'll go ahead and say weights equals self.emotion weights like this. And then for the sentiment, I would like to say weights equals self.sentiment weights. And the loss function should now take care of balancing out this class imbalance issue because we assigned weights to each of the classes. So if there is a massive overbalance in neutral right here, it should make sure to punish that even more and then overrepresent negative, for example, if that is underrepresented. So that is what we'll do with computing these class weights. And again, the problem we are trying to solve is the class imbalance. So if we have a lot of neutral, for example, the model will be more likely to predict neutral. And then if there are too many neutrals, so a lot of neutrals, like way more than the others, then it might never guess surprise, for example, because it hasn't seen surprise more than a couple of times. So that is the problem we were trying to fix. Now what we can do is just go ahead and open up an integrated terminal again. And then you should be able to run the training script. So I'll just save. And then just press the arrow up right here a couple of times until I see Python train SageMaker.py and just run the script again. And now it should spend some time initially before actually training, calculating these class weights. And then when this has been done, it'll automatically start training and you'll see the progress bar again. And then it should just train after that and fix this class imbalance problem. So now in this training job, we have surpassed the step of computing the class weights. So as you see, we still see the dataset sizes right here. Then we see the printout calculating class weights, counting class distributions. And then we see this error right here, but that does not matter because inside the data loader, we skip all of these samples that have an error inside of them. So that does not matter. So we skipped a single sample, so that is completely fine. Now we see this class distribution printout, and under that we can see the different class weights. So for anger 0.11, and it's generally pretty low, but once we reach neutral we see 0.47. so this is way higher than like the second largest one, 0.17. so this is what I mean by this massive class imbalance with neutral. We see the same for sentiments. So here neutral is again 0.47, whereas the second largest one is 0.29. So if we just let the model work with this without the class weights, it'll just learn that the neutral is the most used one, and then start to way more frequently guess neutral, and then never guess any of these other ones. So that is what we wanted to avoid. Great. So now that these class weights has been calculated and printed out, it then set emotion weights on device, sentiment weights on device, and these are both on a graphics card. So this is why you see CUDA. And they are on the first graphics card. That is why we see the index 0 right here. And then what we can then see is epochs. So now it has started the training process. So we see epochs and then 0%. So right now we haven't trained for a single epoch yet, but it is training right now because we see this error again. So for every epoch, it'll run through every sample. And then as we saw up here, when it ran through this sample, we got the same error. So it's probably even for the same video clip. Yeah, dia 125, odds 3, that is the exact same down here. So this is the video clip that gives the error. It doesn't really matter though, but we do know that it is training because it is going through these different samples and then actually producing these errors. So that is nice. So now that we know that it is training like it is supposed to, what you can do is you can keep it running. So just leave it as it is and it'll run for about 13 hours like so. I have previously completed training runs, and those ran for about 13 hours with the current setup, with the current model, and the current data set. So that is what you should expect this training to take. And then what I'm going to do is just stop this training because I've done this exact training before actually. So I'll just press this trash button right here, hop in and refresh the page. And then I'll just press this one or select this one that is called in progress, actions and stop. And this will then stop the training job. So you can actually both see the logs down here, but if you go under the training job and then all the way down, then you can press view logs as well. So these down here will then be gone if you close down Visual Studio Code. But if you then open up these logs inside CloudWatch through this way or method right here, you can then see the logs stored permanently. So right here, they'll just be there forever basically unless you delete them. And you can see all the same logs that we saw down in the terminal right here. So if you want to go back to see some of the previous logs, that is what you can do right here. So here we can again see the emotions and the sentiment class weights and then the epochs printouts. Great. So now we have successfully started up a training run with the finished model which we'll train. So you can keep training this one or you can use the file that I'll provide. But regardless, great job for getting this far in the process. So I just want to show you how it looks when the training has finished. So I've just picked out a training run I've ran before that will then show me the entire logs. And I ran this all the way through for all 13 hours. So you can then check out how it'll look. So if I press view logs over here, and then I just open up the log stream like this, then we should be able to see the logs. So just scrolling up, pressing load more. And I'll just keep doing that. Like this, exactly. Then scrolling down, we can go ahead and see the printouts, so available audio backends, as well as the dataset sizes right here. Then we can see the different metrics. Let me just close this. We can see the different metrics for each epoch. So this is the first epoch. We can then see the metrics after that epoch, so the losses and also the emotions and precisions. We can then see how it progresses through the different epochs, and then hopefully improves. So you can check out the metrics for each epoch down here. And then between each epoch, what you'll see is a couple of errors, for example, where this video cannot be opened, but luckily we do skip this video. Scrolling all the way down, it will then evaluate the model on the final test set, and then it'll print out the the losses and also the accuracies and precisions for these final test set. And then it will stop the training. So that is how it will look when it successfully runs through an entire training sample, an entire training dataset, and finishes up. Good. So what we can now do is take the output of this training job, and then we can go ahead and download the model file, which we can use to run inference on the model that we have trained. So I'll head over to S3, and then what this train SageMaker will do is create a bucket for you if you do not specify an output bucket. So this one is auto-generated, and I'll then just press this one and find the training job that I've ran. So this one right here is one I have run before, and then the output of this entire training run will then be this output right here, and we can then see model.tar.gz, so a tarball containing the model.path file. So we will need to go ahead and download this model file. So what I'll do is just press right here, select it, say copy S3 URI, hop over here, and then just select a new folder. So I'll just create a new one. I'll just create a new folder. So a new folder, call this deployment. Inside this folder, I'll just open up a new terminal. So I'll say open integrate terminal. And then to download the file, I can say AWS, so use the AWS CLI, S3, CP, and then I'll copy it from this S3 bucket path right here and over to my local directory. So you can specify as the second parameter which directory you would like to copy it to. So if I just say dot, it'll copy it to the folder we're currently in. So deployment and deployment right here. So I'll just do that and press enter and just wait for this to finish. So you can see how many megabytes it has downloaded so far. So I'll just come back when this is done. Now we can go into the deployment folder and see that we have this tarball that is compressed. So we can just go ahead and uncompress that or just extract that. So I'll say tar-x ZF, and then I can put in the archive. So this will be model.tar.gz, and then just press enter. And we can then just wait for this to extract. So now we have the metrics.json along with the model path, and we can just delete this model.tar.gz, so the tarball, because we do not need that anymore. So this is going to be the model. So I'll go ahead and create a new folder in here and say model, and then just copy this content into the models folder like so. And since we did this class imbalance fix, I would like to show you the model before and after the class imbalance fix, so you can know exactly why we did this class imbalance fix. So I'll just hop back into my folder full of model files, and then just find the folder with the model after the class imbalance fix. And that is going to be this one right here. Good. So I'll just take the output again and then just download this. So I'll copy the S3 URI and this just press up twice right here. And then I'll just go ahead and paste in the following command. I'll just need this CP as well. And then I'll just let it download this model as well. Now we are done downloading this model too, and we can just head into the deployment folder. And I'll just create a new folder in here called model normalized. So just normalizing the class imbalances. And then I'll just drag this model.tar.gz into that folder and just move into that folder. So I'll just say change directory, model normalized. And then I'll just find this command again. So tar and then extract the following file. And I'll just come back when that is done. So that is done already. And then I can go ahead and delete the tar ball file right there. So now we have the model before the class imbalance and the model after the imbalance right here. One more thing we just need to do is just hop in and download the TensorBoard log files. So if I hop under buckets, what you want to do is find your bucket right here and then find this TensorBoard folder. And then you can go ahead and copy the S3 URI right here. So you'll just need to hop back once again and then copy this UI. So you select TensorBoard, press copy S3 UI, and then you hop in here and say AWS S3 sync. Put in the URI like this, and then you pick the folder you would like to put it inside. So right now I would like to put it inside a folder in the root. So I would like a new folder with the TensorBoard logs. So I'll say TensorBoard logs like this. And then I can say open integrated terminal in root. And then go ahead and say AWS S3 sync, and then put in the following folder right here. And then also copy that to TensorBoard logs like this. If I then just press enter, it should synchronize this folder right here down to my local machine, so the files will be identical. But since I already have another bucket with my training runs previously, I'll just sync that instead. But this is going to be the exact command I'll use, and this is also how you're going to sync the TensorBoard logs down to your local computer whenever you do train in the future. So what I've done is just taken the TensorBoard folder from the other bucket I know and have used, and then I've synced that down to this TensorBoard logs. So this is what you should see after doing that and running that command. And now I can see all my TensorBoard logs. I will then be able to open up TensorBoard and then check these out. So what we can do is hop down here in the terminal and then say TensorBoard like this, and then -- log directory TensorBoard logs like so. This should then open up a server on our computer, which we can click. And then we should see all of our training runs. Now, bear in mind, I have a bunch of different training runs inside of this folder, and you might only have one or two if you have trained from what we did previously. So I'll just go ahead and select those that are relevant to you. So I'll hop under scalars and then toggle our runs. So I'll just deselect these. Then I would like to just filter out the ones I know are relevant to me. So it'll be this one and also this other one. So I'll just go ahead and select those two right now. And this is going to be the run before the class fix and then also after the class fix. If I just open up the relevant graphs, so that is going to be validation, test, and then loss over here, we can then check out the values. So the red arrow, the red graph right here is going to be from before the class imbalance fix, and the gray arrow is going to be after the class imbalance fix. So as we see for both emotion and also for sentiment, for both the validation and the training dataset, the loss is going down over time. The loss is jumping a little bit up and down, but generally is going down over time. So for the training dataset in the left column over here, what we can see is that it jumps more up and down, whereas for the validation dataset, it is going down more steadily. And as we would expect, as epochs progress, so this x-axis, as these epochs progress, the model gets even smarter and the loss will then decrease. So this looks like something we would expect from a model that performs decently. Great. Going down to validation down here, we can check out the accuracies as epochs progress as well. So as we would expect, as epochs progress, we then see the model accuracy getting better. So the model is able to guess more samples correctly whenever we run inference on the model. And this is true for both the emotion accuracy as well as the sentiment accuracy. Great. And as you see, we see larger increases in the accuracy in the start of the training. So right over here, the graph slope is a little bit larger than it is over here. So what happens is that we reach a point where it stops getting better and just kind of converges. So at this point, it would make sense to stop the training because we don't really see any benefits after the training through this point. We see the same for the sentiment over here. After we reach a point about here, it really stops getting better and just kind of stays the same. We see the same for position right there and also here. Scrolling all the way up to the loss, we are able to see the same over here. So we see that the loss keeps getting decreased and decreased in the start, but it kind of converges down here after a couple of epochs. And then we see the exact same over here. So this flattening of the graph, both the loss graph and also the accuracy graph down here, is what we call converging of the model. And when the model starts to converge during training, that's when it's a good time to stop training the model so we don't waste resources training the model even more because it doesn't really get better after this point. Now hopping down to the final test results, so after training the model for all 25 epochs, we then run the model on this test set only once, and we can then find out what the final accuracy for both emotion and sentiment is. So before the class imbalance fix, so that is the red dot right here, the accuracy is about 0.61. After the class imbalance fix, it is about 0.48. Then going down to the sentiment, before the class imbalance fix, it is about 0.67. And then after it is about 0.64. So let me just go ahead and illustrate these values for you in Excalidraw so you know what they mean and how precise the model actually is. So this is my small illustration about the results. So up here we have the emotions, which we can start out with. So the emotion problem is by far the hardest problem because up here we have 7 different labels to pick between, or the model does, and down here it only has to pick between 3 different labels. So if we were to just guess randomly between these 7 different labels, which is basically what it is doing before it has been trained, because it doesn't really know anything about the training data, it will have a 1 divided by 7% chance of succeeding. So that will be about 14.3% chance of succeeding. So that is the results we should see if we just run inference with a model that is not trained, that just randomly guesses. So what we did with the model was that we got results that was 0.62. This means 62% correctness. And down here we got 49%. So this is a pretty drastic improvement from just random guesses, which is about 14%. Down here we have a way simpler problem. This is just guessing the sentiment, from which we only have 3 labels to guess amongst. So right here we have a 33% chance of guessing correctly because we only have these 3. So we got it up to 68% without the class imbalance, and then 65% with the class imbalance fix. So these are the results we got with the model. So now we have an idea about the results. We can go ahead and close down this TensorBoard and just close it down here as well. And then we can start writing out the code for actually running inference on the model we have trained and then also downloaded. So these 2, and then we can see the difference between before and after the class fix, and also how it performs when running actual inference. So the first thing I'll do is just create a new file under deployment. This one is supposed to be called models.py. What I would like to do is just create a duplicate of the models file down here, but without all the things we do not need for inference. So I just closed down the Chrome browser as well, and then we can go ahead and just say, go into models in training, and then we can find the things we need. So we need the encoders, so the text encoder, the video encoder, as well as the audio encoder, and their forward functions, and then also this model right here, along with its forward function. So I'll go ahead and copy these, along with the imports, which we probably need for most of these, and paste them into the models up here. And we'll then just remove the things we do not need. So OS, we definitely do not need the metrics as well, and also not TensorBoard, and also not datetime like this. So now we have a bare bones setup with only the architecture of the model, so the different encoders right here. And we can then create another file. I'll say new file, and then call this inference, like so, .py. Then we can also just find a file to test on. So if I hop under dataset and then def, we can then find one that is clearly not neutral. So this one is positive and joy, and this one says you're a genius. So we'll just go ahead and find that one. That will have the dialog ID 1 and the utterance ID 1 as well. So this should be 1.1 right here. So if I just take this one and copy it and hop under deployment, paste it in, I'll just call this one joy. And now I can just close all of these different folders, hop under deployment, inference, and now we at least have a file to test on as well. Let's first create a function for loading the model into memory. So I'll say def model function and then model directory like this. So this is where the model will be at. So that is going to point to one of these. So either this one or this one. Inside this, we'll then first of all say device equals and then torch dot device like so. And then we can say CUDA. If not, CUDA is available, otherwise we'll pick the CPU. Then we can go ahead and instantiate the model. So I'll say model is equal to, I'll just import torch, and I'll also say from models, import multimodal sentiment model. So I'll say multimodal sentiment model like this, .to, and we'll just move it to the device. Then we'll just try and find this model file, so this model.pth file inside of this path. So I'll just go ahead and say model path equals os.path.join, and I'll join together this model directory along with this path file. Then I'll say if not os.path, so I'll just import os from up here, like this, dot exists, and I pass in the model path. Then we'll go ahead and try another one. So I'll say model path is equal to model directory. And I'll also join together model along with model.tar.gz. So I'll just replace this with model.pth like so. So we'll just try and see if there is another model folder inside of this model path. If we cannot find that, then I'll just go ahead and do the exact same down here. So I'll just pass in the model path again. And then if that is the case, I'll then say raise file not found error, model file not found. And I'll just say in directory, just so we know it for debugging purposes. And then model directory like this. And then we might want to change this from directory to path. So model path like so, and just hop down to the next line. Now we can say print loading model from path, passing in the path like so, like this. And then I can say model dot load state dictionary. We'll then say torch dot load and then pass in the following. So map location is going to be the device, and waits only will be set to true like this. And we'll then set the model to evaluation mode like this. Now we can just create the return statement. So I'll say return, create a dictionary, say model, and return the model like so, along with the device right there as well. We then want to create a video processor for processing the video we want to run inference on. So I'll say class video processor, and then I'll just create a method in here called process video like so. So we can actually just go ahead and head back to training, then find the melt dataset, and then we can find this load video frames method, copy this one, and then just paste this into this new class. And we just need to fix the indentation like this. And then we need to import CV2 as well. So I'll say import CV2, and then it doesn't look like we need other imports. Oh, we do need NumPy. So import NumPy SNP, and then those should be all the imports. So now we are able to load a video, which we'll use for inference when running this model as well. We can then just create the audio processor as well. So this will just be another class. So I'll say audio processor like this, and then I can just copy the audio processing method from in here. So that'll be extract audio features, which I'll just copy 1 to 1 and paste it into the audio processor. And I'll call this extract features, and we'll then just say max length and give it 300 right here. We can then just go ahead and import things such as subprocess. So I'll say import subprocess, and then also torch audio. So we'll import torch audio as well, like this. And then we are good for this method right here. Great. So my plan for running inference is the following. If I get a video that is maybe 1 minute long, I would like to take the transcript of that video, because right now, going into the dataset, you see that we have the transcript of each video. we do not have the transcript if we just input a video, so we need to find the transcript ourselves. So we'll find the transcript and then we'll divide it into all the utterances, and then for each utterance we'll then run inference on that utterance, because that is what the model has been trained to do, running inference on specific utterances. So I'll just create a class for processing these individual utterances. So I'll say class video utterance processor, like this. In here I'll just create a constructor where we expose the video and audio processor, like so. Under this I'll create a method called extract segment. I'll pass in self, video path, start time, and the end time, like this. And then also just a temporary directory, which we can use to store these extracted video pieces. So an utterance will just be a subpart of a video. So an utterance will have a start time and an end time in the video, and we'll then extract the utterances part of the video from the video and then run inference on that little sub video. So that is why we need to create this extract segment, to extract the utterance segments from the video. Now we can just go ahead and say os.make directories. So we just want to make sure that this temporary directory does exist before we can use it. Then I can just go ahead and create the path for the file we'll extract. So I'll say segment path equals os.path.join, like this. And then I can say temporary directory. I can pass in a formatted string. So we'll say segment underscore the start time underscore the end time dot mp4, like so. Now I can just extract the video from the start and end time to this segment path. So I'll say subprocess.run and then pass in each argument. So I'll say FFMPEG. I'll just need to format it in this way. And then -i. Then I can say video path. Then I can go ahead and define the start time, like so. I can define the end time like this, so SS and then 2. I can then just re-encode the video. So I'll say dash CV and then CV, like so. And then I can go ahead and pass in libx264 right after that. I can then re-encode the audio, like so. And I can then just override the output if I have an output already. So -y. Then I'll just pass in the segment path lastly. So this is where we'll extract the segment to, and this is going to be where we extract the segment from. So this is the original video. Then I'll just say check equals true to raise an error if it does not succeed, and then just set these to null to not have a lot of output. Then what I can do now that we have extracted the segment, I can just check that it actually exists. So I'll say if not os.path.exists, and I put in the segment path, or os.path.getSize, that segment path equals 0. Then I'll just raise a value error saying segment extraction failed, and then I'll also just pass in the segment path actually. And then if this is true, this is not true, so if it worked out fine, then I'll just go ahead and return the segment path. So return segment path like this. And now I'll be able to extract a single utterance from a video, so just the video part basically, from a original video. We need to be able to tokenize the text, and we also need to be able to use a transcription service. So what I'll do is just use a Whisper model from OpenAI. So we'll use it exactly like we use these pre-trained models in here. So let me just find one of these. So if I go in, just to models, and then scroll all the way down, we can see these models. So this is the bird model, for example, and then we say from pre-trained. So this will download the model to our computer and then just use another person's model or another research group's model inside our software. So we'll do the exact same just for finding out the transcription of the model. And the model we'll use comes from OpenAI and it's called Whisper. So we'll say pip install OpenAI Whisper. And from this package, we'll just use the base model. So I'll install this right here. And then I would also like to say import Whisper. And then while we're up here and we are talking about text, let me just go ahead and say from transformers, import the bird tokenizer. I'll just import the auto tokenizer. And then we should be ready to both take the transcription and also to tokenize the text later on. Now hopping down to this model function, we already returned the model. So I'll just return a tokenizer as well. And this should be auto-tokenizer.from pre-trained, so bird base uncased. And then what I can also do is just return a transcriber. So I'll say transcriber like this. And I would like to return whisper.load model like so. And then I would like to load the base model with the device being the CPU if device.type is CPU, otherwise we use quota, or just the other device that was currently used or currently selected, so just device like this. Then we can just put in a comma and we should be all good for this method right here. And now we can create a function for predicting. So first I'll say if name equals main, then I'll go ahead and say process local video. And then I'll just pass in so select the same directory we're currently in, and then joy.mp4 like this. So just pass in this joy video, and then we'll just need to create this function. So I'll say def process local video. I'll pass in a video path, and then also a model directory, which we'll just set to model right here. So just this one. Then what I can go ahead and do is just say model dictionary equals model function, and we'll just pass in the model directory right there. Now I can go ahead and say input data equals, and then just a dictionary with the video path, and then the video path like so. And then I would like to create a function for doing the prediction part. So I'll just say predictions for now equals, and then some predict function, and we'll pass in the input data and then also the model dict. I'll just comment this out for now and just go ahead and implement this predict function. So over here I'll say def predict function, and we'll receive the input data as a parameter along with the model dict from down here. Now I can just go ahead and say model equals model dict model. Then I can say the tokenizer equals the model dict tokenizer like so. I can then also get the device. That is just going to be model dict device, and then also the video path, which is going to be input data video path. Now I can just get the transcription with timestamps from the transcriber. So I'll say result equals model dict, and then transcriber like so, and then dot transcribe. And then I would like to pass in the video path, and then also word timestamps true, so we can get the timestamps of the words, so we can cut out that segment. Great. Under that, I'll just create a new instance of this utterance or video utterance processor. So I'll say utterance processor like this equals video utterance processor, and then I'll say predictions equals an empty array for now. And then I'll loop through each segment we find in this transcription, and then I'll create a segment for that and do the inference for each segment. So I'll say for segment in results segments, and of course this is just result as I just renamed it. And then I'll say try, and inside this try I'll just say print for now, and then I'll just do this except as well, and just say print. Great. Now we can fill these out later. So inside this try, I can first extract the video segment. So I'll say segment path, so we get the path to the extracted video, and then I can say utterance processor.extract segment, and then I can pass in the video path like this, and then I can just say segment start time, or just start like this, and then I can say segment end. And the segment we get from this result, so that is coming directly from the transcriber, which will then give us all the segments, so basically just all the utterances. And then we can first of all process the video. So I'll say utterance processor.video processor.process video like this. And then I'll just pass in the segment path. Then I can say utterance processor, I'll just copy this line, and then say audio, and then just pass in the segment again. Then I'll say video frames equals, and down here I'll say audio features equals like so. So we do just need to call this audio processor, and then we can say dot extract features. And up here, this is not called process video yet. We still call it load video frames. So I can just replace that name as well and hop back down. So now we have the video modality for the input of the model. We have the audio modality, and now we just need the text modality, so the tokenized transcription. So I'll say text inputs equals tokenizer, and for the tokenizer I'll pass in the segment, and then I would like the part called text. I can then also say padding, that's going to be max length, and truncation will be true, like so, and max length will be 128, and return tensors will be in PyTorch form. Now I can then move all of these to the device, so I'll say move to device such that we have all the inputs, so all these tensors, on the same device as we do the model up here. So I can go ahead and say text inputs equals, and then I can go and say for key value in text inputs.items, and then for each of these I'll just say key and then value dot to device, like so. So that was the text inputs. Then I can say video frames like this, and that is going to be video frames dot unsqueeze 0, and the exact same for the audio features. So this will just be audio features like so. And the reason we unsqueeze right here is to add another dimension in the tensor that is just 1. So the model expects the first dimension of the tensor to be the batch size. So something like this, batch size, and then comma, channels, and then height and width, for example, height and width. So this is what the tensor or what the model expects. But right now we do not have this batch size, but we trained the model for using batch sizes. So we'll just need to add this dimension. So this is before unsqueezing, and this is after unsqueezing, and this will just be 1. So we'll basically take a model meant for batch processing and just run a single sample through it. Then we can go ahead and get the predictions. So I'll say get predictions, and I'll then go ahead and say with torch.inference mode. Then I can say outputs equals model, and we'll pass in the text inputs, the video frames, and also the audio features. From that we can then get the probabilities of emotion. So I'll say emotion probabilities, and then this will be torch.softmax, and then I'll say outputs, and I'll get emotions like this, and then we'll take dimension 1, and then the first element like this. And then I can do the exact same for sentiments right under, just calling this sentiment probabilities instead. So an output will have the batch, so batch, this could be 1, and then it will say 7 after this. So the output will then have the batch right here, and then the probability for each after that. So for sentiments, this will be 3, for example. So this means that the tensor will look something like this. So 0.3 or 0.4, sorry, 0.2, and then 0.2. So this could be the output tensor. So what we do is that we take the softmax of this for the first dimension. So we skip, let me just go back. We skip this batch dimension, and then we just take the first dimension, so the probabilities, and softmax will then make all these normalized to between 0 and 1. Then we take the normalized probabilities with the following indexing right here. And this way we can get the emotion probabilities and the sentiment probabilities. So this will be a probability for each of these labels for both the sentiment and the emotions. Now we can get the top 3 emotions and sentiments, so those with the highest probabilities. So I'll say emotion, values, and emotion indices like this. And that is equal to torch.topk. And then we can pass in the emotion probabilities along with 3. And then for the sentiment, we'll do the exact same. And after this, we can just add this prediction to the array of predictions up here. So this is an array of predictions per utterances. So each element in this one will be a prediction for a single utterance in a video. And we have done it this way again because we can have videos pass into the model that are longer than an utterance length. So I'll say predictions.append. And what we want to pass in is the start time. And this will be segment start, the end time, and then we would like to pass in the text as well. Now we can pass in the emotions. So this will be emotions like so. The emotions will be an array, and I'll just say label. And let me just go ahead and define a map for finding out the label from the number. So if I go all the way up here, we can just define the mappings. So the emotion map will be, let me just spell this correctly, emotion map. Then we'll also have a sentiment map like so. So the emotion map will contain 0, that will be anger, 1 will be disgust, 2 will be fear, 3 will be joy, 4 will be neutral, 5 will be sadness, and 6 will be surprise like this. And then down here, we can just have 0 for negative, we can have 1 for neutral, and then 3 for positive like this. Oh, sorry, we just need to fix this. So 2 for positive. So it'll look something like this. Exactly. 0 for negative, 1 for neutral, and then 2 for positive. And going back down, we can use these in our predictions when mapping the results. So all the way down here, under emotions, I'll just say label, and that should contain the emotion map. So we'll just map it to an emotion, and then I'll say idx.item. And one thing that is important to know is that we'll just go ahead and say for idx and conf in zip emotion indices and emotion values like this. So now we will be able to get this idx.item, and then we'll just go ahead and call this item method. And then apart from the label, we also need another thing. We need the confidence. So this is going to be conf.item like so. So I'll just go ahead and press save and then hop down to the sentiments. So if I just copy this one right here, hop down to sentiments, we'll just say sentiments. This will be the sentiment map. We'll have the exact same otherwise, so we'll just call this sentiment indices, and this should be the sentiment values like so. And then we'll just put a comma in between these. For except, we'll just go ahead and say segment failed inference, and then we'll just create a finally, and we'll just do some cleanup in here because we did do some processing, including creating another extract of a video file right here. So this should create another file. So we just want to clean that up. So I'll say if os.path that exists segment path, then we'll just delete that file. Now, right under this, I can go ahead and say return, and then I should return the utterances, and this will then just be the predictions for each utterance like this. And now we should be able to call it down here. So predictions will be equal to this, and then I can say for utterance in predictions, we'll then print out all of these informations. So utterance, let me just format it myself actually. So I'll go ahead and say print, and then I would like to put in a new line and then say utterance. In here I'll say print a formatted string with the start and the end time. So the following right there. Then I would like to put in the text so that it did correctly as well. Then the top emotions. So I'll just create a new line, say top emotions. Right here we should say for emotion, utterance emotions, we'll print out the label along with the confidence, and we'll do the exact same for the sentiments. So top sentiments, then loop through those, and then we'll just print out this character right here times 50, just to create a separating line. So let's go ahead and check out if that works. So we'll just say open an integrated terminal in this deployment folder right here. Then I can say Python inference.py and just run that. and we can just go ahead and see what happens. So it loaded the model from model.model.path. That is correct. Segment failed inference. So let's just go ahead and print out. So we can just print out the exception. .e like this. And if we then just do it again, we should be able to see what the error is. So pre-trained tokenizer got an expected keyword argument trunction. So searching for trunction, Control F, we can see that it says trunction. It is supposed to be truncation like this equals true. So let me just go ahead and run it again and just see what happens. So I'll just keep waiting. And then at least something is happening right here. So we actually got an output. So we get the utterance, start time, end time. The text is "You are a genius." This comes from the model that is pre-trained that runs the transcription. So this one right here. Then we get the top emotions and the top sentiments. So this is the model that is not normalized. So this one has the class imbalance problem. So we see that neutral is 0.70 and joy, which it is supposed to be, is 0.15. So this is obviously very wrong, but joy is still way higher than anger. So it's relatively better than anger, so that is fine. For the sentiments, the neutral is also way bigger than both positive and negative, but positive is still bigger than negative. So it seems that if we can just normalize these values, they will be correct because positive is better than negative, or it's larger than negative, and joy is larger than anger, which it is supposed to be. So let's just go ahead and try and run it with the normalized model where we did fix the class imbalance problem. So hopping down here, instead of model, I'll just use model normalized like so, and just make sure we don't use model anywhere else. So we have model like this, and we should then be able to just try and run it again, just to see the difference in the results. So let me just run it again and come back when it is done. So now that it is done running, we can see that neutral is still bigger than joy and also bigger than positive down here, but it is way larger than it was before. So before it was 0.70 and joy was 0.15, and down here it is 0. So it's basically twice as it is supposed to be. So right now it is more balanced, but we still see the same problem. So when building out the frontend for this app, what we're going to do is just list the top 3 emotions and sentiments, such that if this class imbalance problem does occur, like it does right here, we will be able to show the user which ones are actually the most predicted ones. We should be able to find a video though we can test on where we can actually showcase that it does work. So hopping into the CSV file, let's just find one that is positive. So this one really just like a super simple word, and then it is surprise and positive, and this one is 2 and 3. So if I just go ahead and find 2 and 3 right here, this one is supposed to say really. So I'll just copy this file, hop into the deployment, copy this name, so I'll press enter and copy it with Control C, hop back into the Inference file, and then just paste this in instead of the joy.mp4. If I then just say python.inference.py, we should just be able to see that it hopefully works. So right here, we actually see surprise being the most predicted one, emotion, and then positive being the most predicted sentiment. And then neutral is not overbalanced like it is supposed to be, like it is not supposed to be. So this actually lets us know that the model does work. So if you remember back to the TensorBoard graphs, you might remember that the accuracy was lower for this normalized model than it was for the model without this class imbalance fix. And the reason is that if the neutral is overrepresented such that it is about 60% of all the samples, so way more represented than other ones, and the model always guesses neutral, then the model will then be correct in about 60% of the different cases. But now the model is actually forced to guess some of the other ones, some such as surprise and positive. The model will be less accurate because it won't just guess neutral all the time, but at least we'll have responses from the model or predictions that we'll be able to use for anything. Because what we would use a model for that would just predict neutral all the time, that is not something that is very generalizable. So this is why we went with this class imbalance fix. I just wanted to show you as well how our model is performing compared to state-of-the-art models in the research field. So I've opened up this website, paperswithcode.com/dataset/melt. So this is a pretty popular dataset to work with, so it has its own page right here. We can then see the different benchmarks for how the different models are performing with this dataset, and one of these benchmarks is emotion recognition in conversation like this. And this is one of the prediction heads that we have as well. So if we set the view to accuracy instead of weighted F1, we'll be able to see how our model is performing. So for the emotion without the class imbalance fix, we have a score of about 62%. So hopping back, that would correspond to somewhere about right here. So we have some models performing worse than us, but also the majority of the models performing a little bit better than us. And what you can then do if you're interested in how other people have solved this problem, you can go into the paper, find PDF, and then open up and see how they build out the model. So this will explain the entire architecture of the model, along with the results that the researchers got. But what I think is the most interesting right now is this class imbalance fix right here. So hopping into a couple of these different papers from this MELT dataset benchmark, what I can do is just check out if they have written about the imbalance. So in this paper, for example, what they have written in one of their sections, and I've read through a couple of these papers. So this one is called SDT, their model. So SDT also tends to misclassify other emotions as neutral on MELT due to the neutral as the majority class. They additionally also say it is difficult to correctly detect fear or disgust emotion on the MELT dataset because the two emotions are minority classes. And this is also exactly what we saw and also why we fixed the problem with the class imbalance fix right here, even though the class imbalance fix gave us lower accuracy. So another paper over here is the following one. So over here they say MELT is highly imbalanced with neutral emotions comprising about 50% of the dataset. The high weighted F1 score primarily reflects the model ability to predict the dominant neutral class rather than its capacity to distinguish between other emotions from the speech features. So what we saw over here was that it just guessed neutral every single time. So that meant because we had a dominant class which was neutral, we got a relatively high score of 62%. Whereas if we did fix the class imbalance problem, we got a lower accuracy down here. But what we did was that we got better results in total. And then I also found another paper over here, which is the following one. And here they say, even in the case of MELT, the emotion in which the most emotion classes are misclassified is neutral with the highest count. We can observe that a similar misclassification tendency in other research happens as well. And then they say, hence, we suspect that the cause of the misclassification is not a problem with the method we proposed, but rather stems from the class imbalance issue, which is what we saw as well. Now, to be able to deploy this Inference script as an endpoint on AWS, we first need to know that when we do deploy the endpoint, it is going to run on an instance exactly like when we did when we were training. So when training, what we did was install FFMPEG. So going under training and then install FFMPEG, I'll just copy this entire script and we'll just install this again. So I'll just paste it in somewhere. I'll just hop all the way up and just paste it in right there. And then if I scroll down to the model function, what we can then do is just install FFmpeg. So we'll then say load the model for inference. That is what we do in this model function. So we can then say if not install FFmpeg, then we say raise runtime error. FFmpeg installation failed, and then we can say required for inference like this. So this install FFmpeg we'll just need to install sys or import system as well. So import system like this. So what it'll do is it'll return true if FFmpeg is already existent on the computer, or if it just installed it. Otherwise it will return false. This way we can abort the script if we see that we will not be able to run inference. We need to create an endpoint letting SageMaker or the SageMaker endpoint know how it should process the data it will receive. So when it receives a request, how should it then run inference on the endpoint? This will be called input function like so, and it will receive a request body and then also a request content type. So I can then go ahead first of all and say if request content type is application JSON. So if it is a JSON body we get, then we can say input data equal JSON.loads request body. So if I just import JSON up here, we should then be able to scroll down and continue. Now what I would like to send each endpoint when I call each endpoint is a video path, and this video path will be the S3 URI to a video somewhere in an S3 bucket that this endpoint should run inference on. So I'll say S3 URI equals input data, and then this I'll just call video path, like so. Then I can say local path equals, and then I'll just create a method called download from S3, and then I'll pass in this S3 URI. Then I can say return video path, and then local path like this. And if it is not a JSON object we receive as the request body, I'll just say raise value error, and then I'll put in a formatted string, and this one should say, unsupported content type, like so. And I would like to pass in the request content type just so we know what it is in case. Then we can implement this download from S3 method, which will then download it from the S3 bucket down to the local instance that this sentiment endpoint will be stored on. So I'll say def download from S3, like so, and we'll pass in the S3 URI. Then I can go ahead and say S3 client is Boto free, and we'll just need to import Boto. So import Boto free, like so. Scrolling down again to where it is, right here. What I can do is say .client and then S3. Under that I'll say bucket is equal to S3 client URI splits, and I'll take the third element, so index 2. So an example of a URI that we might process is the following one. So if we have an S3 bucket, this will be the bucket which we created probably. Then we will create another folder called Inference. So inside this is the same level of folders that Dataset is also at. So I'll create another folder next to that called Inference. Here we will be able to upload videos from the front end, such as this one. And then we'll get the bucket from this element right here. So this will be the first element. And right here it will break again when we split. So this will be the second element. And this will then be the third element in the split when we do split this. Then we can get the key, which will be this entire piece right here. So we'll need both this element and every element right after that. So I'll say key, and then I'll take the following one, .join. So we'll join together with this as the middle thing in the middle of the things we join together. And then we'll take the S3 UI.split, and then we'll take the third index and then everything after that. So that will correspond to the following right here. Now that we have that, we can say with temp file, which we'll just need to import as well. So I'll just hop up and import that, import temp file, scroll all the way down to right here, and then I can say named temporary file, and then delete equals false. And then I can say suffix is mp4, so .mp4, like so. And then I can say as temporary file, and then we should be able to say S3 client .download, and I'll just say download file. Then we can put in the bucket, the key to the item we want to download, and then we can say temp file .name to get the name of the file we would like to download it to. Then I can just say return temp file .name, like so. So we get the S3 URI we're supposed to download from the incoming request to the endpoint. We then create a temporary file with that S3 file. So we'll download it down to the local instance which the endpoint is running on, and then we'll get the bucket and key from the S3 bucket. We can then download it down to a local path which is stored inside this temp file.name. So this temp file.name will store the absolute path to the temporary file, and this will work on any operating system. So using temp file.name temporary file. And then after doing that, we can then return the temporary file.name, so the absolute path, and then use it in here. So now we have a local path, which we'll be able to use inside the model function and also the predict function, because that is where the video we're going to run inference on is going to lie. The last thing we need to do is just define an output function. So I can go ahead and say define output function, and then I can say prediction, and then also response content type. So this is how the endpoint is supposed to return the predictions that we made with the inference. So I'll say if response content type equals 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 application JSON. Then we'll just say return JSON.dumps prediction right here. Otherwise, we'll then say race value error and then unsupported content type like this. Now we should be almost ready to deploy the endpoint. So I'll just go ahead and delete these two files, close down the training folder, and then as you see inside the training folder, what we did was that we used this train SageMaker to then bundle up this entire training folder, send that up to the cloud, and the cloud would then run that as a training job in a Docker image. And we're going to do almost exactly the same with this deployment. So instead of a train SageMaker, we'll just create a file in here. So this one will be called deploy endpoint.py like so. And then here we'll do kind of the same thing as we did in here. So I'll just go up to the deploy endpoint and then first of all just import a couple of things. So SageMaker.PyTorch. We'll import PyTorch from that, and then we'll also import SageMaker. Then I can say def deploy endpoint and then just print something. And then outside this, I'll just call this if we are inside main. So if name is main, then we'll deploy the endpoint. Then I can say SageMaker, or I can just say SageMaker.session. We'll start a new one of those. Then we'll just take a role. So this is going to be the role from AWS. So we'll just go ahead and get that. So now we have this window open over here as well. Then I can go in under IAM. So I'll search for IAM like this. Then I can just hop under roles and we can find our deployment role. So that is going to be sentiment analysis deploy endpoint role. And one thing I just want you to do before taking this role is just opening this execution role in another tab. Then we can open up the deployment role in the main tab. Then we can just open up this execution role, find this right here, so the policy. And you need to remember how we added this line because it failed. Well, we just need to do the same thing under the deployment role. So right here, I'll just edit this policy and I'll just paste in this line right here, just so we are able to access all the items from the bucket because we didn't do that before. Now I can just say next and save changes, close down these tabs right there and right there. And we can then just grab the ARN of the deployment role. So that is going to be the following one. Paste it in on the role right here. Create a new line and just save that. Great. Then I also just need to put the model file inside an S3 bucket. So right now we have it in these folders right here, but that won't really do it. So what I'll do is just find S3 over here. I can just close down this tab. So I'll find S3 and then the model file should be inside your SageMaker right there, and we'll just see if we can find the model. So this is the one that I'm going to be using. So let me just search and replace that. So this is the one that this is the output of this training run, which I'll use, and this is going to be the model with the class imbalance fix. Then I can go and click output. I can select the model.tar.gz file. That is what we want to put inside of our S3 bucket. Then copy the S3 URI, and I'll just paste it in as a comment right here for now. Then what I would like to do is just go back, find the bucket, which we made, so sentiment analysis SaaS. Then I can just say create folder. Then I would like to just say Inference like so, and press create folder. Under Inference, I'll just go back. I'll just select Inference right here and copy the S3 URI. And then I'll open up a new terminal over here. So open an integrated terminal. I can then say AWS S3 CP. So we'll copy it, and then we'll copy it to this Inference folder, and we'll copy it from this URL right here. So this is the file we'll copy. We'll copy this, and we'll copy it over to the other bucket right here, to this Inference folder. So I'll just press enter, and we'll just see how that works. So it is copying about 500 megabytes, and it'll be very fast since it is inside this ecosystem of AWS. If I then just refresh right here and press Inference, we should be able to see the model.tar.gz file right there. So that is all good. Now I can just go ahead and copy this URI, so S3 URI right there, and we'll just say model URI is equal to the URI right there. So let me just remove that and this one. Now I can say model equals PyTorch model, and I'll then say model data equals the model URI. Then I can say role equals role, and the framework version is going to be 2.5.1. The Python version is going to be Py 3.11. The entry point is going to be inference.py, and the source directory is going to be the one we're running it from. So that'll just be dot, because we'll run it from inside this deployment folder. Then we'll just say name. The name of the endpoint should just be sentiment analysis endpoint, like this. So this will set up the configuration values. So we'll just need to import this PyTorch model up here. Instead of PyTorch, we can then say predictor equals model.deploy. We'll deploy a single instance, and it'll be ml.g5.xlarge. So just the same that we used to train on, because that is super fast. The endpoint name again should just be sentiment analysis endpoint. I'll just call this sentiment analysis, like this. Great. I'll call this model sentiment analysis model, and then I'll call this endpoint sentiment analysis endpoint. Great. So now I can just save this, hop into deployment, press open in integrate terminal, and then we should be able to deploy in just a second. We're just missing one thing. First of all, I'll just hop into SageMaker, go under Inference and Endpoints, and then the same way we created this requirements.txt file whenever we created the training job, we'll also need to do that on the instance for deployment. So I'll just copy this file up, and we'll just need to change a couple of things. So I'll delete from transformers and down, and then I'll say OpenAI Whisper, which we used, and this is kind of a weird version, 2024, and then it's going to be 930, like this. So that's going to be the OpenAI Whisper version. Then I'll say numpy equals 1.26.4, and then NV GPU, and that is not something we have installed right here, but if we do not install this, then the endpoint will fail whenever we deploy it to the endpoint. So that is just something I spent a lot of time figuring out at one point when I was training models. So you might as well just do this now and save yourself the headache. So if we install NV GPU, I can then say 0.10.0, like this. And then I can go ahead and say sound file as well for the FFMPEG backend. And then FFmpeg Python. And this is not the FFmpeg backend, sorry, that did not make sense. It is the Torch audio backend. Then I can say 0.2.0, like that. I'll just go ahead and save. Oh, I just need to change one thing. This is supposed to be 4, and this up here is supposed to include another 0, like that. And we'll also just bump up this version to 47.1, like this. And then we're also just missing OpenCV Python, like so. And this will be 4.10, 4.10.0.84, like this. And then we should be all good. So saving that, closing it down. Now we have the requirements all in order right here. And then I can go ahead and just say Python, because we are inside this deployment folder right now. If you aren't, you can say cd and then deployment. So I'll then say Python deploy endpoints.py, like so, and then just run that, and then we can just see what happens, if anything is created over here or not. I'll just come back when anything has happened. Alright, so it just finished, and this is what we see. If I scroll up, we see a couple of logs we saw from the beginning, and then we saw creating a model with name, sentiment analysis model. So if you go under models, under inference right here, you should be able to see this sentiment analysis model, which was created. Great. Then we see the endpoint, which was also created. So first it's creating an endpoint configuration. That is this one right here. Afterwards it's creating an endpoint, which is the sentiment analysis endpoint. So right now it does say in service, but it looks like it crashed out with a kind of weird bug or something. So let's just go ahead and try and fix that. So if I click this endpoint, then I scroll down to the model container logs, we should be able to see the logs of the instance that are hosting this endpoint. So we can click this log stream, And then I'll just enlarge this screen a little bit so we can check it out. So we do see some kind of error right here, and it looks like, let me just enlarge it a little bit, an error up. So undetermined string literal detected at line 332. Then I'll just try and find this inside the code. I think it's inside models. So if I search for that, no. Inference, yep, we do see something right here. And it does look like it could do a line break that it is not supposed to do. So if I just go ahead and remove this line break, press save, and then add these 2 more strings, that should fix that issue at least. Now then I'll try and save right there, and then hop back, and then we can just delete this endpoint because that is obviously not working. So I'll just take this endpoint, say delete, because we don't want it to retry because it costs money every time every second it is running basically. So we'll delete that endpoint, hop over to endpoint configurations. I'll just delete these ones as well, like so. And then for the model, I'll just delete the model as well, just to make sure we have a clean slate for deploying the endpoint. Right there and right there. This one should be deleted right now as well. Then hopping back over here, I can just remove this one. Then I should be able to say Python deploy endpoint.py and then press enter. Okay, so I just tried running this command again, deploying the endpoint, and I kept getting these errors with line breaks. So what I'm going to do is just comment out this code because we won't really need it anyways. It was just for local testing. And then we don't have any other print statements that should be able to give us these errors anymore. So we only have this one, and that's about it. So let me just open up the terminal once again, right there, and then just deploy the endpoint again. So I'll hop into deployment, and then say Python deploy endpoint.py, like so. And that should then deploy the endpoint. So I'll just come back when this has finished. Okay, now it's deployed, and it seems to have deployed fine. And hopping over here to the endpoint, we can just check out the logs just to make sure that it actually is fine on the instance. So I'll open up the container logs, and then I have a log stream from about 12:36, like so. 56. And then scrolling all the way up, we should be able to see the logs from the beginning of the instance. So up here it installed FFMPEG, right there. It did that successfully. Then it loaded the model right here. It says loaded model from path, so that worked fine as well. Scrolling down, we do not seem to have any errors. And right now it is just listening right here. So everything seems to be fine. And with this done, we can go ahead and create the user that is able to invoke the endpoint from the front end. So if I just close down the logs again, then hop over to IAM, I'll just open up IAM in a new tab like this. Under users, we'll create a new user. I'll call this user, or actually sentiment analysis invoke user, like so. And then just press next right here. Then we can attach policies directly. And what I would like to do is just create a policy from scratch. So under permissions, we can just go ahead and pick JSON right here and just fill this out ourselves. So what we want here is a couple of different things. Under statements, the first one I'm going to do is the following one. So under effect, I'm going to put in allow. Under action, I'm going to put in s3 and then put object, like so. And then under the resource, which we would like to do this, or to be able to do this action for, I'm going to put in the folder for the S3 bucket. So I'll just search for S3 like so, find our bucket down here. This is the one. Copy that bucket's ARN. So I can copy this one right here, go back, and then under resource, I can just put in this one. Then I'll just refer to this inference path right here. And then we will be able to upload objects into the bucket under this folder specifically. Now, what I would like to be able to do then is to be able to invoke the endpoint. So first we upload a video to our bucket, and then we'll be able to invoke the endpoint and download that video from the bucket and then run inference on that. So the next thing I'm going to do is just copy this one, paste it down below, And then under action, I'll say SageMaker Invoke Endpoint, like so. And then under the resource, I would like to grab the ARN from the endpoint over here. So I'll just copy this ARN, hop back into the policy, and just paste that in under resource right here. So now we'll be able to invoke the endpoint, but only this specific endpoint right here. Good. And then I'll just need to remove this comma right there. And then I can press next. And then the policy name is just going to be something kind of like the user's name. So just going back, I'll just copy this name and paste it into the policy name. Sentiment analysis invoke user policy. Like so. And then I can just say create a policy. Then hopping back over, under create user, going to next, we can then just see if we can find the policy. So I'll just paste in this one, and then I can find the one we just created. Press next, and then I can press create user, and the user will then be able to use the policy which we just created. So this one right here. Like so. So this way we can, under this user, when we build the frontend, create an access key right here. And then from the frontend, we can then upload to the bucket and then also invoke the endpoint through this user with these access keys right there. And with this done, we should be ready to build out the frontend. So now all the Python code is done basically. So we have the endpoint with the trained model, and now we just need to upload elements to the bucket and then run inference as we talked about earlier. So what I would like to do before building out the frontend is just delete this endpoint. So this endpoint is going to be priced by the pay-per-hour pricing model. So depending on how many hours you have this running, you are going to pay a price for that. So it is not serverless where we pay based on usage. So therefore I would like to just delete this endpoint right here. And then when we do need it, we can always just go ahead and deploy the endpoint like so. But for now, I'll just go ahead and delete this. So if you want to save money and you do not need this endpoint right away, you can just go ahead and delete that. And then we will be ready to build out the front end. So again, congrats for making it this far. Now we have a fully functional AI model, and we will be able to deploy an endpoint so we can run inference on that. Good, so now that our endpoint has been deleted, what we can go ahead and do is just open up a new folder right here. And this folder we would like to open up is our repositories folder again. And I'll just say open. And then in here, I'll open a new integrated terminal from the root of this folder. And now that we have this folder, we would like to create a project. And again, I'm going to use the T3 stack, which I've used in all my previous videos. So I'll say T3 stack, just search for that. In here, we can just copy this line and use npm. That is what I always use. And then we can just go ahead and paste this into the terminal right here. What will your project be called? And our project will be called Video Sentiment SaaS. So this is going to be the front end part of the project. We'll use TypeScript, Tailwind CSS, Node-to-gRPC, and then Next.auth authentication. We'll be able to use Prisma, and the app router as well. And then we'll just use SQLite for now, just to get it set up. I'll then say no for the Git repository, but if you're doing this on your own computer, then you might want to say yes to this, just so you can have it in your GitHub, in your local portfolio. Then I'll just say no to this, therefore, and then just yes to the npm install. And this one I'll just leave as it is and press enter. And then it should just install all the dependencies and create the project for us. And then we can just open up the folder in a second when it is done. And in the meantime, I'll just go ahead and close down these different things and then just find our user right here. And then when this is done, I'll come back in a second. So now it's done installing, and we can go ahead and open up the repository it just created, which is this one. So I'll hop into File, Open Folder, and then just find my repositories, and then the Video Sentiment SaaS right there, and then press Open. Now we should see the project which it has just generated. And then the third thing I would like to do before closing down AWS is just to copy the access key, which we'll need to be able to invoke the endpoint. So under the environment, I would like to just go down and then create a new line. In here, I first want to define the AWS region. And this is going to be US East 1 for me. So you can see it up here. You can see different regions, but I always work with US East 1, so not 10, 1. And then under that, I'll just say AWS access key ID, and then also AWS secret access key, like so. So I'll just go ahead and save, and then go over here to my user, which we just created, and then say create access key. Now I'll just say other for now, and then just say next, create access key. And now we should be able to copy the access key right here. That is going to be this one. And then the secret access key is going to be this one right under that. Great. Now I'll just remove these auth Discord ID as well, since we will not use those. I'll close down this env. Wait, I'll actually just wait with doing that. I'll just say done, continue. Then I'll make this a little bit smaller, hop over to the source folder, and then the environment.js, open that up, and then also this env. And I'll just do it in 2 different panes if I'm able to. I am not. Oh, I am, right. So these auth Discord ID, I'll just delete those, like so. And then also from down here. So I'll just delete these 2 as well. And then I can just go ahead and add 2 more lines. So this will just make our environment variables type safe. So the AWS region is going to be a string. So I'll say set.string, like so. And then the AWS access key ID is just going to be a string as well. And the same thing for the AWS secret access key. So I'll just say set the string to, and then down here, we can just paste these in. So the AWS region, the AWS access key ID, and then also the AWS secret access key. So I'll just press save. And now these environment variables should be able to be used within our program in a type safe way. So that is one thing I just wanted to get out of the way. And then another thing you might see right here is that we are using SQLite. So this will just create an SQLite database up here in the Prisma folder, or down here. Sorry, it's going to be down here, an SQLite database. So this won't connect to any databases in the cloud, but rather just use a local file. And then whenever you're ready, you can go into the Prisma folder and then just use another provider. So you can use Postgres, for example, if you would like to use Postgres SQL. And then just switch from SQLite to Postgres if that is what you wish. But to keep this video simple, we'll just use SQLite for now. So that is the rationale behind using that database. I'll just close down this right here, and then also open up a new tab. We won't really need AWS for a while now, so I'll just close that down. Then under npm scripts, we can just open it up, and then find next.dev. If you do not see npm scripts right here, you should be able to right click it, and then toggle this npm scripts right there. This means you can see all the npm scripts from inside the package.json, and each of these will just run a different command specified in the string right here. So we would like to run this one called dev, which just serves the entire application as it is from the development server on a local computer. So I'll just find this one, press run, and then we'll just see what happens. So we see this localhost, so I'll just hold down command and click that. And then we just see what happens over here. So it opened up just fine, so that is perfect. Now, the first thing I would like to do is just set up a simple login system. So if I hop under source, and then server, and then auth, and then config, we should be able to see the config file for next auth right here. So I'll just close down this terminal by clicking here twice, and this will not close the terminal, so close the server, but just close it down so I'm not able to see it. Great, then I can make this a little bit smaller. We can go ahead and define the configurations for setting up authentication with next auth right here. So right now it is using the Discord provider, and that is not what we want. We would like to use the credentials provider like so, and just press enter to import that up here. So now it is imported. Then I would like to also just define another thing. So under pages, that is another key up here. We can just open up a new object. And then I would like to define that my sign in page is going to be /login, like so. So that is where I will put my login page up here in the app structure later on. Great. So under credentials, what we will do is just configure it like so. So we'll open up a new configuration right there, and then say name, and that is going to be credentials, like so. And then under that, we'll say credentials, and we'll set email is going to be a new object, and we'll say label email and type email. Under that, we'll just do this exact same thing for password, like so. So this will define two inputs which can be used for the login form whenever we log in with Next.auth. Under this, we'll go ahead and say async, authorize, and then pass in the credentials like so. And in here, I'll just say try. And right under that, I'll say catch. And under that, I'll just return null, like so. And then just put in this missing end clam right there. And then in here, I can say const, and then email and password. And this will be equal to await, and then some schema. It'll be a login schema.pass, and then we'll pass in the credentials. So the credentials can be a couple of different types right here. The type is just unknown right now. So we would like to pass the credentials object as a specific type. That way we can have type safe email and password right here when working with it afterwards. So if we do not have an email and a password and both are not strings, then we would not like to work with it. So let's just go ahead and define this schema. So under source, I'll create a new folder. This folder is going to be called schemas. In here, I'll create one called Auth.js, like so. In here, I'll just say import set from sort. And now we should be able to define a schema with sort. And sort comes with the tier free stack automatically, so we should be all good with that. So I'll say export const and then login schema equals set.object. And this is how the schema should look. So this is how we would like the forms to be able to look. And then email is going to be a set.string.email. And then the error message, if it is not an email that is correct, we'll say invalid email address. And then the password should just be a set.string as well. And it should have a minimum amount of characters, and that is going to be 8 different characters. And if that is not the case, we'll give the user an error saying the password must be at least 8 characters long, like so. And then I'll just say export type login schema, and this will be equal to set.infer, where we'll just pass in the login schema. So now we have both the schema in this format right here, so set.object, and also as a TypeScript type down here. And we can use this schema to validate that this email variable is going to be both a string and also a valid email address. So if you pass in an email that do not have an @ sign like this, for example, so test@something@gmail.com, if you pass in this right here, this validation would fail, and you would then get the error invalid email address. So that is why we pass in this email function call as well. And for password, we just want to validate that it is a string and that it has a minimum length like this. Great. So now with the schema done, we can go ahead and go back to configure. In here, we can just say login schema. So I'll just say command and then dot at the same time. And then I can say add import from schemas.auth. Now that we have this schema, we should be able to verify that this email and password is actually a string, because that is what we check for right here. So under this, what we can do is just say const user equals await db.user.find unique. And then the user would like to find is a user where the email is the email from the login form. So what this method does right here is that it is being called every time a user logs in with the general login form. So either the one that is provided by default from Next.auth or the one we define ourselves. So every time we log in, this method will be called, and we'll need to authorize in our own custom way if the user should be logged in or not. So first thing we do is just check if a user exists in the database with the email that the user just tried to log in with. And this user can then either be a user or it can be null. And null is if the user does not exist. So I'll go ahead and say if no user or no user.password, and password is not a property we have on the user database table yet. So we'll go into Prisma and then schema.prisma, find the user down here, and then we'll just pass in a new column. So this one will be called password, and this password one should just be a string, and it should not be able to be null. So this password should always be set for a user. So I'll close this down, hop down under my npm scripts, and we'll just update both the client-side TypeScript types from Prisma as well as the database as well. So I'll just say Prisma db push, and this will then create the database. So this SQLite file right here, right there, it'll create the SQLite database, and then also create this client library so it'll generate this and make sure that the types match what we just entered as the schema right here. So now we should be able to access password whenever we use the client-side library for Prisma. Great, I'll just close this down again. And then we should be able to say dot password, like so. Good. So if the user is not found or the user does not have a password, we can then say return null. And then under this, we'll say const is valid equals awaits. And then we just need a way to decrypt the password. So inside the database, we'll never want to store the password in plain text. We always want to store the password in an encrypted format. So we can go ahead and just find out what we can go ahead and just encrypt the password the user just tried to log in with right here. And then if that encrypted password matches the encrypted password from the database, then we can log the user in. But we need to encrypt the password first, and we'll do this with a library called bcrypt. So I can go ahead and search for npm bcrypt.js. So that it's going to be called bcrypt.js like this. And then I should be able to just copy this line, open up the terminal by clicking right here, and then terminal. And then under this one, I can just open a new terminal, say npm I bcrypt.js. And then we should be able to import bcrypt. Maybe they have an import statement over here. They did not. So what we want to do is just say import, and then bcrypt, like so, from bcrypt like this. And then right now it is not defined. So we just need to say bcrypt.js instead of bcrypt, and that it could find. And now we just need to do this. And let me just see what it says now. It can't find the type declarations. We'll just try running this command right here, seeing what happens. And then if it's still complaining, what we'll do is just restart the TypeScript server. It does that sometimes. And now we are able to use bcrypt. Perfect. So bcrypt will just give us a way to do one-way encryption of text strings. So just encrypting a password, but never being able to decrypt it back. So what we'll do is just take this password the user just tried to log in with. And now we did find the user in the database because we reached all the way down here through this guard statement. Then we can say await bcrypt.compare, like so. Pass in the password, and then compare that with user.password. So this is the password the user just tries to log in with in the login form, and this is the password from the database. So what it'll do is it'll encrypt this password the user just tried to log in with, and then compare that with the already encrypted password from the database. And if those two match, it'll then set this is valid to true, and we can then log in the user. So I'll go ahead and say if it is not valid, like so. So if not is valid, we'll then just return null. And then otherwise we'll say return id user.id, email user.email, and then also name user.name, like so. So this is what we would like to store in a session, which we'll just create in just a second. So going down, we can just go all the way down to right here, and then we can say session. And we would like to use the JWT strategy, like so, to store the session in a JWT token. This is just automatically set up by NextAuth for us, so we can just use this to store this information right here when the user is logged in. This will give us an easy way to access the ID, email, and name of the user when the user is logged in. Great. We already set up with the Prisma adapter, and then we just need to look into this callback. So to correctly store this ID from the login up here in the session, what I'll do is instead of user, I'll just say token, and then right here I would like to say ID equals token dot sub, like so. So whenever a user logs in, NextAuth will create this new JSON web token storing the session for us. And this JSON web token will then contain these properties, so ID for example. Then every time we want to access the session when the user is logged in, this callback will then be called to create the session object for us, which we can use to access these properties. So it'll decode the JSON web token into a token object, and then transform the token into a session via a callback, so this one right here. And then what it'll do is make the session available to the application, so we'll then be able to just use this ID within the application whenever we want to use or get some information about the user section. So that is what we do right here with the callback. and then also with returning this information up here. So with this done, we should be able to log in a user, but we'll still not be able to create a user yet. We'll still not be able to log in the user before we create the form, but let's just set up also the schema for signing up a user first. So this should be all done now, so I'll just go ahead and close this config.ts file, and then under this login schema, I'll just say export const signup schema as well. This is going to be a set.object2, which will define the validation rules for the sign-in schema. So we will have a name, and that is going to be set.string, like so. We'll also have an email, we'll also have a password, and we'll have a custom validation method, which we'll call confirm password. And this should be a set.string as well. So this will be the field which we can use to cross-check that the password entered was actually the right one the user wanted to use. And then right under that, we'll just create this custom method for cross-checking that these two are the same. Great, so this will be .refine like so. We can then go ahead and say data, and then this arrow notation, so data dot password equals data dot confirm password. Then we can say message is going to be passwords don't match, like so. And then under that, we'll just say path and just put in the confirm password like so. So this will compare the password and confirm password fields, and then it'll return true if they match, otherwise false if they do not match. And then it'll associate the error with the confirm password field right there. So when running the schema validation, it'll both do these rules up here, but also this custom rule down here, checking if the passwords do match together. And lastly, we can just go ahead and create a TypeScript type for that as well. So I'll say export type, like so, and I'll just export the signup schema, which is just set.infer type of signup schema. So now we have both the schema as well as the TypeScript type for the schema. Now I can go ahead and close this tab down, open up this one up here, and then we can go ahead and hop on the app. And then we would like to create the page for signing up a user. So I'll say new folder on the app and then sign up. In here, we'll just create a new file called page.txx. In here, we'll make this a client component since we'll store some state inside the component, and then say export default function sign up page, like so, and just open that up. Everything we return inside this component right here will then be mapped to /signup right here up in the URL bar. So inside here, if I say /signup, then this right here will map down to the following file because it is inside the signup folder. So right here we should create the signup page, and we'll use a couple of things to create the signup page. We'll use a form library, and then also a library to validate the forms up against our schema. So first of all, I'll just search for npm react hook form. So we can just find this under npm and copy the command and just install it down here. So I'll press this plus and just run the command I just copied. And then we also are going to need hook form and then resolvers and then sort like so. So we can just go ahead and copy this one as well, paste it in right here. And then we're going to need to import, I will just let it do that automatically actually. So first of all, we would like to go into this return statement, and we can just create a new div that is going to be the background of the page. So if I just press, or just put in a div right now, press save, and then over here just refresh, we should be able to see the page if we just navigate to sign up like so. So this is spelled incorrectly, it's going to be sign up right there. And now we see this white page, which is just the background page basically. So this page or this div should have a minimum height of the screen, then a bg white, and then inside this div we'll first of all create a header. So I'll say nav, and inside this nav I'll just give it a couple of classes. So first of all, I would like flex, a height of 16, items center, justify, between, border, be like so, and then border, gray 200, and px of 10. Now, if I just save this and open up the nav, then we should be able to put some content into the nav bar. So we have a nav bar with the flex property, so it'll center items on the y-axis, and then space items as far as apart as possible on the x-axis with justify between. It'll put a gray border on the bottom right here, which is what we see, and then force it to be a height of about 64 pixels right now. So under nav, we'll create a new div. Inside this div, I'll put in some class names, flex item center, and then a gap of 2. In here, I'll just put in another div. In this div, I'll just create a little logo for us. So I'll say SA for sentiment analysis. And then I would like to style this a little bit. So instead of creating a logo as a PNG, I'll just do this for now. The logo is going to be flex, age of 8, width of age, items center, justify center, and then rounded, medium. I'll make the background gray 800, and I'll say text white like so. Just save that. And now we have a small little logo to represent our tool. Then I can just say span under that and just say sentiment analysis and style this a little bit. So if I just save this, it'll say sentiment analysis. Then I can just say text large and font medium to just make it a little bit nicer. So this is going to be the logo for our app. So a super simple setup. Now under this nav, I would like to create the main content of the page. So I'll create this new main tag and open that. In here, I'll just put in some classes. So under class name, I'll say flex and height. And the height should be the full height of the screen minus the height of this bar right here, such that we won't overflow the screen and be able to scroll up and down. So I'll say calc to calculate the height, and then put in 100 viewport height minus 4 rem. So this should take away the height of the bar up here. This should be about 64 pixels, which is exactly what this bar up here is for rem right there. Great. Now I can go ahead and say items, center, and justify, center, press save. And then inside this main, we can go and fill out the content of the screen. So first I'll put in a div. This div should have width full, max width of medium, space y8, and a px of 4. Then I can say div inside of this, say text center. Inside this div, I'll put in an h2, and I'll say create an account. Now you can see it's starting to shape up. Under this h2, I'll just say text to Excel and font bold. And right under this, I'll put in a paragraph saying sign up to, and I'll just put in a pedia, sign up to get started with sentiment analysis right here. And then this paragraph should just have the class name mt2. So I'll make some spacing between that and this heading up here. And then I'll also put in text sm and also text gray 600 just to make it blend in a little bit nicely. So this is how it's going to look. And then we'll create the form right under that. So under these two divs, under this div I'll just create a new form. Inside this form, we should have some inputs. So before creating those, we'll just need to define a form up here. So I'll just go ahead and say const form equals use form. So we'll use this use form hook from React hook form to define the form. We'll pass in the sign up schema right there. And then we can go ahead and just say resolver. So that is how it is going to resolve with the sort schema. So sort resolver, and then we'll pass in the sign up schema right there. And then we can say default values for the form will be name, nothing, and then email, nothing, password, nothing, and then also confirm password. And that is also just going to be an empty string. Great. So that'll be the default value for the form once we do create it down here. Now scrolling back down to the form, we can just say on submit. So when we do submit the form, we'll say form.handle submit and pass in our own custom submit method. So this will be on submit, which we'll just go ahead and create up here. So I'll go under this form and say const async function. Sorry, I'll just remove this const async function on submit, and this will take the data right there. So we'll say data, and the data will then be what the TypeScript type we defined up here, and this will be passed to this form through this handle submit method right here. And then inside this form, we can just go ahead and do the things we'll need to do whenever we need to submit the form. But let us first go ahead and create the things we need inside the form. So I would like to show an error state inside this form at some point probably. So that's why I would like to create a use state up here. So I'll say const error and sets error. And that is just equal to a new string that can just be string or null, or a new use state that can either contain string or null. So whenever you do want to show an error, you just set this error variable right here to something that is not null, and it'll then just show this error as a red piece of text down here inside this form. So inside the form, if I just open that up, we can first of all just show the error. So I'll say if error, and then I need to put in these two and signs, and then I'll just show this diff right here, and I'll say rounded MD, and then BG red 50, padding of 4, and then text small and text red 500 like this. Now we would like to just show this error inside of it, so I'll say error, and then just hop up and just remove this null actually. Just set it to an empty string, and I'll just say test error for now. So now we see this test error down here. And then inside this form, I would like to just put in some styling as well. So I'll say class name, and then margin top 8, and space y of 6. So I'll put some spacing in between the form elements. And then I would like to also space the form from this text up here that is right above it. Great. So under this error, I'll put in another diff. This should have the class name space y4 to create a vertical spacing of 4 between those. So that'll be 16 pixels. And then I can say diff inside of this and create the first element. So here I'll put in a label saying full name. This label should have text SM, font medium, and then also text gray 700. Now right under this, I would like to, and I'll just set this to nothing for now, just to hide the error because we don't really need an error for now. Then I'll put in an input. This is going to be the form input, and I'll just close it with a single tag like so. Inside this input, I'll first of all just destructure all these form properties from React hook form into this input tag. So I'll say form.register, and I'll register it with name because that is going to be the name input. And then under this, I'll just say type equals text. Now I can say class name. I'll just put in a placeholder first. That's just going to be John Doe. Save that. Now we have an input. It does look pretty bad though because it is not styled. So I'll just style this input a little bit. So I'll say class name, and then I'll put in mt1 block like so. Then I can say with full rounded MD border gray 300. Save that. Then I can say px3 py2. I can also say text small. Did I do that correctly? No. Text small like so. Then I can say placeholder gray 400, and I can say shadow small, then also focus, and then border gray 500, and focus outline none like this. And then going all the way back, something seems wrong with the border, so I'll just need to add this border tag as well. So now we see the input field and it looks decent. And if an error were to be shown for this input element, we'll just go ahead and show this right under. So I'll say form.formState.errors.name like this. And then I can go ahead and show the error like so. So I'll say new paragraph, and then I can say form.formState.errors.name.message. And I'll just style this a little bit. So I'll say class name, and then mt1, text extra small, and then also text red 500. And if you want to know how the error message might look, we can just put in, I can just make this entire thing a string actually, press save. So this will just have to be true. And then you can see how an error will look for a specific input field like this. Great. So let me just revert that, and then we can hop back down to the next form field. So if I copy this div right here, paste it right under this, I'll just put in some spacing as well. Then I can say email address, and we'll just need to register this as email. Let me just copy this name so we can see all the places where name is mentioned. So right here as well. This type should then also be email, and then I'll press save. And now this should be an email field, and this should be a text field. And then this one does say John Doe, so we would like to say something like you at example.com, like so. So now we have a placeholder for the email address as well. Then I can just put in the two input fields for the password. So if I just copy div right here, and then say password, so we'll need a password and also a confirm password. This will be password here as well. This will be password, and the placeholder should be something along with a bunch of stars like that. Down here it says email again, email. And now we should have the password field taken care of as well. And you see all those small dots, that is because we put in password as the type. Again, if I just copy this password, we can just call this confirm password instead of password. And here we'll just call this, let me just see if you can find it, confirm password like so. Type will be password again. This will be confirm password and confirm password like so. And then under these two divs, inside this form, we can go ahead and create a button. Inside here, we'll, depending on whether we're submitting or not, then we'll just say creating account or create account. So hopping all the way up, we can go ahead and say const loading and set loading, and this will just be false from the start. So this loading variable will keep track of whether the user is currently logging in or not. So when you press the button should be disabled because you shouldn't be able to log in twice in a row if you're already logging in. So we'll set loading while logging in, and then we'll disable the button. So scrolling all the way down to this button right here, we'll say loading, and if it is loading, we'll then say creating accounts. And otherwise we'll say create account like so. And then we'll just need to style this button a little bit more. So the type will be submit to submit the form. This means that this method up here will be called onSubmit right there. Great. So right after submit, we'll say we'll disable it if we are already loading, like so. So if I press save, nothing should happen. And then under class name, what we want is flex full width, and then justify center rounded MD, then BG gray 800, and I can save, and we just start to see it shape up. PX of 4, PY of 2, text small, font medium, text whites, like so. And now it already looks way better. When we hover it, we should be able to see something as well. So this will be BG gray 700, focus, outline, none, like this. And then focus ring 2, like this. And then I'll also color this ring whenever we focus it. So I can say ring gray 500. I can say ring offset 2. And when it's disabled, we'll set the opacity to 50 right there. So now that it is saved, we should just be able to say text sm, and we can just check that we spell correctly for all the properties. So that does look perfectly fine to me. Great. So now we have this submit button as well. And right now we see that we get all these validation errors if we just try to submit the form. That is because it is just validating with the SOT resolver up here whether we have the correct values or not. And you see these errors right here. They come from the schemas. So if I just search for Auth.js, these are the following ones right here. So when it says password must be at least 8 characters long, if we just put in a password like this, then it'll automatically be gone whenever that criteria is fulfilled. So that is the power of using a sort schema like this along with React hook form inside this use form hook. Great. Now down here under the button, I just want to create one more thing. So I'm going to include it inside the form as well. And I'll say P and then already have an account like this. And then I can just put in this empty one right here. And then right after that, I would like to put in a link. So this will come from next link like so. So I'll just press enter to import that. And this link should say sign in. So if you already have an account, you should be able to sign in. So we'll need to set an href for the link. So this will just be login. And let me just save. So it looks not very nice. The paragraph should have text center, then text small, text gray 600. And then for this link, we can just say class name, font medium, text gray 800. And then whenever we hover it, I can say text gray 700. So if I do hover this down here, we see that it changes color a little bit. So that looks perfect to me. Great. Now that we have the HTML ready for the form, we can go ahead and define the logic for logging in whenever you submit the form up here under onSubmit. So whenever I try to log in, I'll say first a try and then catch, like so. And then this error should just say something went wrong. So whenever something goes wrong, it'll just show something went wrong in the error box up here in red that we saw in the start of building out this component. And then regardless of what happens, I would like to always set loading to false. So I'll just say set loading false regardless of what happens. Now under this try, I'll say set loading to true. So whenever we try to log in, the first thing that should happen is that it starts loading. Then I can say const results equals, and then I'll create a new server component, server action called register user like so. We'll pass in the data, and the data will just be this TypeScript type from sign up schema right here. So we can just go ahead and create this register user server action right now. So if I go under source right here, and then I'll create a new folder called actions. This will then contain all of our server actions. So this is code that we can run on the server from a client component, for example. So just like creating an API endpoint, basically, just in a simpler way because it is Next.js. So we can go ahead and create a new file in here, call this Auth.js, and then I can say export async function, register user. And the data which we'll take is just going to be the sign up schema from auth, which we have exported. And then I can just open up the method right there. Great. So inside here, first we would like to do some server-side validation. So I'll just put in a try catch. And the error is just going to be an error right there, like this. So because the reason we use this try catch is because we want to validate with the schema. So in here, what this does, what the sort resolver does, is that on the client, so in the browser, it'll validate all these input fields that the user type in against this schema right here. And if it's wrong, you cannot submit the form. But what you can do is just press F12 and go in and change the code in the JavaScript files or in the HTML basically. And then you can just call this server action with the values that are not supposed to be correct. With the values that are not correct. So because it is because it is client-side validated, we also want to just validate it on the server such that the user do not submit incorrect information that we can then store in the database. So I'll just go ahead and say server side validation as well. So this will just make our app more secure. Then I can say const result equals sign up schema dot save pass. And then I can pass in the data. So we just do server-side validation as well. So in here we do client-side validation by passing in the sort resolver. So that is why if you press create account, you can see all of these errors and you can submit the the form before you fix this error. So, but if you go and press F12, for example, and then tamper with the JavaScript or the HTML, you might be able to submit the form anyways. So we would like to validate the data both on the client, so the user is immediately able to see it right here, and then also on the server, such that the user can submit information that is incorrect. Great. So now that we have server-side validated it, we can check if the server-side validation was correct. So I'll say results.success. And if it didn't match what the rules of this sign-up schema is supposed to be, we can then just say return, and then error will just be invalid data like so. And then after this means that if we get to this point, this means that the data has not been tampered with, and we can then go ahead and try and create a user. So I'll say const name, email, and password equals data. So we'll just destructure the data. Then I can just check if a user exists first of all. So I'll say check if user exists. And then I can say const existing user. So we'll try to fetch an existing user from the database with that email. So we'll say await prisma.user.findUnique like this. And inside this, we'll pass in a where filter. We'll sort after the email, and we'll just need to import the database like so from server.db instead of Prisma. So if this user is found, so if the user is not null, that means that an existing user already exists. Otherwise, if this is null, that means that no user exists, and we can just go ahead and create a user. So I'll say if existing user, then we'll just return user already exists. Otherwise, we can go and create a hashed password. So I'll say const hashed password equals, and then we can import a hash function. So I'll say await hash and then password like this. And then we just need to import this from crypto like so. And what is it complaining about right here? We'll just remove this. Oh, I think we imported it from the incorrect destination. We need to import it from bcrypt.js like so. Great. And this 12 right here is just these salts. And then now that we have the hashed password, we can go ahead and create the user in the database. So I'll say awaits database.user.creates, and then I can just save the created user as well. So I'll say const user, or maybe we won't even need it for anything. I'll pass in the data for creating the user. This will be the name, the email, the password, which will be the hashed password, and then that should be it for now. Then after the user has been created, what I can do is to say return, and then success equals true. If we do catch an error down here, I'll just return something went wrong, and we can then show that error inside this error right here in the front end. Now I can go ahead and just say command and then dot and try and import this server action which we just created. So this results variable right here should then hold error and success, and then depending on what these are, we can then render what we would like to show if the user is successfully logged in or not. So first of all, if there is an error, we can check that by saying if and then results, I'll just call this result actually, dot error, and then I'll say set error, result.error if the error does exist, and then just return, so we won't do anything more of the code inside of this onSubmit. So then I can say sign in after registration, like so, and then I can say awaits sign in, which we can import from nextauth/react, and then I can pass in credentials like so, along with these configuration values, so redirect false, email, which is going to be data.email, and then also the password, which is going to be data.password. Great. So this is a client-side method exposed by the nextauth library, which we can use to sign in. So after signing up, we would like to just automatically sign in if we're able to. And then I can say const sign in results equals await sign in. And then I can go ahead and say if sign in result.error. Then we'll just need to change where the user is currently at. So change the user's page to the sign in page, or not the sign in page, the dashboard page. So up here, I'll just say const router equals use router. So if we import this from next navigation, we'll be able to use this hook to push the user to another page. So if the user is successfully signed in, we can then say router.push and push the user to the dashboard exactly like that. And this can be undefined, so we'll just put in this non-coalescing operator. So if there is no error, we'll push the user to the dashboard. Otherwise, we'll set an error, failed to sign in. Great. So if I just save right here and then hop under the server action, so that is register user, we see that attempted to access server-side environment variable on client, and that is probably because we have not defined that this is supposed to be run on the server. So we'll say use server up here, save, and then now we should be good. Great. So to check that we just create users in the database whenever we sign users up, we'll just say npm scripts, open up Prisma Studio. So that is a studio where we can view the rows in the database. And then I can say user. And right now we have 0 rows in the table. So going over here and then signing up, I'll just say Andreas and then Andreas at gmail.com. And then I can say, hey. And the same down here. Then I'll say create account. And this will then push us to the dashboard. So it seems like it logged in correctly or signed up correctly. And then over here, if I refresh, we have my name, my email, and then also my password, and an ID we can use to associate me with other things we need to store in the database. So now we'll be able to sign in and also sign up users, and we just need to create the login page as well. So we won't need to create a user every time we want to sign up. Login. So to create this login page, I would like to create a page under login. So to map a page to the following route, I'll hop under app, create a new folder. I'll just make this a little bit smaller. This new folder should be called login. And under here, I'll just take this sign up page and copy it straight in because it is going to look very much like the sign up page. And then in here, I'll just hide these two. And then I'll call this login page. And to log in, you only need the email as well as the password. We also need the login schema and not the sign in schema. Sign up schema, and also here login schema. And then we just need to make sure that we use the login schema all the correct places. So for this register user, we'll just comment this out right now because we won't really need to register the user like so. And then down here, we'll need to just remove the form elements or the form inputs that we do not need. So the name you don't need, and the confirm password you do not need as well. And then right here, we can say don't have an account. Oh, that did not go very well. We can say don't have an account, like so. And then this should be called sign up, and it should link to the sign up page right here. Great. So now it looks more like a login form apart from just the text. So right here, we can go ahead and say welcome back. And then we can say, please sign in to your account like this and press save. And then we just need to do a couple of things up here. So first I'll just remove these two lines, which we do not need anymore. And then also I'll remove this comment right here. Then I'll say sign in results. And then if we didn't have any errors signing in, we'll just push to the home page again. Otherwise we'll set an error. And right here we'll differentiate between two different errors. So I'll say set error. And then in here I'll say results dot, and this sign in results dot error. If that is equals to a credentials sign in, then we can say invalid email or password. Otherwise we'll say something went wrong like this. So if we have this credential sign-in error, if that is what this error is called, then we know that we will have an invalid email or password. That is just how Next.auth returns the error. Otherwise, something completely different went wrong, and we might even have the correct email or password. So that is why we do it this way. So this should be enough for us to log in. So I'll just press Shift Option O to clean up all these different import statements. Then just go over here, press refresh, and then say andreas@gmail.com, and hey, and then we just need to change this from create account to login. So this will need to be login, and this will be logging in like so, like this. Then I can say login over here. And now it's at logging in while loading, and now we are logged in and at the homepage. Great. And now I just want to make sure that you can't access this homepage unless you are logged in, because we don't have any logic for doing that right now. So if I right click source and say new file, I can say middleware.ts. In here I can say export default auth, which will import right up here from server/auth. And we'll then receive a request. So this will be run every single time we receive a request to the backend or the server. And then we can just check whether a user is logged in or not. So I'll say const is authenticated equals, and then this request.auth. So we can then know if the user is authenticated or not. Then I can say if is not authenticated, like so. In that case, we just redirect the user to the login page. So we'll just construct a new URL which we can redirect the user to, and this will be const new URL equals new URL, and would like to redirect to the login page. And then this route should be appended to a base URL, and we'll get this base URL from request.nexturl.origin. So the base URL will be this, and we'll then append /login to whatever URL, base URL you do have in the request. Great. So what we can then do is say return response, and which will import right here. So I'll say response.redirect and new URL, and we didn't even have to import it, it was already there, so that is perfect. And then I can say export const config, and this is going to include a matcher. So when do we want to apply this rule? And we only want to apply this rule if you're on the dashboard page, like so, because we will only create a single homepage/dashboard page. So whenever you are on this URL right here, or what we're currently on right now, we want to apply this rule. So if you're not logged in, we'll redirect you to the login page. But if you're on the login page and you aren't logged in, well, that's fine, because you need to go to the login page to even log in the first place. So hopping over here, if we refresh, we do not see anything because we are currently logged in. So I can just press F12, hop under application, and then find my Auth.js cookies, and I'll just press delete to just delete those. Go back under console and just close F12 again. Now if I refresh over here, we are instantly pushed to the login page because we are currently not logged in anymore. So if I just try and go to the home page, we will not be able to access that. If I switch between the sign up and the sign in page, that works just fine because those are not applied to this rule right here. So that is what this middleware will do for us. I can just try and log in again. Log in, and this will push us to the home page, and now we are logged in and able to access all the content on the dashboard page as we would like to be able to. Now we can just go ahead and close down all the different folders, then hop back into source and app, and then layout right here. Then I would like to just change this title right here, description and icon, such that we do match up here with what we would like our app to be called. So I'll say sentiment analysis like this, and then just the exact same thing down under description. And then I would like to just create a favicon icon. So I'll say favicon icon emoji generator like so. And then I'll just say emoji to favicon, and we'll just find some smiley if we are able to. So right here, press close and then download. And we should then be able to just import this into our folder in public right there. So I'm currently just dragging this into the public folder and pressing replace. And then we have the favicon we actually want to show right now. Now I can just press save over here and then maybe restart the server. So I'll say terminal, close all of these down and just npm scripts. I can refresh over here as well. And then I'll press def a again just to restart the server. And then hopefully we should be able to see our new favicon over here. If I just wait for a second, now we see the favicon and it says sentiment analysis like it is supposed to. Now we should be able to create the dashboard page containing all the business logic and then also all the things and functionalities that the user should be able to use when logged in. So I'll hop on the page right here, just close the other pages, and then we can just take this page and delete all the content since we do not need that anymore. So I'll go ahead and do this and just say div and then you're in, like so. So this is what you see when you're logged in. Now, first thing I would like to do is just say sentiment analysis up here, just like we did before. So I'll just take this bar from right here and copy this. This isn't the perfect way to do it. You should probably reuse some of these things in a component, but just to get the front end over with quickly, we'll just go ahead and do that. So I'll just put in the end tag for this div, press save, and now we have this bar up here to show the logo of our app. So what I would like to do is just create a sign out button. So right inside this nav, I'll just create I'll just say paragraph and then sign out like this. And then we'll just create a client component for signing out like so. So I will go to the source, say new folder, call this components. I'll divide the components into clients and server components. So I'll just call this client. And in here I'll say sign out the TSX. And we can then say use client because it will be a client component. I'll then say export function sign out button like so. And we can then first of all get the router. So const router equals use router from next navigation. Now we can say const handle sign out. So what happens when you do press the button? That is going to be an error function that is async. Like this. And we can then say awaits sign out, importing this from nextauth/react. That is the client-side way of signing out with the nextauth React library. We can then pass in redirect to be false because we'll do that manually down here with router. So we'll push the user to router/login and then save. If I just take this sign out button and just import it over here, like so, we'll then just need to import it. What does it say? Void is not assignable in React type node. We'll just need to make this a server component as well before going back actually. Use server, make this async as well. This will make this a server component. And this sign out button will just need to return some HTML and then it'll work all fine. So I'll say return a button that says logout like so. And we'll then just import React icons as well as a library. So npm React icons. We can then just install this by clicking right here, new terminal, pasting it in like that. And then if I just close this down, we should be able to import a nice component. So this will be fi logout like this. And I'll just style this with h4 and width of 4 as well. This will make it 16 pixels tall and wide. I can then just go ahead and you see how this login button is above the logout text. So that is not correct. I would like to make it side by side. So I'll say flex. Then I can say height of 8 like this. And then items center, justify center, gap of 2 between the two. Then I can say rounded, medium, and a border like this. I can then say border, gray 200, a BG of white, a padding on the x-axis of 3, text small, text gray 600 like this. And now it already looks way better, but it does not have any hover state or anything whenever we do hover it. So I'll just say hover bg gray 50 like this, and now it looks better. And then I'll just go ahead and say transition colors like this. Perfect. And now we just need to add the functionality to the button. So if we do press it, nothing happens. So I just need to call this method whenever we do click it. So I can say onClick and just pass in this handle signout method right here. And because we're inside a client-side component, we can use this onClick property for the button elements. So going over here, pressing logout, it'll log us out and push us to the login page. And we then need to log in again before we can continue using the software. So login, and now we're logged back in again. Great. So before moving on with the front end or the dashboard, what I would like to do is just talk data with you. So hopping into schema.prisma right here. So prisma/schema.prisma. We should then be able to create some new tables inside our database. I would like the user to be able to have 10,000 requests per month, and this should then reset every month, so they basically have a quota. So I'll create a new table, and we'll do this by saying model, and then API quota, and then open up this to create this new table. I want an ID, and the ID should just be a string. So I'll say string like so, and this should be an ID, and it should have a default value of a CUID, so kind of like a GUID. Then I would like to have a user ID that should also be a string, and it should be unique. And then I would like to have a reference to a user. So these two will make the reference to the user. And then I can say user, and I can say relation. And I would like to have a relation to the user ID on the user. Sorry, I would like this user ID that I've just defined to reference the ID of a user. So the ID up here. That is how we bind these two rows together. So a row from this table can then be bound to a row from this table. And if we then delete a user, I would like to also delete all the user's API quota rows. So therefore I'll say onDelete cascade. And now it gives us an error because we have only defined the relation one way. So we say, okay, an API quote is related to a user, but we also need to let a user know that it is related to an API quote. So I'll go ahead and say API quota. And this will then be an API quote like so. So one user can have one API quota. So this will just need to be quota instead of quotes. And then one API quota can then also be related to a single user. So what should the API quota table store? Well, it should store the requests used like so. And this will be an integer with a default value of 0. So you start out having used 0 requests. I would like the max requests to be stored as well. This should be an integer with a default value of 10,000. So you have 10,000 requests per month, like this. And then I would like to keep track of when I last reset this. So last reset dates, and this is a date time. And when we first create this API quota, I would like the default to just be now. And then I would like to have a secret key, which will act as the API key for authenticating and then making requests to our endpoint. So I'll just say string and then unique like so. So unique just means that you can only have one row in the table with that specific value in that column. So we only want one API quota to have this specific secret key. So this means that every secret key must be unique. Now, before making this request and then running the inference, the user should also be able to upload video files to make requests to or make inferences on. So we'll create a new table for storing that. So I'll say model, video file. In here, I'll just create a relation to a user as well. So I'll do this, copy these exact lines, and then I'll just make a reverse one up here. So one user should be able to have multiple video files. Video file like this as an array. So one user can have multiple video files, and this is represented by this array form right there. Great. And then a video file should store the key. So this is the key in the S3 bucket to that video file. So this should be a string that is unique because we don't want 2 video files in the table with the same key. That would just be duplicate data. Then we want analyzed, so whether we have run inference on it or not. And this should just be a boolean, and by default that is false, and it'll be set to true when the inference has been run. Then we'll just say created at, just to make sure that we can store when this video file was uploaded. Cool. So this should be it for the simple data structure, which we'll use to build out the front end right here, and then also keep track of which users have uploaded which video files, along with all the requests that has been made to that user's account. Cool. So we can close this down. Then we can say npm scripts, and we can say prisma db push like so. So this will just push the new schema to our database db.sqlite, and also keep the client-side TypeScript types updated as well. Cool. So whenever we create a new user, we just need to also create an API quota for that user, and this will be done inside the Auth.js. So it should be a config file right in here, or not a config file, sorry, the server action right here. So whenever we create a user, we also just create the API key and also a quota for the user to use the service. So I'll just say API quota, and then I'll say create. So this will create both a user record in the user database as well as a record in the API quota database. And we'll do this by saying create inside this API quota key right there. And then we can specify that we would like to create a new secret key. So we'll have to generate kind of a good like secret key, which will then be used as the API key when making requests to our service. So I'll say sentiment analysis and then live, and then I'll say crypto. So we'll just import this library crypto up here, dot random bytes, and then 24 random bytes, and we'll say .to string, and we'll just convert it to string right there. And now we just need to import the correct crypto library up here. So we'll say import crypto from crypto. So this will then generate a long secret key for us. So what I'll do is just say DB Studio right here, hop over and just delete my account. So I'll just log out, click right here and delete my user record, because right now I do not have an API quota because we didn't have this logic before. And then I can just say sign up, put in my information again, and say hey for the password along with create account. And this says something went wrong, so we can just check out what was the error. So unknown argument, API quota, so it couldn't find this. So maybe if we just restart the terminal down here, so I can just go ahead and restart the server, because we did do some changes in the database which did rebuild the client-side library for Prisma. So this might have changed some of the things, and this didn't update quite as well as it should. So I'll just go ahead and do it again. Andreas@gmail.com, and then my password, and then create account. And now it works perfectly fine. So going into Prisma Studio right here, right now it's not running, so I'll just start it up again. And we should be able to have an API quota relation, as we see right there. If I click this and say open a new tab, we can see that it's related to me, the user, and that we have 0 requests used, and we have a max requests of 10,000. We also have a secret key being generated over here that looks kind of like how a secret key would look, so something that you wouldn't quite be able to guess. Perfect. So that is exactly what we wanted. So I can close down this again, just hide the terminal, and close down this tab over here again. And then we can continue with building out the front end. So in here, we can first of all get the API quota. So I'll say get our const session equals awaits session, auth. This will get the session. I can just import this from server/auth, and we can use this auth because we are inside or on the server. So we put in use server right here. This means we can use server functionality, such as the one being exposed right here under the server folder. So this will get the session for us containing a session. So a session will then contain a user and then also an ID. And this user ID we can use to find the quota of the user. So I'll say const quota equals awaits. And then I can say db.api quota and then I can say find unique or throw, because if it can't be found and it's unique, then something is wrong and we definitely need to throw an error. In here we'll just say where, and then user ID equals session.user.id, like so. So this should be able to get the API quota for the user that is currently logged in. Then I can just create a new tag down here or a new element. So right under nav, I'll say main. And inside here, we want the main contents of the page. So I'll first put on some class names, flex, minimum height of the screen as well, width of full, flex call, and then gap of 6, padding of 4. And then when we are above small size screens, we'll then say padding of 10. And then above medium size screens, we'll then say flex row, like so. This is just to make it mobile friendly with the MD and also the SM tags. Great. So what I want to do is divide the screen into two parts, a left part over here where you can run some inference, so just test out your endpoint, and a right part over here showing your secret key, for example, along with some code examples. So I'll just open up this one, and then I'll put in a divider between these two. So I'll say div, and then I'll put some class names on. This should just be hidden, border L, border slate 200. And then when we are on a medium size screen or above, we'll say block. So what this will do is that when we're on the mobile, it will just hide this bar right here, because on the mobile, things should be a column and not a row. But if we are on a computer, so over medium-sized screens, we'll just show it as block. So when we make this on the mobile size, it should disappear, as you see right there. Great. So now let's make the left box first. So this will just be a div, and the class name should be flex height fits with full flex call, and then a gap of 3 and a MD width of 1/2, like so. Good. So this should fill out the first half of the screen, and then we can just copy this div, paste it under the divider, and now we have two divs to contain the content for each part of the screen. Then we can put a heading into the right side. So I'll say h2 and then say API, and just format this a little bit nicer. So I'll say text large, font medium, and then I'll just say text slate 800. And this goes kind of nice with our theme up here as well. Great. So under this h2 tag, we'll just put in another div. And in here, we'll just do some formatting as well. So I'll say mt3 to space the contents of this box or this div from the top heading over here. Flex, height of fits, width of full, flex call to make it a column, rounded, XL, BG, gray 100, BG opacity 70. So like this, and then a padding of 4. I'll just save that. And now we have a gray box to contain some of the elements we would like to put on the screen. So first I'll put in a secret key. So I'll just say secret key, and I'll then say class name, text small, like this. And then we can put in the actual secret key right above this. Right below this, I'll just put in some text describing the secret key first. So I'll say text small and then text gray 500. And this should then be the descriptive text of the secret key. Then I can say this key should be used when calling our API, like this, to authorize your request. Great. So right after this, I'll just say it cannot be shared publicly and needs to be kept secret. Great. So now we have kind of a descriptive text and it looks pretty nice. Good. So right below that, I'll just put in a div. I'll then say class name mt4, flex call, gap of 2. And then on larger and smaller screens, we'll say flex row. Also items center, and justify between. Inside here, we'll put in a span saying key, and we'll just put in the class text small right there. So we will have the key on the left side over here, and then we'll have the actual key, we'll have the text key right here on the left side, and then the actual key on the right side over here. So what we do is we put MT4 to make some spacing on the top part, so right above this to the descriptive text. Then we say, okay, we'll make it flex, and then if we're on mobile, we'll then say flex call. Otherwise, if we're on larger screens, we'll say flex row, so they are next to each other. So instead of key being here and then the key being under that on mobile, on the desktops, we'll then just have the key right here and the key to the right side of that. And then we'll also just center it on larger screens vertically, so they're next to each other. They're centered on the y-axis. And then we'll also say justify between to make this one all the way over here on the left and the actual key all the way over on the right. So that is why we use the classes that we do. And then I'll just, under this key, put in another div. And then this div should have some styling, flex wrap, and then items center and a gap of 2. In here, I'll just put in a span. So I'll just say span, and then I'll just say quota.secretKey like this. So now we do see the key and we just need to format it. So we'll say class name width full, max width of 200 pixels like this. After this, we can say overflow x auto. So this means that we now are no longer able to overflow it and it should be scrollable. Great. Then we can say rounded MD and give it a border like so. And then we need to say border gray 200, px of 3 and a py of 1. So it looks like this. Then we can say text small. Text small right there. And then text gray 600. Great. And then we can just put in, when we're on large screens, we say width of auto right there. Cool. So over here, this looks perfectly fine. And we can see the entire key. And then on mobile sizes, this is how it'll look. So it'll turn into a column instead of a row, but we will still be able to see all the information inside the div. Great. So under this div, I'll create a new button or a new component called the copy button. This means you can click it over here and it'll copy this entire string for you, such that you do not need to do this and then copy it with Control Z or Control C. So under components on the client, I'll say copy button.csx. Then I'll say function like this, and then copy button. And the text we should be able to copy, we'll just pass in as a parameter. And this will then say text string again. And up here, we'll just say use client. We can then just return again. So we'll return the button, and the button should have some class names on it, which we'll set in just a second. So let's first create the logic of actually copying. So I can say const copied and set copied like this equals use state false. And then right under this, we'll say const handle copy. So what happens when you click the button? This will just be an async method like so. And we'll then say try, and we'll try to await the navigator.clipboard.write text. We will write the text, and then we set copy to true. Then we'll set timeout to 2 seconds. Let me just fix this. Great. So what happens here is that when we click the button, we'll then call this method. This will copy the text to the clipboard, set copy to true, and when copied is set to true down here, we'll show some text that says, oh, it was just copied, by the way. And it'll show that for 2 seconds, and then it'll set copy to false after those 2 seconds. So down here, we can now go ahead and say copied. So if copied is true, we'll then say, oh, it was just copied like this. Otherwise, we'll say copy, so you know that you are able to perform an action. Good. So if I just take this copy button and import it over here, right under span, like this, we just need to export it maybe. So export default copy button. I can just import it over here, and we see the copy button. We just need to make it a little bit nicer. If I click it, nothing should happen yet. So if I just put on click and just pass in the handle copy, we then just need to pass in the secret key as the text like this. And now over here, if I click copy, it says copied for 2 seconds and it disappears. So that was the exact effect we were hoping for. And then we just need to put in an icon as well. So I'll say copied. So if we just click copy, we'll put in fi check like this with the width and height of 4, so 16 pixels, width of 4, and a height of 4 as well. So we just need to import this fi check. And if we didn't just copy it, we'll just put in fi copy and just import that as well. So it'll look something like this. And when you copy it, then we have this check mark right here, and this will disappear after just a second. So what we need to do now is just format this button class or this button styling a little bit. So I'll say flex to make them side by side, age fit, width fits, items center, justify center as well, like this, gap of 2, and then I'll put in rounded, medium, border gray 200, BG white, PX2, and PY1, like this. Then I'll just make the text a little bit smaller, so I say text SM. Then I'll say text gray 600. And then when you hover it, I'll say BG gray 50. And then transition colors like this. So when we do hover it, it looks nice and has a transition to it. I can then press copy. It looks pretty decent. And it works. So if I go over here and press paste, we do see the key. So everything looks to work exactly like it should. So we can now move on with the functionality over here. So under this div right here, we'll create a new div. We'll say class name empty3, flex, height of fit, width of full, flex column, rounded XL, BG gray of 100 again. So we'll create the same kind of box, BG opacity of 70, and then a padding of 4, like so. So now we have the same kind of gray box right under the other one. And then I'll just put in another div inside of this. So I'll say div, and we should be able to just copy some of the things up here. So we have secret key. Instead, we'll just say monthly quota, like this. And then we'll just put in some descriptive text under that as well. So we'll just do this. And then we'll just put in this down here. And this should then be saying quota.requests used out of quota. This is then just max requests. And we'll just say requests after this. So now we can see how many requests we have used. So it'll look kind of like this. Great. So what we can do is just take this and position it on the right side over here instead of below monthly quota. And then we can actually put in a progress bar down here instead. And I think that will look kind of nice. So I'll put this inside a div, both of these, and then just put some styling on that. So this is going to be flex call, and then gap of 2. And then it's going to be on larger screens, flex row, items center. And then it is also going to be justify between, exactly like this over here. Great. So right under this div, I can then go ahead and put in another div. Here I'll put in some classes. This is going to be empty1, height of 1, width of full, rounded, full, bg gray 200. Now just save, and we can see the background of the progress bar right there. And then inside this progress bar, I'll put the div that is actually supposed to be the progress that moves to the right as you use more requests. So this will have the class name h1 again, rounded, full 2, bg gray of 800, so you can actually notice the difference like this. And then we need to adjust the width based on how much quota you have used. So I'll say style to make a calculation. I'll put in the width, and then the width should be calculated based on quota.request used divided by quota.max requests times 100, and then we can just append this percentage symbol to it. And now we see that we have used 0 requests. So if you, for example, use 500 requests, you'll have used this much. So this will kind of visualize how it looks like that perfectly. And then I would like to also have some documentation down here. So I can go ahead and create a new component under client and call this code examples.tsx exactly like this. And then in here I'll say function code examples, and go ahead and open up a new function where I just return a div, for example, like this. I can then say use client and then just copy code examples in right here. So code examples, and we just need to export that as default. So export default code examples, and we should then be able to import it right there. Great. So now this component should be able to display some documentation right down here. So inside this div, I'll first put in a heading. So I'll say span and then just API usage like this. Great. And then we can just format that a little bit. So we'll just say text small. And then right under that, we'll just put in some descriptive text. So this will be text extra small, a margin bottom of 4, and then also text gray 500 like this. And then instead of API usage, we can go ahead and say examples of how to use the API with TypeScript and CUL curl. Great. So we just need to format this a little bit nicer. So I'll say div and then mt3 like so, and then flex hfit with full flex of column, and then rounded XL like so. And then I can say bg gray 100 and bg opacity 70. And then I can put in a padding of 4. So now it'll look kind of like the other ones up here. And if I just make this text small instead, then it should actually also match what it is up here. So it looks the same. Great. Now, right under this span, I'll put in another div like this. And inside this div, I'll just give it a couple of classes. So I'll say overflow, hidden, rounded MD, and bg gray of 900 like so. Good. And then inside of that, what I would like to put in is another div. This should have class name flex, then border bottom, and then a border gray 700 like this. And inside this div, what we can do is just place in a button. So this button will say TypeScript. So I would like to create a little menu of being able to pick between different programming languages, for example. Then you can click that and then see different code examples for each right under this. And then we have a border bottom to separate the buttons from the documentation itself. So this button will then look like this. So TypeScript, and then I can say class name, and this should be something that is determined based on variables. So first of all, up here, I'll just create a use state for keeping track of which button is currently active. So I'll say active tab, set active tab equals use states, and the types should be either TypeScript like so, or it should be curl, and we'll then just start out with TypeScript as the default one. And let me just import use states. Great. And then down here under class name, I can say px of 4, py of 2, text extra small, like this. And then if this tab is the active tab, so if active tab equals TypeScript, then what I would like to pass in to the classes is bg gray 800 and text whites. Otherwise, if it is not currently active, I'll say text gray 400 and put on hover text gray 300. So now it looks like this. And when we then do click it, I would like to just change it to the setting that we clicked. So I'll say on click. And if we do click it, then we set the active tab and we set it to TypeScript in case we click this button. And then we can just copy this entire button. And right down here, I'll just call this CUL instead. And then just set this to CUL like so. And now we just need to input curl here. And then we can switch between them like so. So when we do hover them, we can see there is a difference right there. Great. So that is exactly what I wanted. And then down below, we can then put in the text itself. So I'll say div and then class name, I'll say padding 4. And then inside here, I can put in a pre. Then I'll say code inside of that. So we can then say something like public static void, blah, blah, blah. And then we can just format the pre first of all. So I'll say max height of 300 pixels. And then I can say overflow y auto to make it scrollable, text extra small. Like this. And then text gray 300. So it'll look like this regardless of the menu now. And then we just want to replace this code based on which option you have currently chosen. So we can go up and just define what the code should be in each of these cases and just switch between those whenever you click the different buttons. So first is the TypeScript code. So I'll say const ts code equals, and I'll just do this so I can do multi-line. Then I can say one get upload URL. So this will also kind of serve as how we're actually going to use the API in our own code. So first thing we'll do is just say await fetch, and we would like to fetch an API endpoint which we'll called API and then upload URL like so. And we would like to pass some things to this fetch request. So first of all, the method is going to be post. So let me just indent this a little bit. So the method will be post, like so. And the headers will be the following. Authorization, that will be bearer plus our API token. So your API key basically, like this. And then right under this, so the next line, what I would like to do is just put in the content type, and that is just supposed to be application JSON. Now under this headers right here, I can go ahead and define the body, and the body should just be JSON.stringify, and then it should be file type, and then .mp4 right here. And let me just remove this one right there. And right down under, we can then go ahead and say .then, and the result will then be run through this .json method right here. And I'll just indent that a little bit as well. Oh wait, I won't actually. So down here, what I can then do is just say const and then CUL code. Just do something like that as well. And then down here, I can say active tab equals TS. In that case, what we'll do is just show the TS code, otherwise we'll show the curl code. Great. So it'll look something like this. And then when we switch between them, we won't be able to see the TypeScript code anymore. So I'll just format this correctly. I'll put in 2 spaces instead of this tab, so it'll look a little bit better. So kind of like this. And then for this one, I'll just say it's 2 spaces as well, right here as well. And then it should look way better. Great. So the first thing you do is you get the upload URL. So our endpoint, or we'll create an endpoint to get an upload URL, and then you can do a fetch to that upload URL, which will upload the video you want to run inference on to the bucket in S3. And we'll just document how to do that as well. So I'll say to upload file to S3. Then I'll say await fetch. And I'll then fetch to the URL, which we just got. So up here we'll say const URL and a key, like this. And we'll just say we'll fetch to the URL, passing in the parameters, method being post, for example. And then the headers will be content type video MP4, exactly like this. And then under this we'll put in the body, and this will be a video file, so some kind of file right there. Great. So next we have uploaded the video to the S3 bucket, and what we'll then do is just say free analyze video. So we'll say const analysis is another fetch call to our backend, and I'll call this sentiment inference. And to this call I'll put in a method which will be post, like this. And for headers I'll then just go ahead and pass in authorization and content type, exactly like that. And then under this, so right there, then under this I can just say the body, that is supposed to be JSON to stringify the key to the video in the S3 bucket which we want to run inference on. So whenever we upload, or whenever we get the upload URL, we both get the URL to upload the video to, along with the key to where it is located in the S3 bucket when it has been uploaded. So whenever we do want to run inference, we just pass in that key from the initial request to then get the result back from the inference on that video. Cool. So down here we can then say, we can go ahead and do this, and then dot then to just await it basically, and then we'll just run it through this JSON again. Cool. So if I just go ahead and save that, like this, we should then have the full example right here, and it should be scrollable exactly like we want it to. And then maybe up here I can just press delete once so it's moved up. Perfect. And then what I'll do to get the curl code is just take all this right there, and then go to ChatGPT. So I'll just use this one. You can also use ChatGPT over here in the browser. And I'll just say convert to curl instead, pass it in, and run the query. And what we should then see is the curl code, because we don't want to write it to curl code that is not really relevant. So we'll just wait for this to finish. So I'll just go ahead and do this instead. And we'll then just call this curl code like so, and press save. Now if I press curl over here, we then see it as curl code, and this isn't really something I've worked that much with, but that's just how it looks apparently. So now we have a couple of examples of how to use our API. So this kind of aligns with how an API SaaS should look like. So now that is done as well. So we can now move on to creating the following endpoint right here, API/upload URL, and this is just what we'll create inside this API folder. So I'll just close all folders, go under source, app, API, and right here I'll create a folder under API, and this is supposed to be called upload URL. This will map that URL to the API which we can call. Then we'll create a file inside of that called route.ts, like this. In here we'll export an async function called post, so we can receive post requests. We'll receive a request of type requests, like this. Exactly. And in here, we'll put everything into a try catch. Like that. And the first thing I would like to do is just get the API key from the header, because we do pass in this API key right here, which is the following one up here, just to make sure that we can count up the person's monthly quota or the user's monthly quota. So I'll say const API key, and we can get that from the headers of the request because we pass it in under headers and then authorization. So I'll say request.headers.get authorization, and then I'll say dot replace, and I'll replace this bearer with nothing because we do pass in bearer as well. And then we should have the API key in its pure form right there. Good. So now that we have the API key, we can say if no API key, then we, instead of throwing an error, we return a next response, like so. And .json. Good. And we just need to import next response. And what we want to return is a error API key required. So if we do not find this API key, so that is why we put in this optional chaining. If this is not a valid key inside this dictionary of headers, that means that the API key was not passed to us in the request. So this will just be set to undefined. So if it is undefined, we'll just return this error API key is required, and then just along with a status 401, like so. Great. So if the API key does exist though, we'll then find the user by API key, like this. And to do that, we'll say const quota, because an API key belongs to a quota, and that we can get from awaits database dot API quota dot find unique, like so. And we want to find it where the secret key from the database matches the API key and what we would like to select from the row that we find. So we'll say select is the user ID, so we can know which user ID or which user that this API key belongs to. So that is the logic behind it. Then I can say if not quota. So this can be undefined if you pass in an invalid API key. And if that is the case, we'll then just return a next response saying invalid API key along with the status as well. Good. So under this, I'll say const file type equals awaits request.json, so we get the request as JSON. And file type we can get right here because we send it in the request. So we pass in file type JSON, file type right here as the body. So we can just take the body, so the request as JSON, and then get the file type out from that. We can then say if file type is not there, and file type dot match, and then we can put in a regex. So this is going to be one that matches video files. So I'll just put in a backslash, first a forward slash, then a backslash, and then I'll say dot, and this will be MP4, or it will be movie, or it will be AVI. Then I can put in this one right here, /I. So we have created a regex that checks if the file that was uploaded matches either MP4, movie, or AVI, like this. And then if it doesn't, then we'll say return next response.json. So I'll then say error, and then invalid file type, only these are supported. And then I'll just set the status to 400, so a bad request. Now, if that is not the case and the file type is correct too, I'll then say generate upload URL that will return to the user. So to do this, I can say new s3 client, and this comes from a library we'll need to install. So this library is going to be called AWS SDK and then client s3, like so. So we can just take this one and copy the install command, hop back over here, open up the terminal, a new one, and just install that. And that should just take a second. Great. Then down here I can say const s3 client equals new s3 client. We'll just need to import that from here. And then I would like to create a new S3 client based on the environment file, environment variables describing the AWS region, access key ID, and also secret access key. So this will be the the user we created earlier that is allowed to invoke the endpoint and also upload to the S3 bucket. So we'll need to put in the region. This will be environment, like so, dot, and then AWS region. Then we can put in the credentials, and this will be environment.aws key ID, and also the secret access key. And notice how these are type safe. You can see that it's a string. That is because we have defined them in here inside this env.js file. Great. So under this, we can then say, let's just save this. We can then say const ID equals crypto.randomuid. So we'll generate a random file name for this file inside the bucket, such that all files have random names that do not conflict. So we should only have one file name, all the file names should be unique. So there will only be one file name per file. So we'll say const key equals, and then inference, and we'll like to pass in the ID as the key for the file in the bucket, as well as the file type, which we got from up here. So that is the file we would like to be able to upload. Then under this, I can just say const command. So this is the put object command equals new put object command, like so. We'll specify the buckets. So the bucket will just need to get from AWS. So I'll just open that up. So I just opened up the bucket, and we can now go under properties and ARN, copy that. And then in here, what I would like to do is just hop into environment and say inference buckets equals the ARN of the bucket, and I'll just prefix it with AWS, like so. Now, and we can just add this to this environment.js file to make it type safe. So I'll copy this line, paste it in, and down here, I'll also just do the exact same. AWS inference bucket equals process.environment.aws inference bucket. And we can then just grab this bucket right here from the environment.aws inference bucket right there. Great. So I'll just hop back to localhost, and then under this AWS inference bucket, we'll just need to put in some other configuration values. So one is key, so where we would like to, what we would name the file, and also where we would like to put it. And then we can also put in the content type. This is going to be video, and then we'll need to concatenate the actual type of the file, because we do have different types we support. So we'll say, file type dot replace, and we'll replace the dot right here with nothing. So we want the file type to look something like this, the content type to look something like this, video at MP4 for example, but the file type right here will look something like this, .mp4 or .avi. So we just remove this dot. This way we can get the correct type we want. So video / and then just the file type without the dot. So that is what we're doing right here. Great. And now we have a problem where it says invalid environment variables. So we can just go ahead and see if we can find that. Down here, we say AWS inference buckets. And this is what we have referenced all these different places. If we do go into environment, that is what it is called there as well. So maybe we just refresh the server. So I'll just go into npm scripts again and reload the server, see if that changes anything. And it looks like it works now. So that is great. It was just an error because we changed a couple of things without it knowing about it. Cool. So now that we have this command, we can then get a signed URL, which is a URL we can send back to the front end, and then they can then make a request to that URL and upload the file through the URL. So we'll say const URL equals awaits, and then get signed URL, like so. And let me just see if we can import that. So it comes from npm and then AWS SDK requests pre-signer, like so. And this is a package for itself apparently, so we just need to install this. And let me just close down the server again because we just installed the new package. And we should be able to import it now. Great. Then we can pass in the S3 client along with the command, and then how long out into the future this UL should last. So we'll say expires in 3,600 seconds. So this is an hour. Now if we then go under npm scripts and press def, we should be able to start back up the server. And then under UL, now that we have generated this UL, we can then create a database record. So I'll say awaits database.videofile.creates, and I would like to create a video file with the data key equals key, and then user ID equals quota.userID, and analyzed should be set to false by default like so. Great. So now we also know in the database that we have created this UL such that we can check whether the same user who created this UL is also the user running inference on the file. And what we'll then do is just say return next response.json, and we'll just pass in the URL, the file ID, which will just be ID, and then we'll pass in file type and the key like this. And if we catch an error, I'll just say console.error so we can log it in the console on the server side and just see what's wrong. And I'll say upload error plus, just comma error like this. And we'll then also return an error, so just an internal server error, so an error 500. And this will then have the status 500 like so. So, it already had 500 right there. So this should be perfect. I just need to close it correctly. Great. And now that we have this first API endpoint down, so API/upload UL, the user will then be in charge of uploading the file to the S3 bucket. After that, the user can then use this endpoint, which we'll just create now. So this is to run inference on a file that the user has already uploaded to the bucket. So I'll just remove this code examples and page and just create a new folder under API. This one is called sentiment inference. And in here, I can just take this route right here, and copy it into it because it'll look kind of like the same route which we have already built. Great. So inside the sentiment inference routes, what we'll do is first of all the same with getting the bearer token. So this logic we can reuse. We can also again find the user by the API key, and we can then also check whether the user has an invalid API key or not. But in this request down here, the user will send a key as a parameter in the body. So we'll check for the key right here instead of the file type, which we did up here. File type right there. Great. So going over here, we can just delete this logic, which we don't really need. So all of this with generating the upload URL. And now we do have the key. I'll just delete this as well. Now we have the key, which is the location in the S3 bucket to the video that they want to run inference on. So I'll first of all say if, and then not key. So if the key is not passed as a parameter in the body, then we'll go ahead and say return next response.json key is required with a bad request status. Now after this, we can go ahead and say const file equals awaits, and then database.file or video file dot find unique, and just check if the user who made this request also owns the file, and we can check that by the key. So we can say where key like so, and we can then say select user ID true and analyzed true. So we get the user and also if it's analyzed or not. Then we can say if not file, then we can say file is not found. Then we can also say if file.userid is not quota.userid. So if the file that the user is trying to run inference on does not belong to the current user, then we say unauthorized. So we can then say return next response.json. I'll just copy this right here and say authorized like this, and we can then pass in a 403. Let me just make it uppercase. Great. Next we can say if, and then file.analyzed. So if it has already been analyzed and ran inference on, we can then return file already analyzed. Next up, we can actually check if the quota is enough to to run inference on the file, and then run inference if it is the case. So we'll say const has quota, and we'll just create a method for that now. So we'll need to check whether the user has enough quota or not, and then if the user has reached the end of the month where the quota should be reset, we'll also just do that inside this action right here. Or not action, I meant a function. So I'll go under source and then create a new file. First a new folder. I'll call this lib. So this is just for library. This is just for business logic that fills a little bit too much out here in the route. So I'll create a new file called quota.ts. Inside this one, I'll say export async function. Check and update quota like this. We'll pass in the user ID, which is a string, as well as the deduct from quota, which is a boolean, and this should just be true by default. Then we can say we return a promise of a boolean, so whether the user has enough credits or not, and we can then open up the method like so. Now first we get or create the quota, so I say quota equals awaits database, which we'll just import .api quota .find unique or throw, and we'll find it where the user ID is the user ID. So now we can find the user's quota. Then we can check if we need to reset the count over here because it is a monthly quota. So once a month we need to reset this. So I'll first get the point in time right now. So const now equals new date like this. Then I can say const last reset, which is a column inside the database for the API quota. So last reset, and we can then check the difference between these two. This will then be new date, where we pass in quota dot and then last reset date right here. And this needs to be now and not new. Cool. We can then get the time between these. So we'll just say if 30 days has passed, that's about a month for now. So we'll just go and reset it if 30 days has passed. So I'll say const and then days since last reset equals, and that will then be now.getTime like so, and then minus last reset.getTime, and then this calculation right here will then determine how many days has gone by since the last reset. Cool. So what we'll then do is say if, and then days since last reset is greater or equal to 30. So if 30 days has passed, we'll then say if deduct from quota. So deduct from quota is true. So the parameter we pass into the function up here, if that is true, then we'll say awaits database.api quota.update, and we'll update where the user ID is the API quota that belongs to the user, and we'll set the last reset date to right now, and then we'll also set request used to 1, because we are currently calling this as we are trying to make one of these requests, and I think that should be it. So down here, right over this one, we'll then just say return true. This way out here, we can then know whether we have quota or not, and it will be true if we just reset it, because then the user will have plenty of quota left. Cool. So below that, we'll then say check if quota is exceeded. So if we are not within 30 days of the last reset, then we'll just check if the quota has been exceeded and then just deny the request if it has. So I'll say if, and then quota.requests used is larger or equal to quota.max requests. In that case, I'll return false. So this means the user will not have quota left and we won't fulfill the request. And then I'll just say if deduct from quota. We can then say awaits database.api quota.update and just say where user ID, and then we can increment the request used by 1. And of course we do need to return true down here as well. So we'll say return true like this. So if the quota is exceeded, we'll return false. Otherwise, if we have set this to true, then we return this regardless of whether this has been set to true or not. But if it has been set to true, then we just deduct a point from his quota, so by adding one of the requests used. So this will count up the monthly quotas over here. Great. So we just need to call this method, so check and update quota over here. So we'll just say await check and update quota, and we need to pass in the user.id, which we'll get from up here somewhere. So this will be from the quota. So we'll say quota.userid, and we'll pass in true because we would like to deduct quota whenever we run inference. Great. Then we'll say if not has quota. In that case, we'll return a next response.json, and we'll then say error is monthly quota exceeded, like so. And we'll then also return the status 229. Great. And we'll just need to say return correctly right there. So if the user does not have enough quota, then we'll just return the response monthly quota exceeded, and we'll then know in the front end, wherever this is called, that we do not have more quota left. Great. And otherwise, the user will actually have enough quota, and we can then go ahead and call SageMaker. So to call SageMaker, we'll need another library. So AWS SDK and then SageMaker runtime, client SageMaker runtime, like so. We'll copy this install command, open up a new terminal and install it. And we can then just close down the terminal like this, and then say call SageMaker Endpoint like that. Cool. In here we'll just say const SageMaker client equals new SageMaker runtime client, like that. We'll then pass in the region as well as the credentials, so exactly like we did in the other route. So right there. We also passed in some credentials and a region, so it's just to establish a connection to, or just establish that we do have the right credentials before making the request. Great. So then we can say const command, and then we'll define the command we would like to send to the endpoint. This is going to be a new invoke endpoint command, like so. And we'll have to define the endpoint name. So going back to our other solution, right here with the video sentiment model, so this is the entire Python codebase, we can then find the name of the endpoint. So under deploy endpoint, we can see endpoint name right here. So I'll just copy this and then head back. And now that I'm back, I can then go over to environment variables like this and say AWS endpoint name equals, and then the endpoint name. I'll just quickly add that to the environment variables as well right here. So there, and then just define it as a string up here. Now we can just say environment dot endpoint name, and then that is all good. Then I can say content type, which will be application JSON, and the body, which we would like to call the endpoint with, is going to be JSON.stringify. And we'll then just pass in the video path like so. And the video path will then be the buckets. So right over here, if I go ahead and press Inference and just copy that URI, this will be the one. So the video path will be formatted like this. And then instead of inference, we'll just put in the key because the key should include inference. And we'll just remove that so it works. And then under this command, we'll actually send it off. So we'll say const response equals await SageMaker client.send command. We can then also say const analysis equals JSON.parse. and we'll pass the new text decoder like so, .decode response dot body like this, and that should then give us the full analysis. And now that we have called the endpoint, we can then go ahead and just mark the video as mark the video file as analyzed. So I'll say awaits database.videofile.update where the key is, and then I can say data and analyzed should then be set to true, and the sentiments we do not store yet, but you can do that if you want to. And this of course just needs one more of these closing. Great. Under this I can say return next response.json, and I'll return the analysis. So this is the analysis we get back from the SageMaker endpoint, and this is then inside our endpoint, and we'll send that all the way back to the original caller. And instead of upload error down here in the catch, we'll say analysis error like that. So this should take care of this entire step in here, where we say analyze video, and then inside the front end, we should then get the analysis like so, and we can then use it inside the front end to show all of the analysis all of the inferences for the video. So let me close these pages down, hop into page right here, and this is where we would like to do that. Now let's create a component that handles uploading the file and then also handles calling this endpoint with the uploaded file and showing all the results. And we'll do all of this in the left side of the screen right here, because now the right side with the documentation has been taken care of. So I'll hop all the way up to right under main, and this is the divider we see right here in the middle. So right above that is going to be the left part of the page, and I'll create a new component called Inference like this. And what I want to pass in is a quota, and this quota should then contain a secret key, and that we get from the quota.secret key like this. So now all we got to do is just take this component under components and client and just create that inference.tsx like this. In here I'll say export function. I'll just make this a client component first of all. Use client. So I'll say export function, and then inference is what I called it, will receive quota, and then we will create inference props, and then this is just a type, so an interface up here called interface props, receiving quota containing secret key like that. In here we'll create a div that looks kind of like the other page over here, also the other side. So I'll just take this div right here and copy it into inference. So I'll say return and then the div. I can then just say h3 inside of this, and h2, and then call it inference, putting in the class names text large, font medium, and then text slates 800 like so. So now it says inference is not defined, so let me just hop back and import that like this, and we just need to spell inference correctly. So now we have a little start for the left side of the page over here. So I'd like to create another component called upload video. So under client components, I'll say upload video.tsx, and then in here I'll just say const function upload video like this, not even const. In here I'll just return nothing for now, and then I'll just say export default upload video, make this a client component, then import it over here. So right under this h2 I'll just say upload video, and then to be able to upload the video, we need the API secret so we can make the fetch call. So we'll just need to pass down the API key. So this will be quota.secret key. So we'll just start doing that. And then in here, we'll just say API key, which is a string. And we'll just make that an interface just like we did right here. So I can just go ahead and say upload video props and just set the API key as a string like that. Exactly, great. So now we can first go ahead and create a use state that sets the status of what we're doing. So the status can be either idle, it can be uploading, or it can be analyzing like this. And we'll just set it to idle, so that's when nothing is happening basically as the start. Then when the video is uploading, we'll then show uploading right here inside this upload field. And then when the video is being analyzed, so when we call the third endpoint right here, that's when we show analyzing. So this way we can show the user that something is actually happening, so it doesn't just show processing for the entire, for all the steps, for example. We can then also just create a use state called error and set error for showing any errors that might happen during the upload, for example. So use state string or null, and then I can say const handle upload. So this is what is going to happen whenever you upload a file. This will be an async method receiving a file as the input. Good. Then hopping down to the HTML itself, we can say return div, and it should take a class name flex with full flex call and gap2 like this. We'll then put in another div inside of this. We'll put in some class names. This should be flex with full like this, cursor pointer, then also flex call items center, justify center, a gap of 2, rounded Excel, border dashed, and then border gray 300, and a padding of 10 like so. Now opening up this div, we can just put in an input. So you might see what we're doing already. We are creating a drop zone basically. So it should look like you can drag a file onto the drop zone and just upload it. That's also why I put cursor pointer onto it, so you can tell the user that will be able to click it. Then we are making it item center and justify center, just to make sure everything inside of it is centered. We are rounding it, and we are putting on border dashed. That makes the border not solid, but like dashed, so you have all these small holes between the border. Great, so that is what we're doing. And then inside this div, we'll put in the input, so what we can use to upload the file. So we'll say type, and then file. We'll accept, and this is what we'll accept. So video MP4, video of type movie, or video of type AVI like this. Now, if I just save this, you see that it looks absolutely hideous. So that's why we'll put on the class name hidden. So we still want to be able to click this to open up the file picker dialog, but we do want to hit it though, or hide it though, and then open it up in another way. So I'll just go ahead and say hidden for now, and then we can say ID equals video upload, and then create a label that will instead open it for us, so we don't have to show this ugly button. Now we can then say on change, so that's when you do pick a file, we'll then receive an event. We can then say const file equals event.target.files 0, so the first file, and we can say if file, then if the file does exist, I'll say handle upload like this, and pass in the file to match this type right here. So that is what happens if we do pick a file. Now, since we can't click this anymore, we'll need some way to click it. So hopping down under this input, I'll then say label, and I'll say HTML4, and I'll pick video upload like this. I can then say class name flex, cursor pointer as well, flex call and items center, and just save that. Then up here, nothing happens yet if we do click it. So we need to just change a couple of things. You see there's no content inside this label, so it doesn't really fit much space. So if I just say height of, 20 for example, and then a width of 20, then we should be able to click it up here, and it'll trigger this input because it is a label with HTML for video upload. So we need to put some content into it so that we will be able to click it. Great. So we can then say if I upload, just a file icon from React Icons. We can then say class name, minimum height of 8, minimum width of 8, and then we can say text gray 400, press save. So now it'll look kind of like this. Then after this, we can just put in a h3. So we'll inside this based on the status say, so let me just do this. If we are uploading, then we would like to say uploading. Otherwise, if the status is analyzing, then we would like to say analyzing. Otherwise, we say upload a video like this, and that should take care of it all. So now it says upload a video, and then if we do upload one, it'll start the entire process up here and handle upload, and this will then set the status to either idle, uploading, or analyzing. So that is why we handle it this way. Great. Now we just need to style it a little bit because it doesn't look very nice right here. So I'll say class name, text MD, margin top 2. It'll look like this now, and then we'll probably need to say font medium and text slate 800 like so. So now we have this kind of heading thing, and then under this we'll just put in something else. So we'll just say p and then get started with sentiment detection by uploading a video like this, and we'll just style this as descriptive text. So text extra small, text gray 500, and then it looks like this. So this is something that looks pretty nice, I would say. I can then just say text center to center it like this. Now it looks even better. And then this error we created up here earlier, we just need to be able to show. So under this diff, I'll just say if error, then I'll show a diff with the class names text small, and then text red 500, and then we'll pass in the error like this. So let me just emulate that. If this error right here is hello, then the error would look kind of like this. So that is what would happen. Great. Now hopping up to this handle upload, that is basically what will execute the following code inside this documentation, or from this documentation. So we can just go ahead and implement that. So let me just first take this code and paste it into handle upload, and then we need to do a couple of things. First, we need to take this API key from API keys up here in the parameters. Then we also need this video file, and also we need the API key down here. So now we just need a video file, and this will be file.type like this. And of course, we do need to change a couple of things. I would like to put this inside a try catch first of all, so we can show an error if it doesn't work. So I'll put this inside a try, and then also a catch down here, and we'll catch an error. And if we do catch an error, we can then show it in the error field down here. So we'll say set error, and then error dot message like so. And because error is unknown, we can then say error instance of error. Then we can say error dot message. Otherwise, we just say upload failed like so. And then we can also say console dot error, and then we say upload failed error like this, and then we just throw the error again. So that is how we're going to handle the error. Great. So all the way up here inside this try, we first set the status to uploading like this, and then we set the error to null such that if an error is showing already, then we want to reset that in case another error happens, or in case it actually succeeds uploading. Then we can get the file type. So I can say const file type, and that will be equal to dot like this, and then file.name.splits, and we'll split it at the dot, and then we'll say pop to get the file type. And then down here where the file type has been hard-coded, we can just take that and pass it in instead, like so. And then we also want to check in between the steps if they actually succeeded. So I'll say if the results that okay, if result is not okay. So I'll just say result right there instead. And then down here I can say const URL file ID and key, like so, equals results.json. And then I say result right there, that okay. So if the result is not okay, then I say const error equals awaits rest.json, because then the JSON will include the error. Then I can say throw new error, and this will then be error.error. Otherwise, if that doesn't exist, fail to get upload URL, and I'll just make this a null coalescing operator in case error does not exist. And then down here, after uploading the file, I can just say const upload results equals this, and then I can say if upload results.okay. So if the upload result is not okay, then I can just throw this new error, failed to upload file, and then I'll say set status to analyzing, because now we have uploaded the file to S3. So first we were uploading, now we are analyzing, and then the user will be able to follow the entire journey. And then when doing the analysis, I can just find where this ends. Then I can say if analysis is not okay, then we throw a new error, fail to analyze a video, like this. And then under that I can say const analysis. So this is it, everything succeeded. Then we'll say awaits analysis.json. And then because this upload video component isn't the component that is supposed to actually show the results from the analysis, we'll pass the analysis which we just received from the endpoint all the way up to the parent component. So we'll go ahead and define another method we can called on analysis. This will take an analysis. We'll just set this to any for now. And then I can just get it on here, right here. So on analysis, and then scrolling all the way down, we can just call on analysis. So I'll say on analysis right there, and just pass down the analysis, or pass up the analysis to the parent component. And then since everything is done now, we can say set status to idle again, so let the user know that they can now upload a new video. And then I would like to just say console.log analysis and just print it out, just so you can see it in the terminal before we even create the view. So going back to the parent component, so upload video is used inside Inference. We can just create a use state, so const analysis set analysis, and this will again contain the entire result that we get back from the endpoint. And remembering back to the Python code, you can take a look at that and see what we specifically returned. But what we did return, if we want to create a type for this response from the endpoint, is the following. So I'll just say export type analysis equals, and then we have utterances. So for each utterance, remember we created inferences, and inference has a start time, it has an end time, it has a text, so the transcript, also the emotions. This is an array of type label, which is a string, confidence, which is a number, and we have the same for sentiments, like so. So that is the type we're working with. So I'll just it is export already. I'll just use it down here, and then also in upload video I'll use the same. So I'll say on analysis, we'll just pass down the set analysis method right there, and then in here we can just say analysis instead of any, and then the types should match perfectly. So inside this inference component, I would like to show the averages of all the utterance scores, such that we can show a single score for the entire video. So which is the most prominent emotion and also the most prominent sentiments. So we'll have to take the average of all the emotions to find the most prominent emotion and do the exact same for sentiments right here. So I'll just create a couple of types which we'll need just to be able to do this. So first I'll create one called const emotion emoji. This isn't a type, but rather just a dictionary I can use to map between the labels. So anger, for example, and then over to an emoji. This will be a record where we'll have the label and then also the emoji. So this could be anger and this could then be the emoji. It'll look something like this. Anger, that'll be an emoji. And then we'll need disgust and then fear, like this. And then under this we'll create joy. Under this we'll create this neutral, like that, and then sadness. And we can also put in surprise, like so. Great. And I'll just do the same for emojis, for sentiments. So I'll say sentiment emoji. And for sentiments, we had these three. We had the negative one, like this. Then we had neutral. And lastly, we had positive, like so. Great. And then I'll just create a method for calculating the average scores for the emotions and also the sentiments. And I'll do this inside this inference component right here. So I'll just make this a little bit smaller and then say const get average scores equals this one. So just a normal method like so. And then I can first say if analysis dots. So if this is null, and then utterances dot length. If that is not there, so I'll just need to change the type up here. This is not a single dictionary, but an array. So I'll say array, where the type of the array items is the following, and then we should be able to take the length right there. So if that length is not there, then we'll just return null. Otherwise, we'll say aggregate all scores, like this. Then I'll say const emotion scores, which will be equal to a dictionary. And the type of this should be a record with the label. So angry, for example, or since it's emotions, it could be anger, for example. And then a number of scores like this. So this is just a number of the confidences, which will then aggregate into this dictionary right here. We'll then also say sentiment, like this, and this will be the exact same data format. Now I can just loop through all the different utterances and then calculate, put all of these different confidences into these dictionaries right here. So I'll go ahead and say analysis dot utterances dot for each utterance, like this. So we'll loop through all the different utterances. Then I can say utterance dot emotions dot for each. Do the exact same, so just loop through all the emotions. Then I can say if not emotion scores label, then I'll just go ahead and add a new empty array as this number right there. So a new empty number array. And then not otherwise, in any case, I'll say emotion scores, emotion label, and then I'll push the confidence like so. So we're looping through all the utterances, and then if you find a specific emotion, because we loop through all the emotions as well. And then if that emotion, so for example, anger up here, is not pushed to this emotion scores array yet, then we'll just push this number array to this dictionary, to this dictionary up here. And then we should be able to push the confidence score right after that as well. And the TypeScript server doesn't really pick up that we do create a new array up here at all times. So we'll just need to go ahead and put in this null forgiving operator just to let it know that we have it under control. And then I'll just copy this for loop right there and thus just call this sentiments instead. And then sentiment like this. And then we just do the exact same for the sentiments. So this will be sentiment scores like this. And then we should have the aggregation of all the different emotion scores and sentiment scores. Great. Now under this, I'll go ahead and say calculate the average. So to do this, I'll say const average emotions equals object.entries. And I'll put in the emotion scores object like so. And then I can say .map. So this object .entries will give us the keys and also the values of each dictionary item up here in the dictionary. So I can then say .map, and I can get the label. So let me just see if I can get this to work. So label, and then also the scores from this. And then I can open up a new function like this. Great. And then I can say label and then confidence, which will be scores.reduce. And then I'll get one object and then another one after this. And then I can say A plus B and 0 right here. And then divided by scores.length. So this should calculate the average score of the emotions from all the different confidences, and then put this into this average emotions right here. So this will contain the average confidence for each different label there is. So anger, for example, or joy. So we go through all the key value pairs in emotion scores, and then for each of these, we map them to another array, which is the following one right here. And each element inside of this array will have the label and then also the average of those confidences. And we get the averages from summarizing all the scores first of all, and then dividing that summarized scores with the scores.length, so the amount of scores. Good. So we can then go ahead and do the exact same for sentiments. So I'll say average sentiment like this, and then we can say sentiment scores instead of the other one. And then I'll just need to, I think that should be fine actually. Then I'll take each of these, so average emotion for example, and I'll sort each of these elements inside of the array by the confidence, and I'll then take the label with the highest confidence average. And that is going to be the one that I assume is the highest emotion or the most prominent emotion in the video. So I'll first of all sort by confidence, and then I'll get the top score afterwards. So to sort them first of all, I can say const top emotion equals, this will be average emotions dot sort, and we'll have two elements in this sorting algorithm which we'll define. So this will be one given element, so B for example. This will be another given element, so A for example. So this is how we tell the sort function to sort between elements, and we'll sort based on these confidence variables for both A and B. So by going through all of these different emotions in the array, we can then take the confidence for any given element A and any given element B and sort them by comparing the confidences like so. So that is how we sort it. And then we can just take element 0, and element 0 is going to be the one with the highest confidence. So we'll just do the same for top sentiments as well. So const top sentiment, and we'll then go ahead and say return top emotion and top sentiment like this. Now I'll just take this method we just created, and down here I'll say const averages equals get average score like this, and then call it. And then we can use this to render out these scores over here on the left side, and then actually show them to the user once the user uploads a video. So right under this upload video, I can first put in a new heading. So I'll say h2 and then say overall analysis. Save this, and then we see it over here on the screen. Good. So now we have overall analysis, and then I would like to just say averages, since it can be null. We first want to say if analysis. So if the analysis is not null, then what we would like to do is the following. So let me just put in some HTML right here. So I'll just put in a div for now. And then if it is null, I would like to put in an empty state, and this empty state should just be something like upload a video to see the overall analysis. So I'll just put in an empty div here as well. This empty div should contain a span. The span should say upload a video to see overall analysis. Great. And then we just need to format this to make it look a little bit nicer. So this h2 up here, I'll put on some class names. I'll say empty2, text small, text slate 800, like this. And then for the span, I would like to say text small, like this. And then also text gray 400. Exactly. So now it looks a little bit nicer if we see it like this. And then for this diff, I can just put on some classes too. And these will just be to make it look more like the empty state. So I'll say class name and then flex, height of 32 with full, item center, justify, center, rounded XL. I'll put a border on it, border dashed, then border gray 200 and a padding of 4 like this. So now we have the same kind of box as the upload box up here, but it's a little bit more subtle with the colors. So that's going to be the empty state before a video has been uploaded. And then right above this, if the analysis is present. So we'll just first of all make analysis not null. I will just say true right here, just to show the other case, like this. If that is the case, then I can put in another diff. And here we'll just say class name as well. So flex, age, fit, with full. I'll also put in flex wrap, then items, center, justify, center, a gap of 4, rounded XL, border gray 200, a padding of 4, and then on large screens, so not on mobile, I'll put in a gap of 8, and then also a padding X of 6, like this. Good. So now we have a box where we can put in the content. So I'll just make the code a little bit larger, and then just open up this diff right here. Inside this, I'll first put in a diff with the class names flex call, and items center. Inside this, I'll put in a span saying primary emotion right there. Under this, I'll just style this already. Class name text small, great. And then under this, I'll just put in another span, and I'll say text 40 pixels, so way larger, like this. In here, I'll just put in the emoji itself, so I can say emotion emoji. And then if I say label right here, for example, or sorry, sadness right here, for example, this should then reflect in the UI over here. So we then see sadness. So I can then use the averages.topemotion.label to find the correct label to show. And then if I just put in averages up here and then make this null forgiving, it should then work whenever a video is actually uploaded. So I'll just go ahead and create a new span under this. I'll copy this one. So we'll have text small and then also text gray 500. This one I'll call, or in this one I'll show the label itself. So if the span right here shows the emotion, I would like to say sadness under this, and then also the confidence level, so the score as a percentage. So first I'll say averages.topemotion.confidence, and then right after this I'll put in averages.topemotion.confidence. I just need to fix this by closing them correctly, like so. And then I'll say averages.topemotion.confidence times 100. Then I'll say 2 fixed like so. 0, so number of digits after the decimal point, and we'll set this to 0. And then we'll put in a percentage sign right here as well. And then this just needs to be null forgiving, and then we'll get no errors right now. Great. So I'll just copy this box and paste it down here. And then I can say overall or primary sentiment. So now we have the primary emotion and then also the primary sentiment. And this will just need to be sentiment emoji. And I just need to put in top sentiment instead of top emotion, like this. And just go ahead and save that. Now to test it out, we can just go ahead and create some demo data for this averages variable up here. So inside the use states. So what I'll do is just open up Copilot. You can just take this entire piece of code and put it into ChatGPT as well. And then I would like to say populate the use states with some demo data according to the analysis type above. Great. And I'll just tag the inference file right here. So I'll basically just take all the code and put it into the prompt as well. So I'll just do this so we can just see how it is going to look in real life. So it should be ready in just about a second. So we have some demo data right here. So I'll just copy this in a second. Great, so I'll just copy this object right here with the demo data. Like so. And then make sure to get all of the data. All the way up to analysis right here. So I'll copy this and just set this as the default states inside the analysis, right so. So it is going to look something like this. So right now we can actually already see a couple of errors. So first of all, this toFix did not seem to work very well. So going all the way down, we can just add this toFixed. We can just add this toFixed to the confidence up here as well, because this is the number being shown right here. And this should then remove all of the decimals, or just the one we want. We'll just set it to 3 for now, both there and also down here. So now it looks way better. We have the confidence right there and also the decimal point, also the percentage right after that. So one thing that looks pretty weird over here is that we have this big space right here that seems to take up half the width of this inference, left side of the dashboard. So we'll just go ahead and figure out why that is. So if we can just select with the select over here, if we just select right here, we see this big purple element. So selecting this, we can go into main and then try to figure out what it is. So this is the culprit right here. So apparently we put in one too many of these divs with the width 1/2 right there. So we'll just go ahead and find this and actually remove it. So searching for these classes over here, we can then find where it is. So let me just close down this so we can see it. So it is going to be this one right here. So we actually moved this one inside Inference, and then that should fix how it looks. And it did. Great. Good. So going back into Inference, we can just continue with the left part of the dashboard right here. And what I would like to create is just a list of all utterances and then their scores, so their emotions and also sentiments, such that you'll be able to scroll down through the utterances and see the transcripts for each along with their start and end times in the video, and then also what emotions they had. So we'll both have the overall analysis and then also the summary, also all the individual utterances down here, just so you can scroll through them if you would like to do that. So first I'll go up and copy this heading right here and then paste it down and say analysis of utterances like this. And then under this, I would like to put in the specific, div showing all of these analysis, but just for the individual utterances. So under this, I'll create a new div, which we just need to close again. Oh, it did it automatically now. So first I would like to use the same structure as we did here. So I'll copy down this right there, and I'll just make it outside the div actually. And then also the following right here. So this is going to be the entity states right down there, and then the state that we do show if averages does exist. So if the averages does not exist, we'll just set this to true just to test it out. False. Then we can say upload a video to see analysis results like that. And then we can just go ahead and fill out this one. So we can say analysis. We can just put this inside a React fragment first of all, and then say, just a div with the classes flex call, and a gap of 2. Then I can put in this mapping where we loop through the different utterances in the analysis. So I'll say analysis.utterances.map. Then we'll get the utterance, along with the index of each utterance. And in here we can then just return a random diff for now, or just a React fragment like this. So what I would like to actually return is a diff. So I'll just say diff like this, put in a class. We just need to close this since it didn't auto close. And then for the classes, I would like to put in flex, height of fit. Then also with full, flex wrap, justify between, gap of 8, rounded XL, border gray 200, padding X of 6, padding Y of 4, and then on larger screens, we can put in gap 4 like this. And then we can just fill out the different utterances inside of this diff right here. So first of all, I would like to put in the time and text. So I'll just comment this out, put in a diff. Inside this diff, I'll just put in some classes. So flex width full, max width 24, flex call, and justify center. And then I can go ahead and put in another diff in here. Here we'll say text small and font semi-bold. Then we can show the from and to time from the utterance. So I'll go ahead and say number, pass in the start time. So that is going to be utterance dot start time. And then I can say dot to fixed to keep only a single decimal. And then this is the start time. So I'll just go ahead and say 2. And then copy this entire thing. Then over here, I'll say end time and just save that. So if I up here, instead of analysis, just paste this in, we should be able to save and then see the start times and end times of each utterance down here. We do have one error though. Each child in the list should have a unique key property. So that is going to be this list right here. So every time you have a map where you render out different elements, you need to put in a key. That key could just be something specific to that element. So I'll say key, and then let's see if we can find something, utterance dot. So we could put together the start time and then also the end time. So utterance dot end time like this. And we can just say dot to string to make them unique. So that's one way for us to do it, like this. And that should remove the error. And then I'll also just put in the transcript as well. So under this diff right here, I'll go ahead and put in another one and say utterance.text like this. And then just style this a little bit. So MC1, text extra small, and then text gray 500. And we then both have the time from and to time as well as the transcripts from the utterance. Good. So hopping down under this, I can just put in the emotions. So I'll just say emotions. What happened there? I'll just say emotions and comment this out. And then diff with a closing tag, say class name, flex with full, max with 48, flex call, as well as gap 2 right there. And then inside this diff, I can put in a span, and this span should say emotions. And I'll style the text a little bit, so I'll say text extra small and font medium, like this. And right under this, I'll just go ahead and say emotions or utterance.emotions.map and loop through all of these. So each emotion is going to have an emotion along with the index. So inside this map, what we'll return is a diff like this. This diff should have a key first of all because it is inside a map. This key will just set to emotion.label, and we can then just put on some classes too. So this will be flex, items, center, and gap of 2. Then I can put in a span. So we'll put in emotion emoji. This will be emotion.label, like so. Otherwise, if that is not, does it work? Yeah, it works perfectly fine, like this. So we'll just press save. So now we have the different emotions. And then I'll just put in the label as well. So I'll say emotion.label, press save. And now we have those two. And we just need to style these a little bit. So width 16, like this, text extra small, and text gray 500. So it looks way nicer now. And then it seems like I can't find the emoji for surprise up here. So we can just go ahead and see what is going on. So surprise, why can that not be found? Oh, surprise. So we just want to make sure that it is actually existent. Then with that fixed, we can scroll back down and pick up where we left. So that is going to be right here. And then under this band, we'll put in a div. So I would like to create a little progress bar showing how big the confidence is. So just like we have the progress bar up here, I would like to do the same, just between 0 and 100, so the confidence. So what I can do with this div is first give this a flex1 class. Then inside this div, I'll create the background color for the progress bar. So I'll say h1, and then I can say width full, rounded full, and background gray 100. Inside this, I'll put in another div, which will be the foreground color for the progress bar. So this will have some styling and some classes. So the class name should be h1, with full as well. Or I'll not make it with full, I'll make it rounded full. And then background gray 800. And then the width will determine based on a calculation. So I'll say style and then pass in the width. And the width will be determined like so. Emotion.confidence times 100. And then we put in a percentage sign as well, right there. And that should give us the confidences like so. And then lastly, I would like to just put in a measure, so just a piece of text that also shows the confidence, such that you do not only have to look at this progress bar. So I'll say span, and then emotion.confidence. So I can go ahead and say emotion.confidence times 100, and then .2 fixed. So just put in 0 decimals, and I'll just make this a percentage number as well. So like this. And the span obviously needs to be formatted just a little bit. So I'll give it a width of 8, text right, and then also text extra small like this. So now this is our final result for the emotions at least. So what I should be able to do is just copy this entire thing for the emotions and just call it sentiments instead. So down here, sentiments. So it'll look like this. Great. And then we just need to put in the correct wordings. So sentiments, right here it'll be sentiments as well. And for emotion, I'll just replace it with sentiment. And the emotion emoji should be sentiment emoji, like that. So that should give us the most predicted emotions and also the most predicted sentiments, exactly like this. So one problem I see right now is that negative right here breaks into 2 lines. So in some lines it is not broken between the emotion and the label, but in other lines it is. So that's not something I would want. So we have the emotion right here and then the label right there. So we should be able to say white space, no wrap, and press save. And this will then fix this error. So we just need to do this for both the sentiments down here as well as the labels up here like this. So now it should look better already, and it does. So with this done, we can go ahead and just delete all the dummy data. So if I hop to Inference, scroll all the way up, and just delete this dummy data, we can then spin up the endpoint and see if it works end to end. So we shut down the endpoint, so we just need to get that back up and running. So now I'm back inside the video sentiment model repository, and this is where we can deploy the endpoint. So if I just right click deployment, open integrate terminal, say Python, deploy endpoint.py, we should be able to deploy the endpoint, and I'll come back whenever this is ready. The endpoint has now been deployed. And hopping back over to this setup, we can just hop into our AWS and search for SageMaker. And we'll just check that everything is up and running as it should be, although nothing has changed, so everything should be fine. So it is in service, and hopping into the logs right here with the model container logs, we can just take the newest one. So this one right here. And it looks perfectly fine to me. We see that it downloaded FFMPEG correctly as it should, and we don't really see any errors down here, so everything looks perfectly fine. Great. So hopping back into sentiment analysis, I'll just close down this one and this one. And what I've then done is downloaded a video. So if I press upload video, we can see the video I've downloaded right here. That is just a clip from a friend's episode, and it should be about 2 minutes long. Yeah, 2 minutes and 19 seconds. So this should be plenty of utterances that our program can enact on and then create this analysis from. So if I try and just press open and just see what happens. Right now it says rest.json is not a function. So maybe we need to just go ahead and do that and fix that. So if we just search for rest.json over here, we can go ahead and see if we can fix that. So this is in the upload video right there at line 33 or 36, const error equals rest.json, exactly like this. So I see that we are doing this rest.json twice, so both right here, and we do actually also await it. So we can just go ahead and remove this .then statement, and we then just do this one as rest.json down here. And then we of course also need to just await, so await rest.json down here as well. And then let me just see if we are doing this then anywhere else we shouldn't be doing it. So right there, we can also just remove this statement because we're doing this .json both here. And then we should also do it if we want the result from when we throw the error. So I can just say const error and do the exact same method down here. So failed to analyze the video. So this is how we're going to do this. Now if I then go over here and just refresh, open up the terminal, we can just try again and just see if we can get some more information. So we get a 500 internal server error, like this. So we should be able to open up the terminal and see if we can see that internal server error. So just opening this up right here, we can see upload error and then invalid ARN, unrecognized format. So we put in the full ARN for the bucket under this get signed URL I can see right here. So that is AWS Inference buckets. So let me just check out what that value is under environment variables, Inference bucket right here. So maybe we need to just remove the following and only pass in the name of the bucket. Let me just try and save and then refresh over here. So it reloaded the environment variables right there. So we should be able to try again and just see what happens. So if I say upload video, friends clip, then we get an error again, failed to upload the file. So I was digging around, and what I found is that if I go into the schema.prisma file, so schema.prisma right here, and go down to the video file, whenever we are inside this route upload URL, we try to create this new video file. So this is just a row in the video file table right here. And I set user ID to unique, which means a user can only have one video file row created per user, because otherwise the query will fail to Prisma. So we'll need to just remove this. This was a type error or typing error. So we need to just remove that, say Prisma db push, like this, and then just restart the server. And then we can try again without getting this error, because now we should be able to create multiple video files for the same user. If I refresh over here, upload again, let me just see if we get another error. So we get the failed to upload file. So going back into the upload video, we can look at how we are uploading the file. So right now we are doing a couple of things wrong. I can see that under body, we need to put in the file, not the file.type. And under the headers, we'll need to put in the actual file.type instead of this right here. So this was just hard coded, but what if we upload a .mov file, for example? So I can say file.type right here, and this will need to be a put as well. Oh, what did it do? File.type, great. So now we should be set for actually uploading the file. So let me see if I can fix that step now. So now we are actually uploading something. So that seems promising. And then down here, we can see if we are actually able to having the video being analyzed. So now it is analyzing. So it looks promising so far. So we can just see what the result is whenever this is finished. So we got this error right here. And what we can see is the following: failed to execute JSON on response body stream already read right here. So this res right here is not the analysis results. It is the results from the initial request. Good. So now that that is fine, let me just try and upload it again. Good, so now we get a result, and the result down here is the following: your invocation timed out while waiting for a response from the container primary. So if we hop into SageMaker and go under the container logs, we can then just open up the logs once again and just check if anything is unusual. So if the model had failed, we would be able to see it in the logs, and maybe it will time out because of that. But it seems like it didn't time out in that way. So there's not really any reason to worry about the model failing. So it seems like we might just have uploaded too big of a file. So we did upload 2 minutes. So what I can do is try and cut the video down to just a single minute, and we can then try and upload that. So I just went into the folder in my downloads folder and cut the video down to just a single minute. So if I just hop back, say upload a video, and then pick this 1 minute one, we'll just try and see if that should fix the error. And now it says analyzing after uploading for a couple of seconds. And this is what happened as soon as it was done analyzing. So it seems to have worked out fine, but we do have an error here. So we have this printout of the analysis. So we do see the analysis with inferences for all the different utterances. So the endpoint works completely fine. So we can just find out where we did print out this console.log. And I think that is inside the upload video. As soon as you do upload it, yeah, we have the analysis right here. And then we see an analysis object inside of that. So the type is probably wrong under analysis. So if I go ahead and add analysis right here, and then just wrap the utterances in that, we can then just try and redefine the types here. So dot analysis, and then this would be dot analysis again. And we just need to add it down here. And let me just see if we have any more problems. No. Good. So I'll try and re-upload the video, and then hopefully it will work this time. So open. And it just finished analyzing after uploading. It took about 20 seconds. So this is the result. We get a primary emotion, a primary sentiment like this. And then we also see the analysis of each utterance. So you'll be here to me, and no, come here to me. And then we get the different emotions and sentiments. So it seems to work out just fine, and that is just great. So now we have something that actually works end to end. But one thing I do want to fix is the following API usage over here. So this documentation obviously didn't work, but we also did write it out quite quickly. So I'll just go ahead and find out where we use that. So I remember COL is something, yeah, right here. So we can take this code examples and actually just update this with the code we just wrote. So under upload video, if we hop down to analyze video right here, we should be able to just copy this entire piece of code like so, and then just hop under code examples and then just put this right under the TypeScript code like this. And then if I scroll up, we'll just see the error right here. So the file type will just set to MP4 like that. And then I'll just remove the following indents, both there, and also if I just copy this entire piece of code and just press Shift and Tab a couple of times just to remove the indents. If I then just save, we should see the updated TypeScript code right here. And then I'll just ask ChatGPT to do the exact same for the curl code. So if I just take this piece of TypeScript code and paste it into ChatGPT and say convert to curl code, like so. Then we should be able to see the updated curl code down here as well. So we have a result right here, and this is the CUL code. So I'll just take this and paste it in right there and save. And now we should be able to see the updated CUL code as well. Great. Now I just want to remove the indents here, so this looks nice too. And now all the code documentation should be updated as well. So great. And as you might have noticed over here, whenever we have made requests, this monthly quota has updated. So we have used about 14 requests. This has been both us testing, but also me testing in the background whenever some of these errors occurred. And I just needed to figure out what the problem was. So we do see the monthly quota increasing right here, as well as our 10,000 requests. And this progress bar have moved just a little bit. So our program works end to end. But let's just go ahead and talk about what we can do about the issue with only being able to have the invocation for about 60 seconds, because that is how long the total invocation time is for Amazon SageMaker AI endpoints. So what can we actually do about this if we do decide to upload a video that is perhaps 2 minutes long? So this timeout issue is caused by the invocation timeout in AWS SageMaker Endpoints. So we have about 60 seconds worth of computation before the endpoint will time out and stop the script completely. And if it times out, we won't get any results back. So because we upload a full video and run inference for every single utterance, if the video is long enough, we'll have a bunch of inferences and they'll all take time, so it might time out. So what we can do is perhaps just optimize the endpoint. So maybe we run inference for only every second utterance, or maybe we filled out some utterances that we deem not worth running inference on based on some fills, for example. So there's a couple of different ways to optimize the endpoint, and this was just one of them, for example. Another thing you could do is introduce a constraint in the front end or in the API saying, okay, you can only upload 60-second long videos and not more than that. So you can upload a 10-second video, but not a 61-second long video, for example. So this is kind of annoying for the user because you won't really be able to upload very long videos, but it can be necessary if we do have this timeout issue and we aren't able to optimize the endpoint enough. We could also be able to support this max duration, this 60-second invocation timeout by chunking the video. So this would require building out some more complex logic, but it could be worth it in the end. So we would then take a 4-minute long video, for example, break it down into 4 videos of 1 minute per video, and then just run the invocation for each one of those videos, and then just aggregate all the results, so all the utterances like we are currently doing. So this would mean our backend would just make 4 invocation calls to this endpoint instead of just a single one. If we do this, the invocation time would take a long time because we would have to make 4 different invocation calls, each taking about 60 seconds. So this would be 4 minutes in total at maximum of processing, and that's quite a long time to wait for the user if they decide to wait. Additionally, one thing you could also do is maybe train a model to take longer videos. So if you had another dataset with even longer videos, so you didn't quite train on small utterances like we did with the MELT dataset, but instead trained it on like 10-second long transcripts, for example, with videos, we might be able to pass in longer clips into the model and thereby also optimize how long it takes to run the inference. This would only be a good solution though if it takes short time for the model to run inference with longer clips than running inference a bunch of time on shorter clips. So in case you have this timeout issue yourself, these are the options you have, or at least some of the options you have to get around the problem. So I hope this made sense for you. Now we have successfully trained this AI model from scratch using AWS SageMaker training jobs. We have also deployed the trained model as a SageMaker endpoint, allowing us to run inference on the model in the cloud. We have built this simple frontend that allows the user to upload videos and run inference on them. The frontend was not the main focus in this video, instead learning to work with AI was. Therefore, it is quite simplistic and doesn't have features that allows the user to buy more monthly quota with Stripe, for example. It does serve as a pretty fine starting point for building a SaaS around a trained model though. So if you want to keep working on this project, I recommend you trying some of the approaches I presented to you in Excalidraw to support inference on longer videos without timeouts from SageMaker. You could also try to deploy the frontend by first running the linter in VS Code and then fixing the lint errors there might be. After this, you could create a Postgres database through Vercel Neon and then deploy this this app to Vercel. So congratulations for making it this far. I really hope you enjoyed this tutorial. I put a lot of hours into it, so let me know what you would like to see next time, and then I'll try to accommodate that.